Preface. This book was written for those who love beautiful buildings and wonder how they stand up. Inspired by the constructive instinct of man, I have studied, taught, and designed structures for a lifetime. I now write about them in the hope of sharing with others my excitement and their beauty. This book offers the reader both the history of some of the great monuments of architecture and an explanation of why they stand up. Chapters on architectural technology usually precede those about the monuments made possible by a particular technology, but some may prefer to read about architectural masterpieces before finding out why they stand up. Since great architecture is the successful marriage of art and technology, the enjoyment of the story I have to tell does not depend on how the book is read. Mario Salvadori. Why Buildings Stand Up. The Strength of Architecture. 1. Structures. The beginning of architecture. Compared to other human activities, architecture is a young art that had its beginnings only 10,000 years ago when men and women, having discovered agriculture and husbandry, were able to give up roaming the surface of the earth in search of food. Until then they had been exposed to the weather, precariously protected by tents of animal skins. Perpetually on the move, they cooked over campfires and gathered in small tribes. All of this changed when people became sedentary. Tents were supplanted by more substantial abodes, and a permanent hearth became the center of the home. Numerous huts sprang up in fertile areas, contact between families became more frequent and intimate, villages grew. From village to village a network of paths was worn. At times paths had to cross rivers and ravines, requiring the construction of footbridges made out of tree trunks or suspended from ropes of vegetable fibers. The clustering of huts created the need for larger huts where village problems could be discussed. These larger structures served both as town halls and churches, since spiritual needs have always gone hand in hand with the physical. Indeed, the larger monuments of archaeological architecture were often motivated by spiritual needs. The last 10,000 years spanned more than 300 generations, but we who have witnessed the incredible changes brought to our cultures by the Industrial Revolution may feel that architecture has not changed much, at least over the last 6,000 years. This constancy in the built environment should not surprise us, if we realize that architecture satisfies basic physiological needs, which have not changed since Homo sapiens appeared about 3 million years ago. We eat the same kinds of food as our prehistoric ancestors, and we cook food much as they did. We sleep on horizontal surfaces, though surely softer today than then, we protect ourselves from the weather, and we procreate in the only way we can. Architecture is the most conservative of the human arts and sciences because it caters to these unchanging needs of man. Even our spiritual needs, which may have changed somewhat and may have produced different rituals, are as basic today as they were in prehistory. Changes in architecture, more quantitative than qualitative, have been motivated by the conglomeration of people. The city is a friend to architecture. Whether we gathered first in villages, and then towns and cities, the better to defend ourselves from enemies, or whether the change of trades and crafts required the proximity of first hundreds, and eventually millions, it was the city that led us to erect taller and taller buildings and to enclose larger and larger spaces. In 2000 BC, Minoan cities on Crete already boasted 4-story houses, and tenements in the most popular sections of Rome had risen as high as 10 stories. We are the heirs of these builders. We think of ourselves as the most individualistic human beings in history, and yet we gather in large halls to see the same spectacles and live in beehives containing hundreds of identical apartments. Nostalgic as we may be for the simple life of the forest, most of us find the ways of the city more congenial and more efficient. In the United States, over 75% of the population live in cities of more than 100,000 people. There are at present in the world 20 cities with over 7 million people, of which 3, New York, Chicago, and Los Angeles, are in the United States. We have become members of group cultures. The relative isolation of the countryside is no longer our way of life. Science and technology at their best are motivated to satisfy genuine human needs. If architecture has never changed much in its functional aspects, it has undergone a fantastic technical revolution. The needs of the city will be satisfied, and technology, spurred by the discoveries and inventions of the industrial and scientific revolutions, has come to help. Function and structure. The purpose of a building is to perform a function. The function of most buildings is to protect people from the weather by creating enclosed structures, but interconnected spaces. These spaces may be many and small, as in apartment houses, or few, perhaps even a single space, as in a church or theatre. The function of the building is fulfilled by the construction of surfaces like walls and roofs, which separate the outside from the inside. But walls must be pierced by doors to let people in and out and by windows to allow the penetration of light and air. Roofs must prevent rain and snow from entering buildings. By analogy with the human body, the functional envelope of a building is called its skin. Within this skin, the separation of internal spaces demands the construction of floors and partitions, while circulation between floors requires stairs and elevators. The structural components of a building assure that the elements required to fulfill its function will stand up. Columns, beams, and floor structure make possible the architectural function. Even in the tense of our ancestors, the functional and the structural components were clearly separated. Animal skins created the inner space and protected the dwellers. They were the envelope or functional component. The center pole and the ropes staying it made sure that the skins would stand up. They were the structural components. Again, by analogy with the human body, these structural components are called the skeleton or frame of the building. It is in the development of structure that architecture has undergone a revolution. Our high-rise buildings, now reaching heights of nearly 1,500 feet, and our covered stadiums sometimes spanning 700 feet, require structures incomparably more complex and stronger than those of the past. Their development demanded both new theoretical knowledge for design and new materials for construction. In the past, structures were erected by the time-honored method of trial and error. Each builder would dare a little more than his predecessor until, faced by failure, he knew that the limits of his structural system had been exceeded. The daring brick dome of Hagia Sophia in Constantinople, first built in AD 537 and one of the largest domes of antiquity, fell twice before it finally stood. It stands to this day. The exceptionally high vault of the Gothic cathedral at Beauvais collapsed twice before the master masons of the 14th and 16th centuries understood the real potential and limitations of this type of construction. Although Leonardo da Vinci at the end of the 15th century knew exactly how a beam works, the great physicist Galileo, often called the father of modern physics, had a false understanding of beams. He thought, for example, that a cantilevered beam, such as those supporting balconies, has a tendency under the action of the loads on it to rotate around the edge of its lower surface, A in Fig. 1.1. Leonardo da Vinci knew 150 years before him that such a beam, instead, tends to rotate around an axis halfway between its lower and upper surface. 0. Today, the mathematical theory of structures is an essential part of physics and has made possible the record-breaking structures of our era. These triumphs in structural design have been achieved through the use of computers, electronic marvels with the capacity of performing millions of operations per second, while simultaneously making logical decisions. 0. The designs thus made possible were unobtainable only 20 years ago, not for lack of theoretical knowledge, but because they would have required years or even centuries of hand calculations. Yet their infallible computer is run by fallible human beings and cannot be trusted to give right answers all the time. No structural engineer accepts the output of a computer run unless it agrees, more or less, with what experience tells him to be the correct answer. The development of structural material has not kept pace with the needs for the realization of advanced theoretical concepts. Except for reinforced and pre-stressed concrete and high-strength steel, the materials we use today are very similar to those used by our forefathers. Wood, stone, masonry and bricks still dominate construction and must be used in ways compatible with their properties, which have remained practically unchanged for centuries. Thus, while mankind's aspiration to reach the sky, the Tower of Babel complex, drives us to erect higher and higher buildings, our tallest, the Sears Tower in Chicago, is only 3 times taller than the 5,000-year-old Pyramid of Cheops. Our largest hall, the Louisiana Superdome, spans a distance of 680 feet, which is only 4.5 times the 148-foot span of the Dome of the Pantheon built in Rome 1,800 years ago. The superiority of modern materials, however, is of a striking nature, economically if not dimensionally. Our large buildings are extremely light and are cheaper to build than those of the past. The Dome of St. Peter's. The largest church of Christendom, spans 137 feet, consists of not one but 2 dome 5 of brick, and weighs about 450 pounds per square foot. The Dome of the C.N.I.T.000 Exhibition Hall in Paris, a double dome made of. This was only rediscovered at the beginning of the 19th century by the French mathematical physicist Navier. The computer can, for instance, compare the result of a calculation with a given number and, depending on whether the result is smaller than, equal to, or greater than the given number, will continue the calculation, stop, or repeat the calculation, incorporating in it the obtained result. Centre National des Industries et des Techniques. Concrete and 5 times larger than St. Peter's, weighs only 90 pounds per square foot. One might suppose, then, that the shape and size of buildings would be determined essentially by the availability of structural materials. Though this is mostly true in modern times, it is fascinating to realize that religious and spiritual tenets have had an enormous influence on traditional construction. For example, the Patagonian Indians, who lived at the tip of South America in one of the worst climates in the world, exposed to a permanent and infernal wind blowing from the South Pole, were capable of building large stone domes for their churches. Constructing a large dome of heavy stone blocks without the help of mechanical devices is no mean structural achievement, and one would think that the Patagonians could have used this knowledge to protect themselves from their hostile environment. But such was their respect for the gods that they would not dream of building their houses in the shape of churches. While their gods rested warmly in the stone-domed churches, the Patagonians lived in the open air and slept behind windbreakers made of vertical stone slabs. Similarly, in Arab countries many traditional houses, which should have been sited according to exposure to the sun, were often oriented by adherence to religious laws such as those establishing that the praying niche or mihrabin, a mosque, must face Mecca. Since in most buildings functional and structural purposes are achieved through different components, the components are usually made of different materials. The so-called curtain walls of our high-rise buildings consist of thin, vertical metal struts or mullions, which encase the large glass panels constituting most of the wall surface. The curtain wall, built for lighting and temperature conditioning purposes, does not have the strength to stand by itself and is supported by a frame of steel or concrete, which constitutes the structure of the building. On the other hand, both in traditional architecture and in modern designs, particularly of exceptionally large halls, the structure may become so all-important as to take over the functional demands of the building as well. Such is the case in large spaces covered by concrete domes. In traditional brick construction, the walls have window openings and doors and act as both structural and functional components. Typical of the integration of structure and function is the traditional housing in certain towns of southern Italy, where the trulli are round, domed, and stone-built structures which do not have separate functional components. Fig. 1.2. Modern construction has obtained its greatest triumphs where load carrying is not hampered by functional requirements. Bridges, for example, have the sole purpose of connecting two otherwise separated points in order to permit traffic between them. During the Roman Empire, all roads led to Rome because the Romans linked the farthest provinces to the capital through 50,000 miles of them. Travel from London and Baghdad to the Eternal City proceeded by crossing innumerable rivers on a type of bridge the Romans made popular, although they did not invent it, the brick or stone arch bridge, capable of spanning up to 100 feet. The manufacture of steel cables, with the highest strength ever achieved by a structural material, has allowed the modern engineer to design suspension bridges which span almost 6,000 feet. We are doing 60 times better than the Romans in bridge design, while we are limited to relatively minor dimensional improvements in other types of construction. Is there hope to go much beyond these recent achievements? If we take into consideration economic factors and limit ourselves to steel, the only way to go beyond our present bounds is to improve the strength of steel. This is feasible, but only within the limits of steel molecular attraction. In building, as in all of life, human endeavors are thwarted by the laws of nature. Architects and engineers. Even though the functional and structural components of architecture are most often distinct, structure has always had a decisive influence on architecture. In the first place, it is unavoidable. Secondly, structure must obey the laws of nature and cannot always accommodate the desire of the architect. Thirdly, structure, while necessary, is often hidden and does not appear to contribute to the architecture it supports. It is to the architect what the lawyer is to the accused, a necessary evil. Finally, structure is costly. Not really, in comparison with the cost of the rest of the building, but costly all the same. In most buildings the cost of the structure is 1/4 to 1/5 of the total cost, but in some, as in a bridge or a very large hall, it is the main cost component. Structure is often a cause of friction in the relationship between the architect and his structural engineer. A good architect today must be a generalist, well versed in space distribution, construction techniques, and electrical and mechanical systems, but also knowledgeable in financing, real estate, human behavior, and social conduct. In addition, he is an artist, entitled to the expression of his aesthetic tenets. He must know about so many specialties that he is sometimes said to know nothing about everything. The engineer, on the other hand, is by training and mental makeup a pragmatist. He is an expert in certain specific aspects of engineering and in those aspects only. There are today not only structural engineers, but structural engineers who specialize only in concrete design or only in the design of concrete domes or even in the design of concrete domes of one particular shape. No wonder the engineer is said to be a man who knows everything about nothing. The personalities of these two are bound to clash. Lucky is the client whose architect understands structure and whose structural engineer appreciates the aesthetics of architecture. In the last resort, the architect is the leader of the construction team and to him accrue the responsibility and the glory of the project. The engineers are his servants. One of the main reasons for their employment is that, as the saying goes, an engineer is a fool who can do for $1 what any other fool can do for $2. Structure and the layman. Where does the layman stand in the middle of this professional controversy? He is the man for whom the building is being built or one of the thousands of people who will use the building. He should be the most important, even if a seldom heard member of the team. Luckily, the interest of people in architecture has increased dramatically during the last few decades. We have learned from the psychologists that our environment influences greatly the efficiency of our work and the enjoyment of our lives. The sociologist has taught us that the design of our buildings induces or prevents crime. The environmentalist has proved that construction creates pollution. The economist has emphasized how the energy needed to condition a building depends substantially on its design. The architectural historian has told us that the image of our city is the image of our culture. The layman is not only conscious of the external appearance and of the aesthetic impact of buildings but realizes the difference between a well-designed and a poorly designed apartment. He is concerned with minimizing pollution and saving energy. Today all the essential aspects of architecture involve the layman and he participates, with increasing interest, in the development of our cities, buildings, parks, and monuments. On the other hand, most laymen seldom look at architectural structures, or ask the simple question, what makes buildings stand up? This apparent lack of interest in structures is due to a misapprehension, that an understanding of structure requires a scientific mind and the acquisition of technical knowledge usually outside the province of ordinary citizens. This fear is unjustified. Structures, even large and daring structures, were built in the past by craftsmen who had no theoretical knowledge and moved on a purely physical intuition of structural principles. We all possess these intuitions through our daily experience. We understand why columns at the bottom of a building must be larger than those at its top, since they must support the accumulated weights of all the floors of the building. We understand how an arch works as Leonardo described it. An arch consists of two weaknesses which leaning one against the other make a strength. Without any theoretical knowledge, we are ready to say that a cantilever beam, like that supporting a balcony, is right if shaped with a decreasing depth towards its tip and wrong if its supported end is less deep than its tip, Fig. 1.3. We may even have aesthetic feelings about this matter and say that the beam is in the first case lovely and ugly in the second. Moreover, we know that the physical laws of structure have not changed over the centuries and that the 5,840 feet long Akashikaikyo suspension bridge, being built in Japan, works exactly as the vegetable fiber footbridges built in Central America 1,000 years ago. Another subtle reason attracts us to the world of structures. A structure is an artifact expressing one of the many aspects of human creativity, but it is an artifact that cannot be created without a deep respect for the laws of nature. A beautiful structure is the concrete revelation of nature's laws. When the famous Italian engineer Pierluigi Nervi, one of the pioneers of modern concrete and the last of the great master builders, saw the George Washington Bridge in New York, his first words were, "To think that before it was built man had never seen such lovely curves." This, of course, does not imply that a correct structure is necessarily beautiful, but that structural beauty cannot exist without structural correctness. Architecture, besides fulfilling a function, sends a message to the onlooker through its varied and significant forms. No passerby confuses a church with a jail. It is perhaps not so obvious that structure too has a message of its own. It can be a message of strength or elegance, of waste or economy, of ugliness or beauty. But without it, architecture cannot exist. Thus, in addition to speaking to us about usefulness, economics, energy, and safety, structure asks us to appreciate creativity and beauty. It is no wonder that some of the greatest minds of the past have given themselves to the study and the creation of structure, and that all of us, more or less consciously, are interested in discovering the mysteries of its laws. To the pyramids. What are they? They seem to have always been there, on the west bank over the Nile, these man-made mountains. But what are they? Tombs, certainly. Perhaps also cenotaphs, that is, monuments to the pharaohs which were not supposed to contain their bodies. Or astronomical instruments establishing the true north. Or gigantic public works destined to give employment to hundreds of thousands of peasants during the autumn floods of the Nile, when the strip of land along thousands of miles of its course is fertilized, but cannot be cultivated. Or temples to the sun god, worshipped by the powerful elite of the Heliopolis priesthood, which had defeated the priesthood at Memphis and ruled the country through the figurehead of the pharaoh. Most probably they were or became all this and more, since they were constructed over a period of 2,500 years, but mainly in a mere 500 years during the Old Kingdom from 2686 BC to 2181 BC. 3 pyramids reign supreme over the 80 known to exist today. The Pyramid of Cheops, as Herodotus called him, or Khufu, to call him by his Egyptian name, the Pyramid of Chephren, Khafra, only 22 feet shorter than Cheops's, but 15% smaller in bulk, and that of Mycerinus, Menkaure, only a tenth as large as the other two. These grand structures constitute the greatest group of monuments built by man and the most celebrated in history. Religious monuments of great awe to the Egyptians, they sit silent in the silence of the African desert. 13 million tons of limestone blocks, mystery of mysteries, sending out a message perpetually changing over the centuries, the oldest monuments in the world and at the same time the largest. fortresses unassailable to the attacks of the Muslims in search of their mythical treasures. Inspiration of glory to the troops of Napoleon, who incited his soldiers by saying, "From their tops 3,000 years of history look at you." Coveted goal of adventurers and archaeologists in search of the entrance to the king's chambers. Bank vaults of incredible loot to the successful thieves of the Middle Kingdom, who from 2133 BC to 1786 BC penetrated the well-hidden chambers and stole thousands upon thousands of golden objects, compelling the Heliopolis priests to plug again and again their entrances against these undaunted, sacrilegious seekers of worldly goods. Source of magic information to this day and of deathly stories concerning whoever dares to invade their mystic kingdom. Cultures are immortalized by monuments, which express their conception of the world, of life and death. It is no exaggeration to say that the Egyptians were obsessed by death. Their theology dealt with hundreds of gods, each one of which supervised this or that life activity, this or that natural phenomenon, but none was as supreme as the god that governed the afterlife. This god did not always remain the same, since his importance depended on the political fortunes of the elite ruling the kingdom. For centuries he was represented by the ben-ben, a conical stone object, and called Re. But under the name of Horus, the falcon, and of Khepri, the scarab, he carried the sun across the sky, Horus flying on his immense wings and Khepri pushing the sun with his front legs, while Re himself sailed through the sky in a boat. The people and the priests of Egypt found no contradiction in this triple conception of the same god. What mattered was that the pharaoh, who united in a single kingdom the Upper and the Lower Nile, upon his death became identified with the sun god and, in order to live happily in the afterlife, had to be supplied, royally supplied, with all the implements of daily life. This prerogative, at first limited to the king, was slowly extended to his immediate family, then to his ministers and priests, and finally to all of his people. Thus, the concern for his happy survival became the democratic concern of every Egyptian. The body of the king was mummified. His internal organs, except for his heart, were enclosed in separate jars, often located in a separate chamber, and his skin and bones were soaked at length in a solution of bicarbonate of soda. Completely wrapped with linen bandages impregnated with a resin or gum, his remains were enclosed in a coffin with the pyramids shape of a human body and set in a sarcophagus of stone. The mummy, together with the implements of daily usage and animal mummies, had to be protected from outside interference. Originally, the sarcophagus was set in an enclosed room, covered by an earth mound, called a mastaba. But through the centuries, the mastaba became a large rectangular mound surmounted by smaller mounds, until the tomb took the appearance of a stepped pyramid, similar to the ziggurats of Babylon and Assyria. As we approach the time of the IV dynasty, the stepped pyramid disappears and the purely geometric pyramid, with a square base and 4 triangular sides, takes its place. It is said that at sunset, the sun rays over the Nile often pierce the clouds of a heavy sky and project a pyramid of light onto the land. The pyramid, according to one interpretation, is the perpetuation in stone of this light shape and symbolizes the aspiration of man to move towards the sun god. Whether the well-preserved body of the king did actually live after death or whether his ka, a word whose nearest approximation is soul, did wander in the afterlife and needed the body's preservation for its existence, has not been ascertained. But whatever the theological or cosmogonical reasons for the elaborate burial of their king, the fact remains that the most massive monuments the world has ever known were erected by a civilization without a metal stronger than copper and with no wheels or tackles, using a considerable part of its total economy and energy in this activity. Setting aside the mystery of human behavior, we cannot avoid being obsessed by a simpler question: how did they do it? The building of the pyramids. In magnitude of construction, no pyramid is more amazing than the Great Pyramid at Giza, erected by and for Cheops, the largest pyramid of them all, Fig. 2.1. A few numbers will make this clear. The Great Pyramid was built around a center mound of local stone and consists of a core of hewn local blocks and an outer facing of Tura limestone, containing an estimated 2,300,000 Blocks of an average weight of 2.5 tons each, a total of 6.5 million tons of stone. Some of these blocks weigh as much as 15 to 20 tons. Its volume could easily contain the Cathedral of Milan, the Church of Santa Maria del Fiore in Florence, and St. Peter's in Rome, the largest church of Christendom, plus Westminster Abbey and St. Paul's Cathedral in London. Napoleon himself, comforted by the opinion of the great mathematician Monge, computed that the 3 pyramids at Giza had sufficient stone to build a wall 10 feet high and 1 foot wide around the entire boundary of France. The Great Pyramid has a square base with sides of 756 feet and covers over 13 acres. Its original height was 481 feet. Hence, it is 2/3 as high as the first American high-rise, the Woolworth Building in New York, but would occupy 10 New York City blocks, rather than 1. Perhaps more amazing than its size is the accuracy with which the pyramid was built. The lengths of the 4 sides of its base differ at most by 8 inches or, to put it differently, their lengths have an error of 1 in 1,134. These sides are oriented to the 4 cardinal points with a maximum error of 5.5 of a degree or of about 1 in 4,000. The 4 right angles of its base are off by not more than 3.5 of a degree, with an error of less than 1 in 1,500. The faces of the Great Pyramid are inclined at an angle of 52 degrees to the horizontal, an angle that is found in all other pyramids except 2, in which the faces are sloped at 43°. A lot has been made of these 2 angles, because they seem to imply that to measure them so accurately, the Egyptians had to know the value of the ratio of the diameter to the circumference of the circle, the famous Greek number 1t, pi, with an accuracy of 1 in 1,000. It is known, instead, that they estimated it to be equal to 3, the same value given in the Bible, with an error of about 5%. 0, that this was not necessarily so how, been suggested by the electronics engineer T.E. Collins, who noticed that if the Egyptians had measured the sides of the pyramid's base by a rolling drum, the pyramid side would be measured by the drum's circumference times the number of its revolutions. The 52-degree slope of its faces would then result from a pyramid height equal to 4 times the drum's diameter times the Greeks' 1t had an error of less than I in 10 million. The pyramid's number of revolutions, Fig. 2.2. Thus the pyramid side would necessarily equal the height times 70/4 without any need to know the exact value of 71 foot. This might sound like pure coincidence, were it not for the fact that the only other slope angle of 43° results from a height of 3 times the number of revolutions times the drum diameter, and a side necessarily equal to the height times, again, 70/4. 0. The Egyptians were not very sophisticated mathematicians, and it is difficult to believe that they might even have conceived of the number 71 foot. Mr. Collins's explanation may destroy one more of the many Egyptian myths, but is quite convincing. The pyramid blocks were of 3 kinds: the interior blocks of local limestone, recognizable by their reddish color, the casing blocks to be used on its surface, which were cut with great accuracy out of the same stone, and the facing blocks of Tura white limestone, quarried up the Nile and carried to the immediate vicinity of the site by boat. These last blocks were smoothed to a fine finish by gangs of skilled masons, who, in terms of trigonometry, in the first case, calling n the number of drum revolutions and d its diameter, Tana equals 4 nd. 1 md equals for 71 foot, from which it equals 51 inch. 85. In the second, Tana equals 3 nd 70 and d equals 31 feet 11 inches, from which it equals 43 inch. 68. Left their names on the blocks: stepped pyramid gang, boat gang, vigorous gang, enduring gang. Their surfaces were so perfectly planed that a postcard cannot be inserted between them. The cutting of stones at the quarries was done either with copper tools, which might have been made harder by an unknown process, or, more probably, by repeated pounding with a ball of diorite, a very hard igneous rock, on the softer limestone, and by inserting wedges of wood in the cuts thus produced. The wood, wetted and swelled, cracked the limestone along vertical and horizontal planes, as shown by the old quarries still in existence, Fig. 2.3. Granite was too hard to be cut by any of these methods. It was heated along straight lines by fires and then suddenly cooled with water so as to produce plain cracks by thermal shrinking. Granite slabs as large as 30 feet by 17 feet were used in the king's chamber of the Pyramid of Cheops, that has a capstone also of granite blocks. Wheels were not used to transport the blocks to the site. The blocks were set on sledges and pulled by men overland. This was no mean feat. While the average block weighed 2.5 tons, the granite slabs in the king's chamber of the Cheops pyramid weigh 50 tons, and some of the blocks in the mortuary temple of Mycerinus at the foot of the ramp leading from the Nile to the pyramid weigh 200 tons. Navigation by boat from Aswan was made dangerous by the Nile's rapids, but the long voyage by water required a minor effort in comparison with the short trip overland. While the materials were quarried and brought to the site was leveled to an unusual degree of accuracy. The greatest difference in level between the four corners at the base of the Great Pyramid amounts to only half an inch, an error of 1 in 18,000. This miraculous accuracy was the pyramids, obtained by leveling roughly the terrain to a level lower than the surrounding area, excavating in it a network of channels and filling the foundations with water. By measuring depth from the horizontal water level and excavating all the channels to the same depth, an accurate bottom level was established for the channels, from which the remaining area of the foundation could be leveled. While the design of some of the early pyramids was altered during construction and some of them were enlarged in successive phases, the largest were built by a fairly uniform procedure, mythically attributed to Imhotep, the great engineer of the pyramids, whose name was immortalized in the hieroglyphics of many a stone wall. Imhotep was a physicist, a mathematician, an engineer and the inventor of building in stone. He eventually became a god and was venerated for over 3,000 years in Egyptian history. The inner core of the pyramid, Fig. 2.4, was surrounded by masonry buttress walls, inclined inward at an angle of 75 degrees with decreasing heights towards the exterior of the pyramid. The decreasing heights of the buttress walls gave the pyramid, during construction, a stepped shape, which is also the final shape in one of the oldest pyramids, the stepped pyramid of Zoser. The outer casing stones were set in layers, not perfectly horizontal, but slightly inclined inward to increase the stability of this outer layer. Finally, the facing stones, with their outer surface cut at a slope of 52 degrees, or 43°, were set, also slightly inclined inward and, in the case of the Great Pyramid, in courses slightly curved downwards, that is, lower at the center of the face than at the edges, again to reduce the danger of sliding of these blocks. It is not known whether a ramp of access for the blocks was built for each face or whether, as the pyramid grew, a single feeding ramp was built around the pyramid in the shape of a square helix. There is no doubt that the blocks were pulled up the ramps by manpower, as shown by the bas-reliefs on the walls of the surrounding temples. The facing blocks were set starting with the granite cap at the top and coming down the sides of the pyramid, while dismantling the ramps of earth and bricks. The sole official purpose of the pyramid was to hide the king's chambers. These were set either in the rock under the pyramid or in the body of the pyramid itself and were reached by narrow passages dug through after the construction of the pyramid. Some of these passages are inclined downward to reach the chambers set below the pyramid, others are inclined upward to reach the chambers in its body. In the Great Pyramid, the passage leading to the king's chamber becomes the Grand Gallery, 153 feet long and 28 feet high, covered by a corbelled roof * of slabs each extending 3 inches inward from the slab below it. The king's chamber is entirely covered with granite slabs and measures 34 feet by 17 feet. It is 19 feet high. Its roof consists of 9 slabs weighing 400 tons, over which are built 5 smaller chambers, the last of which has a roof of inclined slabs. One may question how such a stone roof can support the weight of 400 feet of stone above it, but one must realize that the superimposed enormous weight does not flow vertically down the pyramid. Just as in a river the flow of water is diverted by the piers of a bridge, the chamber cavities in the body of the pyramid divert the flow of compression due to the stone's weight, producing an arch effect that lightens the load to be supported by the chamber's roof. Fig. 2.5. It is still true that the pressure on the pyramid stones increases with its height, the volume and hence the weight of the stones increases as the cube of the height, while the area of the surface on which it is supported. A corbelled roof is a fake arch obtained by cantilevering the stones of each layer inward from those of the layer below it. The cantilevered layers are kept in place by the weight of the layer above them. Corbelled stone arches and domes appear in some of the oldest monuments built thousands of years BC. The pyramids increases only as the square of the height. Thus, the pressure on the stones at the bottom of the Great Pyramid is more than twice the pressure at the bottom of the Pyramid of Mycerinus. In addition to the king's chamber, a pyramid had a number of smaller chambers, some destined to contain the alabaster jars for his entrails, another, possibly, to entomb his queen, and others to store his worldly goods, including food and clothing. A complicated set of passages connects these chambers, while other passages were dug for ventilation purposes. It would also seem that some dead-end passages were introduced to mislead the interlopers, even if they had succeeded in lifting or destroying the heavy portcullis, the vertical stones sliding into vertical grooves used to block the main passage to the king's chamber after the body of the king had been entombed. As many as 3 portcullis, one behind the other, were used to stop the thieves, most of the time in vain. A legend developed that the last workers, in charge of lowering the portcullis, were trapped inside the pyramid and sacrificed to the king, but modern research has determined that escape hatches were always provided and that the priests in charge of this last operation did not die in the process. The erection of a large pyramid was a superb engineering achievement, designed in all its details ahead of time. The granite sarcophagus in the king's chamber of the Great Pyramid, for instance, is so large that it could not have passed through the narrow passages leading to its final location. The sarcophagus was placed inside the pyramid during its construction and the pyramid was actually built around it. What kind of human effort was required to build such colossal works? We owe to the investigations of Dr. Kurt Mendelssohn, a German physicist and passionate pyramidologist, the estimates of the labor that went into the erection of the main pyramids built during 100 years at Meidum, Dasha, and Giza. Between them, these 3 pyramids required 25 million tons of materials, including limestone, mortar, and brick. Mendelssohn divides the workers into 2 groups. The first consisted of unskilled masons who quarried the local stone, built the ramps, and lifted the blocks, and of auxiliary workers who lubricated the sledges with water, fed the gangs, and repaired the transport lines. The other group was made up of skilled masons, employed at the Tura quarries and at the pyramid sites to cut, prepare, and set the casing and finished stones. The first group may have been 70,000 strong and was employed seasonally during the floods of the Nile. The second numbered possibly 10,000, permanently employed. Facilities to house 4,000 of them have been found near the Pyramid of Chephren. Since Mendelssohn has also convincingly demonstrated that many of the pyramids were built simultaneously, the total number of people employed could have been as high as 150,000, an extraordinary number of workers to be fed and kept by the state in relation to the Egyptian population of 5,000 years ago. The only historical information available on the subject comes from Herodotus. Having talked to the priests of Heliopolis in 400 BC, he reports that 100,000 men working in 3-month shifts labored 20 years to build the Great Pyramid. Since, contrary to the opinion of old investigators, Herodotus has been shown to be quite correct in his explanation of the construction procedures used by the pyramid builders, one is inclined to accept the figures of Mendelssohn as accurate, at least in order of magnitude. The consequences of these estimates, together with those of a fundamental discovery of Mendelssohn, are basic in establishing a fascinating social purpose in pyramid construction, which had not been previously considered by archaeologists. The pyramid at Meidum has always presented a number of unanswered questions stemming from its present shape and some essential differences in its construction and passages. In its present state the pyramid is a ruin, surrounded by 250,000 tons of limestone fallen from it on all 4 sides. It was formerly thought that, since the pyramids had been used for centuries as quarries, These outer layers of the Maiden Pyramid had been stolen to build palaces and bridges in Cairo and other large cities of Egypt. The trouble with this explanation is that there are no large cities in the vicinity of Maiden. Furthermore, most of the stolen blocks weigh 2 tons and are still there. What remains of the pyramid is a 3-step structure emerging from a sea of sand and blocks. A careful inspection of this structure reveals 3 significant features of the original pyramid. The casing at its bottom, still intact, indicates that the 52 degrees angle was used in its erection. The foundation under the casings rests on large blocks of solid stone but is set directly on the desert sand. The blocks of the casing are set in horizontal layers and not in layers inclined inward. Fig 2.6. It is not difficult to surmise from these 3 features that the outer layer of the Maiden Pyramid was not dismantled by thieves, but collapsed because of structural defects and lies at present at the foot of the existing structure. If this hypothesis is accepted, it becomes easy to understand why the next pyramid to be built after the collapse of the Maiden Pyramid, the Bent Pyramid of Dashur, Fig 2.7, started at a slope of 52 degrees, about halfway up was continued at an angle of 43°. This unique example of change in angle, at first ascribed to the hurry with which the pyramid had to be finished, is much better understood as an architectural lecture well learned. The builders of the Bent Pyramid, warned by the Maiden collapse, decided to continue construction at a safer, smaller slope. A counterproof of this hypothesis is found in the angle of the next pyramid, the Red Pyramid at Dashur, the only pyramid in existence built entirely at the safer angle of 43°. The engineers of all the later pyramids understood the cause of the Maiden collapse and, having remedied the structural deficiencies that caused it, resumed construction at the classical 52 degrees angle. The social purpose of the pyramids. As Mendelssohn surmised, more than one pyramid must have been built at the same time during the kingdom of the same pharaoh. In fact, one of them, Seneferu, had certainly 2 and very probably 3 pyramids erected in his name. One can only conclude that, since even a pharaoh could only have one body, some of the pyramids were cenotaphs and not tombs. Why would the priesthood that ruled Egypt for thousands of years go to such extremes of extravagance to honor the pharaohs? Why would such an onus of taxation and labor conscription be imposed on the people of Egypt? Why did these large masses of laborious, slaves under the whip of harsh masters, accept these conditions at a time when no physical means of total repression was available to the ruling class? The answers given by Mendelssohn to these questions are both historically significant and technically fascinating. When Menz, the king of southern Upper Egypt, conquered northern Lower Egypt, he assumed the name of King of Upper and Lower Egypt, and the administration of the nomes or provinces of the new United Kingdom became centralized. But it was only after the establishment of the new capital, Memphis, and the acquisition of power by the priesthood at Heliopolis that a state religion developed. No better way of uniting the populations of the 2 separate kingdoms could be found, after the long conflict between them, than to deify the king. This occurred at the beginning of the Pyramid Age. And what better way of assuring economic equality for the peasants of the 42 nomes, each with their different customs and gods, than to establish a draft in the service of the king god? The supporters of today's draft stress the economic, cultural, and political advantages of such an institution, and the Egyptian peasants might have been ready, perhaps even eager, to serve during the Hood period, exchanging their labor for the support from the king's granaries. Thus, an army of 150,000 healthy young men became available for the erection of the pyramids. They could not very well be sent home when a pyramid was completed without disrupting the economic and labor balance of the kingdom. Some pharaohs are known to have reigned for many decades, while others were on the throne for only a few years. It became imperative, then, both to begin the construction of a new pyramid before the death of a king, and to finish the pyramid started by a prematurely dead king while starting the tomb for the new king. In either case, work on the pyramids became a continuous process, which welded the nomes into a modern state. All the features of a centralized, powerful, and skillful administration were developed at this time and have remained the model of the state to this day. If this explanation is valid, pyramid construction became one of the most important activities and justifications of the state. One could go so far as to say that the pyramids ran the pharaohs rather than the pharaohs running the pyramids. The Mendelssohn hypothesis gives also a rational explanation of the contemporaneous building of pyramids and of the fact that a single king could have 1, 2 or even 3 pyramids in his name, only one of which could be his actual tomb. It must be emphasized that the land of Egypt still hides a fund of information about its history and that Egyptologists have barely begun to unravel the complex sequence of events during its 5,000 years. Practically all statements about ancient Egypt are based on interpretations and assumptions which can seldom be verified with absolute certainty. While the Mendelssohn studies seem to be quite factual in terms of the collapse of the Maiden Pyramid and the temporary adoption of the 43-0 slope, his social surmises are less certain, although they may appeal strongly to our modern conception of the state. The death of the pyramids. Pyramid construction lasted for 500 years, starting with the mastabas, reaching a climax in the 4th dynasty, 4,600 years ago, and slowly degenerating into the erection of smaller and smaller monuments of lower quality. Stone blocks, less heavy and haphazardly assembled, became the rule and finally sun-baked bricks were substituted. The guilds of skilled masons vanished and the quarries at Tura were abandoned. The king who succeeded Chephren, Shepseskaf, had the Mastabat Foruyun built for his tomb rather than a pyramid. This indicates a slow transition to new types of worship, requiring a smaller participation of the population in the former basic, ritual activity. The monolithic obelisk became in due time the symbol of the sun god Re, although the first obelisks were built of superimposed stones and had a squatter structure, reminiscent of the pyramids. If the spire of an Egyptian obelisk seems puny compared to the Great Pyramid, let us remember the engineering difficulties of transporting such an obelisk from the back to the front of St. Peter's. In Rome, this process was described in minute detail by Domenico Fontana in 1590. The obelisk, cut from the granite of Upper Egypt in the 10th century BC, weighed 361 tons. Transportation and erection required a complex set of block and tackles and the use of 140 horses and 907 men. Fig. 2.8. The men were given the sacraments, and strict working rules, under penalty of death, were enforced during the operation. Lowering the obelisk took 1 day, but its transportation along the 800 feet of a specially prepared roadway took 6 months. Erection at the new site was achieved in 1 day. The sophisticated engineers of the Italian Renaissance had a hard time dealing with the puny monuments of Egyptian decadence. The fascination of the pyramids is due as much to their mystery as to their size. As the creator of the Eiffel Tower, for 30 years the tallest tower in the world, put it, there is an attraction and charm inherent in the colossal that is not subject to ordinary theories of art. Does anyone pretend that the pyramids have so forcefully gripped the imagination of men through artistic value? What are they but artificial hillocks? And yet what visitor can stand emotionless in their presence? In the ancient past, religious awe and sun worship dominated the feeling of the onlooker. Yesterday we admired the pyramids as extraordinary engineering feats. Tomorrow we may be moved once again by a social achievement akin to the contemporary construction of enormous dams by the Chinese masses. Today, sensitized to the aesthetic values inherent in elementary geometric forms by an entire school of minimalist sculptors, we may look at the Great Pyramid as the greatest of minimal sculptures. The message changes with the evolution of our cultures, but the mysterious fascination of the pyramids remains. 3 loads. The collapse of the Maiden Pyramid demonstrates that the problem of loads, of weight distribution, even in apparently simple geometric structures, is a complex, ever-present concern for builders. If the earth did not pull, the wind did not blow, the earth's surface did not shake or sink, and the air temperature did not change, loads would not exist and structure would be unnecessary. This would be, indeed, the Alice in Wonderland world of architecture where attention could be focused only on the definition and enclosing of interior spaces. But in the real world, the builder must concern himself with structure. Structure supports all the loads that act, unavoidably, on buildings. The engineer's first job is to determine which loads will act on a structure and how strong they might be in extreme cases. This is anything but a simple task. Let us look into the world of loads. Dead loads. A structure consists of heavy elements like columns, beams, floors, arches, or domes which must, first of all, support their own weight, the so-called dead load. And here lies the paradox of structural design. To determine the weight of a structure, once the dimensions of its elements are established and the material chosen, one has only to compute the volume of the elements and multiply it by the weight of a unit volume of the material, its specific weight. Zero table of specific weights are available to the engineer to facilitate this basic but boring task. The trouble is that, for example, in order to make sure that a beam will carry its own weight, and other loads on it, we must first know its dimensions, but these in turn, depend on the beam's weight. Structural design, the determination of the shape and dimensions of structural elements, can only be learned by experience. The dead load is a load permanently there. In some structures built of masonry or concrete, it is often the heaviest load to be supported by the structure. By the way, any other load also permanently there is always included in the dead load the weights of the flooring, ceiling, and insulation materials, for example. Similarly, the weight of the partitions, the walls dividing one room from another, which may be changed or shifted in rearranging the plan of an apartment but will always be there, must also be included in the dead load. Live loads. In addition to its dead load, a structure must support a variety of other weights: people, furniture, equipment, stored goods. These impermanent or live loads may be shifted around and they may change in value. One may be alone in one's room today and have 10 visitors tomorrow. These may gather in one corner or spread themselves throughout the room. The next tenant may have massive furniture and distribute it differently. It is obvious that we can never know exactly what the live load is and how it is going to be distributed. Concern for safety suggests that live loads must be established on the basis of the worst loading conditions one may expect during the entire life of the structure. These are determined by responsible and practiced engineers and contained in building codes, which are published by cities, counties, and states. In the United States, a few codes have gained general acceptance and most local codes are based on their prescriptions. For example, the so-called Uniform Building Code is akin to the engineer's Bible, and no designer ignores the live load values suggested in it. The values of the code loads are conventional. They assume that the worst effect of the varying and shifting live loads may be represented. Degree, for example, a reinforced concrete beam 30 feet long, 1 foot wide, and 3 feet deep has a volume of 30 x 1 x 3 is equal to 90 cubic feet. Since 1 cubic foot of concrete weighs 150 pounds, the dead load of the beam is 150 x 90 equals 1,350 pounds. By a uniform load, that is, a load evenly spread over the surface of the floors. For example, the New York City Code suggests that the live load allowance for a private apartment room should be 40 pounds per each square foot of floor. By the way, engineers abbreviate the words pounds per square foot as PSF. This is a most conservative allowance, but engineers must be conservative when confronted with the uncertainties of live loads. It is better to run scared than to be responsible for a failure which may damage property and even kill people. On the other hand, the chances are absolutely minimal that each square foot of each room at each floor of a building will be loaded at the same time by the full code allowance, and buildings designed for this absurd assumption would become unjustifiably expensive. Hence, the codes allow a live load reduction, which may reach 60% for a high-rise building. Naturally, the value of the live load varies with the type of building, its location, and its importance. The floors of a warehouse must be expected to carry a much greater live load than those of an apartment house. The roof of a building in Colorado must support a much heavier load of snow than one in Alabama. The public areas of a building, its corridors and halls, which at times may be jammed with people, must be designed for larger live loads than a private room. Live load calculations are lengthy and important, although not very demanding on the imagination and intelligence of the engineer. Luckily, computer programs do most of the evaluations now, saving engineering time and increasing both speed of calculation and accuracy of results. The computer, when properly used, is a wonderfully useful slave. Dynamic loads. The dead load is permanent and unchanging, and the live loads have been tacitly assumed to change slowly, if at all. Together, these unchanging or slowly changing loads are called by engineers static loads, loads that stay. But other loads change value rapidly and even abruptly, like the pressure of a wind gust, or the action of an object dropped on the floor. Such loads are called dynamic and may be exceedingly dangerous because they often have a much greater effect than the same loads applied slowly. For example, a hammer laid slowly, gently, onto the head of a nail will make no impact. But dropping the same hammer suddenly on the nail will why buildings stand up. Drive the nail into the wood. Such suddenly applied loads, actually called impact loads, can be shown to be fleetingly equivalent to many times their statically applied weights. The dynamic pressure of a slap, compared to the static pressure of a caress, may never have been measured, but one can certainly feel it. The fleeting effects of a dynamic load depend on how fast the load varies. This raises a question: for example, should the pressure on a building created by a wind gust, first increasing and then decreasing, be considered a static or a dynamic load? The answer is that no varying load is ever static or dynamic in itself. As we shall see, its effects can be static or dynamic depending on the structure to which it is applied. To prove this, let us consider a tall building acted upon by a wind gust. Under the wind pressure the building bends slightly and its top move, Fig. 3.1. Its movement may be small enough not to be seen by the naked eye, or even sensed, but since structural materials are never totally rigid, all buildings do sway in the wind. If one could push the top of a building, say, 1 foot to the right and then let it go, the building would start oscillating, going back and forth. Its top would first go back through its original vertical position, then move 1 foot to the left of it, and continue swinging back and forth until it eventually stops. It is easy to visualize these oscillations by considering the building as an upside-down clock pendulum, which also swings back and forth when displaced from its lowest position. The time it takes a pendulum to complete a full swing, from extreme right to extreme left and back, is called the period of the pendulum. Similarly, the time it takes a building to swing through a complete oscillation, Fig. 3.2, is called its period. For example, the period of the oscillations of the steel towers of the World Trade Center in New York City, which are 1,350 feet high, is 10 seconds, while the period of a 10-story brick building may be as short as half a second. We can now answer the question about the effect of wind pressure on a building. The action of the gust depends not only on how long it takes to reach its maximum value and decrease again, but on the period of the building on which it acts. If the wind load grows to its maximum value and vanishes in a time much shorter than the period of the building, its effects are dynamic. They are static if the load grows and vanishes in a time much longer than the period of the building. For example, a wind gust growing to its strongest pressure and decreasing in 2 seconds is a dynamic load for the World Trade Center towers with a period of 10 seconds, but the same 2-second gust is a static load for the 10-story brick building with a period of only half a second. In a sense, a force the building can slowly absorb is static, an unexpected one is dynamic. The weight of snow and people is always a static load. Because snow takes hours to accumulate and people enter buildings singly or in small groups. On the other hand, the explosion of an atomic device reaches its maximum effect and decreases so rapidly, less than 1,000th of a second, that it is a dynamic load on all structures, and has enormously destructive effects. Interestingly enough, there are loads which, though not growing rapidly, do have dynamic effects increasing, not instantaneously, but progressively in time. This phenomenon, called resonance, is one of the most dangerous a structure may be subjected to. To understand resonance, let us consider how a heavy church bell, which swings like a pendulum, is made to ring by the relatively small yanks of a single man on its rope. If the bell weighs a few tons, often the case the ringer might try in vain to move it with a single yank. But if the ringer starts yanking the rope with a small pull of, say, a few pounds, and before yanking it again, waits for the bell to go through its first tiny swing, then keeps yanking in rhythm with the bell's oscillations, eventually the bell swings widely and rings. The trick here consists in yanking the rope at the beginning of each new WHY building's stand UP oscillation, that is, at time intervals equal to the period of the bell, so the applied pulls will add up. When a force is rhythmically applied to a structure with the same period as that of the structure, the force is said to be in resonance with it. Resonant forces do not produce large effects immediately, as impact forces do, but their effects increase steadily with time and may become catastrophic if they last long enough. If a long series of wind gusts, growing and waning in pressure with a relatively slow period of 10 seconds, were to hit the World Trade Center towers, the swing of the towers would slowly increase until the structure of the building might sway so widely as to collapse. The story is often told of a German army infantry company goose-stepping across a small wooden bridge in rhythm with the period of the up and down oscillations of the bridge. The company ended up in the river when the bridge collapsed under the resonant load of the goose-step. There are, finally, some perfectly steady forces which produce dynamic effects on certain types of structures. They derive from the interaction between the wind and the structure and are called aerodynamic. In 1940, the Tacoma Narrows Bridge in Washington, a particularly narrow and flexible suspension bridge, 2,800 feet long, was destroyed by a steady wind blowing at 4 to 2 miles per hour for about 70 minutes. Up and down oscillations of the bridge, traveling like a wave along the length of its roadway, had been noticed since its construction. Indeed, the bridge had been nicknamed Galloping Gertie. These oscillations were caused by winds blowing at right angles to the bridge which, as the flexible roadway moved up and down, hit the bridge alternatively from below and from above, naturally in resonance with the period of the bridge oscillations. Their effects, while similar to those of a resonant load, had never been sufficiently strong to wreck the bridge. The collapse occurred when similar, but twisting, oscillations were added to the roadway by the wind blowing not horizontally, but at a slight downward angle. The downward wind pressure first pushed down slightly the windward edge of the roadway, twisting it, then the structure, reacting, twisted the roadway back up, thus allowing the wind to push the windward edge up from below. This cycle was repeated, again and again, gradually increasing the twisting oscillations of the roadway until the wind destroyed the bridge. Luckily nobody was killed, since authorities had cleared the bridge. The roadways of all modern suspension bridges are now stiffened against twisting to prevent this dangerous phenomenon. It is interesting to notice that, although the recent technical literature had never considered the aerodynamic effects of winds on suspension bridges, English newspapers at the beginning of the 19th century carried descriptions of the collapse of flexible suspension bridges caused by the identical aerodynamic phenomenon that destroyed the Tacoma Narrows Bridge. In the history of science and engineering, facts and laws have been forgotten which, if remembered, would have saved time, energy and, possibly, lives. Wind loads. The forces exerted by winds on buildings have dramatically increased in importance with the increase in building heights. Static wind effects rise as the square of a structure's height, and the high-rise buildings of the 1970s, which are at times almost 1,500 feet tall, must be 50 times stronger against wind than the typical 200-foot buildings of the 1940s. Moreover, the speed of wind grows with height, and wind pressures increase as the square of the wind speed. Thus, the wind effects on a building are compounded as its height increases. Wind pressures act horizontally and, in tall buildings, require a structure separate and different from that which resists the vertical gravity loads the weights. In very tall buildings up to 10% of the structural weight, and hence of the structural cost, goes into this wind bracing. In a 20 or 30-story building, on the other hand, the gravity structure is often sufficient to resist the wind. The chances are slim that the strongest possible wind will occur when the structure is also loaded by the heaviest possible gravity loads. Thus, the codes allow structural materials to be stressed 33% more when the loads due to gravity and those due to wind are taken into account simultaneously. This judicious allowance, based on probability, allows considerable structural savings without impairing structural safety. One of the basic questions to be resolved before designing a building is often, what is the strongest wind to be expected at its site? To answer it, wind measurements are conducted daily in all parts of the world and maps are plotted, like that in Figure 3.3, which give at a glance the maximum wind speeds to be expected. But should one design for the strongest wind ever at the site of a building? If this maximum wind were always taken into account, the cost of the wind structure would become unjustifiably high. It is wiser to design buildings so that they will be undamaged by a wind with a chance of occurring once in, say, 50 years, but to allow minor damage under the forces of a 100-year wind, as a wind is called that has a chance of occurring once in 100 years. The cost of fixing the minor damage would certainly be less than the long-term cost required to guarantee total integrity under the stronger wind. It is thus up to the engineer to choose the design wind, and a 30 or a 50-year wind is often considered acceptable unless the strength of a 100-year wind is such as to endanger the entire building and the life of its occupants. Besides depending on wind speed and building height, wind forces vary with the shape of the building. The wind exerts a pressure on the windward face of a rectangular building because the movement of the air particles is stopped by this face. The air particles, forced from their original direction, go around the building in order to continue their flow, and get together again behind the building as shown in Figure 3.4. In so doing, the air particles suck on the leeward face of the building and a negative pressure or suction is exerted on it. The total wind force is the sum of the windward pressure and the leeward suction, but each of these two forces has its own local effects. During Hurricane Donna in New York City, in 1960, occupants of high-rise buildings were justifiably frightened when large glass panels of the curtain walls were blown into their offices by the wind pressure. They were probably even more frightened and amazed when the leeward wind action sucked the window panels out of their offices. These leeward panels fell to the street, creating an additional hazard to passers-by. In designing for wind, a building cannot be considered independent of its surroundings. The influence of nearby buildings and of the land configuration can be substantial. The buildings around a new hall at MIT in Cambridge, Massachusetts, produced such an increase in wind velocity at ground level that it became, at times, impossible to open the entrance doors. Originally the two curved structures of Toronto's City Assembly Hall had only a narrow space separating them. This defile compelled the wind to increase its speed in order to pass through it. Air is a fluid and increases its speed when constrained to go through a narrow space, just as water increases its speed when passing through a narrow gorge of a river. This increase in speed created such high pressures on the two buildings that their wind bracing had to be redesigned on the basis of information gathered in wind tunnel tests. The swaying of the top of a building due to wind may not be seen by the passerby, but it may feel substantial to those who occupy the top stories of a high building. Under a strong wind, the tops of the World Trade Center towers swing left and right of their vertical position by as much as 3 feet, and a hurricane can produce swings of 6 to 7 feet on each side of the vertical. These horizontal swings are not structurally dangerous, but they may be inconvenient for those who work at such great heights. Occupants sometimes become airsick. Recent research by engineers and doctors indicates that the airsickness induced by wind motion in high buildings is a resonance phenomenon. It occurs when the period of the building more or less coincides with the period of the and down oscillations of our own insides. This explains why some, but not all, of the people in a building may feel queasy. To avoid excessive wind deflections, or wind drift as it is technically called, buildings should be stiffened so that their tops will never swing more than 1/500 of their height. Thus a 3-foot wind drift is acceptable in a 1,500-foot building. Lateral movement due to wind may be even more dramatic in long and flexible suspension bridges. After the collapse of the Tacoma Narrows Bridge, the actual lateral swings of all large suspension bridges in the United States were measured. It was found, for example, that the Golden Gate Bridge in San Francisco sways laterally as much as 13 feet under heavy winds. Sometimes the bridge must be closed to traffic since it is not safe to drive a speedy car on a roadway that moves right and left under it. How does one prevent the resonant oscillations in a building? The basic method consists in changing its period by reinforcing its structure to make it stiffer. The stiffer the structure, the shorter the period. This is 0 tall chimneys and high television towers, which have reached over 2,000 feet and are among the highest structures ever built, are subjected to a dangerous resonance phenomenon, in which they oscillate at right angles to the wind. As the wind hits these extremely slender structures, it tends to go around them and creates air eddies which separate from the sides of the structure, causing an alternating vacuum, first on one side and then on the other. When the air eddies separate with a rhythm that coincides with the period of the chimney or tower, the structure starts oscillating laterally with increasing swings, which may damage or eventually destroy it. A costly remedy but recently a mechanical gadget used for years in cars and planes has been adapted to the reduction of wind oscillations. It is called a tuned dynamic damper and consists of a heavy mass of concrete attached to the top of the building by means of lateral springs, Fig. 3.5. This heavily springed mass has the same period as times the building. When the building oscillates with its own period, the tuned damper after a short while also tends to oscillate with the same period, but in the opposite direction. One could say that the damper moves in anti-resonance with the building. When this happens, the oscillations of the building are completely damped out by the counteraction of the damper. The damper's resonant oscillations do not grow because they are controlled by large shock absorbers that break its motion. A spring-connected, 400-ton mass of concrete at the top of the Citicorp building in New York City reduces its top oscillations without a substantial increase in the cost of its wind bracing. Similar dynamic dampers, consisting of heavy metal rings connected to the top of chimneys by radial springs, are used to avoid the lateral swings of these high structures due to air eddies. We have acquired a great amount of knowledge about wind in the last 20 or 30 years, and it is comforting to know that very few modern well-designed structures suffer today from wind damage. Earthquake loads. Earthquakes have wreaked destruction since oldest antiquity, and it is only in the last 30 or 40 years that our knowledge of earthquakes and of their impact on buildings has resulted in the design of earthquake-resistant structures. These are built with particularly strong wind-bracing type structures, which tests and computer calculations prove capable of resisting the jerking forces of an earthquake. Even so, the number of quake victims is still high all over the world. When 27,000 people died in the Guatemala earthquake of 1967, we thought we had seen the worst, but 242,000 people died in an earthquake later in the same year in the region north of Peking. The Earth's crust floats over a core of molten rock, and some of its parts have a tendency to move with respect to one another. This movement creates stresses in the crust, which may break out along fractures called faults. The break occurs through a sudden sliding motion in the direction of the fault and jerks the buildings in the area. Since the dynamic impact forces due to this jerky motion are mostly horizontal, they can be resisted by the same kind of bracing used against wind. Earthquake strengths are evaluated on scales like the Richter scale, which measures the magnitude of the energy in the earthquake. For example, an earthquake measuring 4 or 5 on the Richter scale does little damage to well-built buildings, while one measuring 8 or above collapses buildings and may cause many deaths. Not all parts of the Earth are subjected to earthquakes, but there are two wide zones on the Earth's surface where the worst earthquakes take place. One follows a line through the Mediterranean, Asia Minor, the Himalayas, and the East Indies, the other the western, northern, and eastern shores of the Pacific. It is comforting to know that we are on the threshold of accurate earthquake forecasting and that some earthquakes have already been fairly well predicted in the United States and abroad. In this we lag behind horses and cows, which give obvious signs of fear at the approach of an earthquake. Our new capabilities are due to the fact that when an explosion is detonated at a point in the Earth's crust, waves move out concentrically through it, as they do when we drop a stone in the calm waters of a lake. It has been proved that the wave speed through the crust increases when the stresses in it increase. Thus, when a geologist notices that the velocity of the waves created by a small explosion increases, he knows that the stresses in the crust are increasing and concludes that an earthquake may be imminent. The first successful prediction in the United States was made by a Columbia University student in the Adirondacks only a few years ago. 0. Thermal and settlement loads. The last category of loads the engineer must worry about consists of those caused by daily or seasonal change in air temperature or by uneven settlement of the soil under a building. These are sometimes called hidden or locked-in loads. Let us assume that a steel bridge 300 feet long was erected in winter at an average temperature of 35 degrees Fahrenheit. On a summer day, when the air temperature reaches 90 degrees Fahrenheit, the bridge lengthens, since all bodies expand. While earthquake prediction will certainly be a great boon to humanity, it will present extremely complex social problems. What will the mayor of Los Angeles do if he is told by scientists that a strong earthquake will hit the city a few days or even hours hence? Is it possible to evacuate at short notice a city of 7 million people in an orderly manner? What if at first the geologists are not accurate and predict an earthquake that does not take place? Will people believe them if they cry wolf once too often? Scientific progress can only be a blessing to humanity if man learns to use its results wisely. Loads. Joe times 300 feet B1. When heated, the increase in length of the bridge can be computed to be only 1.2 inches, Fig. 3.6. It is indeed small, 1/3000th of the bridge length, but, if the bridge is anchored to abutments that do not allow this thermal expansion, the abutments will push on the bridge to reduce its length by 1.2 inches. Unfortunately, steel is so stiff that the compressive load exerted by the abutments uses up half the strength of the steel. There is only one way of avoiding this dangerous overstress: one of the bridge ends must be allowed to move to permit the thermal expansion to occur. While gravity loads must be fought by increasing the strength and stiffness of a structure, thermal loads must be avoided by making the structure less rigid. Similar thermal loads appear at the bottom of large domes, which tend to expand when the temperature of the ambient air increases. Due to thermal expansion, the lower edge of a large dome tends to move outward and, since it is impractical to allow this edge to move in and out depending on temperature changes, one must build around it a strong ring to prevent this motion. Most of the large domes built in the past have shown a tendency to crack at their supported boundary, due to both thermal and gravity loads, and have since been circled with hoops of steel. Hagia Sophia in Constantinople and St. Peter's in Rome have been so reinforced after cracks appeared at their edges. In many modern high-rise buildings, the structural frame is set outside the curtain wall, rather than hidden inside it. An emphasis on the importance of structure and a feeling for its aesthetic value is at the basis of this architectural innovation. Good examples are the 100-story John Hancock Insurance Company steel building in Chicago, see Fig. 7.9, and the Columbia Broadcasting System concrete building in New York, see Fig. 7.12. While there is no denying the aesthetic value of some of these exposed structures, it must be noticed that they create problems for the engineer. The interior of these buildings is air-conditioned and maintained at a constant temperature of 65 degrees to 72 degrees Fahrenheit, while the exposed structure is subjected to air temperature changes. In summer, the exterior columns may reach a temperature of up to 120 degrees Fahrenheit, and become 2 or 3 inches longer than the interior columns, while in winter they may become that much shorter when their temperature goes down to 20 degrees Fahrenheit. These variations in length do not damage the columns, but, as shown in Figure 3.7, they bend the beams connecting the outer to the inner columns, particularly at the higher floors. These would be badly damaged if they were not properly designed, either by reinforcing them or by allowing their ends to rotate, that is, by hinging them to the columns, Fig. 3.8. It is easy to conceive of a mechanical way of avoiding these beam stresses. Have the hot and cold water system circulate inside the outer columns of the building and regulate the water flow so that the temperature of the outer columns be always more or less equal to that of the inner columns. This system has not been applied yet because of its cost, but the United States Steel Building in Pittsburgh does have a cold water circulation system in its outer columns. Its purpose is to prevent any heat generated at a point on the outer structure, say, by a fire, from dangerously heating and possibly melting these columns. Bending of the beams connecting outer to inner columns may also occur if the soil under a building settles unevenly, Fig. 3.9. Such uneven settlements caused the leaning of the Tower of Pisa, which started while the tower was being built. The Pisans thought they had straightened the tower up by building its upper part vertically, but the 191-foot tower is still going over at the rate of about 1 inch every 8 years, and its top is now out of plumb by 16 feet. Various measures are being studied to arrest this dangerous rotation, but the Pisans are resolved to stabilize the tower in a leaning position, since no tourist would travel far to look at a straightened-up tower. It must be emphasized that most damage to buildings is caused by foundation problems. Soil mechanics, the study of soil behavior, has moved to a science from an art only during the last 50 years. The island of Manhattan is blessed by a rocky soil, which permitted in 1913 the WHY buildings stand up. Erection of the first high-rise, the Woolworth Building. Mexico City, on the other hand, is built on a mixture of sand and water. Such soils settle when heavy buildings are erected, squeezing the water out of the sand. The National Theatre in the center of Mexico City, originally built at grade level with a heavy cladding of stone, in a few years sank as much as 10 feet. Downward stairs had to be built to its entrance. People were amazed when later on the theatre began to rise again, requiring the construction of an upward staircase. This strange phenomenon can be explained by the large number of high-rise buildings which had been erected nearby. The water squeezed out from under them by their weight pushed the theatre up. Loads may be a necessary evil to both the architect and the engineer, but their basic importance cannot be minimized. Wise is the engineer who gives them his care and attention before starting the design of a building. For materials, tension and compression. The purpose of structure is to channel the loads on the building to the ground. This action is similar to that of water flowing down a network of pipes. Columns, beams, cables, arches, and other structural elements act as pipes for the flow of the loads. Obviously, this becomes a complex function when the structure is large and the loads numerous. The remarkable, inherent simplicity of nature, Einstein called it elegance, allows the structure to perform its task through 2 elementary actions only, pulling and pushing. Many and varied as the loads may be and geometrically complicated as the structure may be, its elements never develop any other kind of action. They are either pulled by the loads, and then they stretch, or are pushed, and then they shorten. In structural language, the loads are said to stress the structure, which strains under stress. The imagery of this terminology is significantly human. When a structure is overstressed, it breaks down and sometimes buckles. As will be seen later, this is said of thin elements subjected to compressive loads too high for their capacity. Another basic law of nature governs the structure's response to the loads. With a judicious sense of economy, or intelligent laziness, a structure will always choose to channel its loads to the ground by the easiest of the many paths available. This is the path requiring the minimum amount of work on the part of the structural materials and is a consequence of what is termed in physics the law of least work. Structure behaves humanly in this respect too. When a material is pulled, it is said to be in tension. Tension is easy to recognize because it lengthens the material. The cables of an elevator are pulled by the weight of the cabin and the passengers. The cables are longer when they lift or lower the cabin than when they were originally installed. We can detect tension easily in elements made of very elastic materials, like a rubber band. Pull on a rubber band and it easily becomes twice its original length. When a material is pushed, it is said to be in compression. Compression, in a sense, is the opposite of tension, since it shortens the material. If we push on a rectangular sponge, the sponge becomes shorter. Structural materials are much stiffer than rubber bands or sponges. Their lengthening under tension or shortening under compression may not be seen by the naked eye, but it always occurs, since there are no perfectly rigid structural materials. As a high-rise building is erected, its lower columns are compressed more and more by the weight of its grow times in number of floors, but we cannot see the shortening of its columns because, whether they be made of steel or concrete, this reduction in height may amount to only slightly more than 1 inch in a building 1,000 feet high. The cables of a suspension bridge are set in tension by the weight of the roadway and of the vehicles traveling on it. Their elongation is 1/300 of their length, but cables are pre-stretched, stretched before being loaded, to reduce it. The tiny changes in length due to tension and compression when divided by the original length of the element are called strains. If an elevator cable originally 300 feet long, 600 inches, becomes 4 inches longer under load, its strain is 600. Or 900. The pull or push on an element, divided by the area it is applied to, is called stress. If a column 10 inches square carries a load of 120,000 pounds, its stress is 120,000 plus 10 x 10 equals 120,000 plus 100 is equal to 1,200 pounds per square inch, abbreviated 1,200 psi. Since all structural actions consist of tension and or compression, all structural materials must be strong in one or both. Strength has quite different values in wood, reinforced concrete, and steel, but all three materials have the capacity to resist tension and compression, that is, to be pulled or pushed by larger or smaller forces before they break under load. Elasticity and plasticity. Strength is not the only property required of all structural materials. Whether the loads act on a structure permanently, intermittently, or only materials. Briefly, the lengthening and shortening of its elements must not increase indefinitely and must disappear when the action of the loads ends. The first condition guarantees that the material will not stretch or shorten so much that it will eventually break under the working loads. The second ensures that the material and, hence, the structure will return to its original shape when unloaded. Whenever we walk on a wooden footbridge, we notice that its planks move down, even if minimally, under the action of our weight. If this downward displacement were not to disappear when we leave the bridge, the next time we walk on it a second displacement would be added to the first and the floor would sag more and more until it would become unusable. If the lateral displacement of the top of a tall building, its wind drift, were not to disappear when a gust stops pushing on it, each new gust would displace the top more and more until the building would look like a gigantic leaning tower of Pisa. A material whose change in shape vanishes rapidly when the loads on it disappear is said to behave elastically. A rubber band is correctly called an elastic, since it returns to its length when we stop pulling on it. All structural materials must be elastic to a certain extent, although none is perfectly elastic under high loads. Most structural materials not only behave elastically, but within limits show deformations that increase in proportion to the loads. Let us say that if a man stands on the tip of an elastic diving board, the tip moves down by 1 inch, and that, if a second man of equal weight also stands there, the tip deflection becomes 2 inches. In this case, the diving board is not only elastic, since its deflection vanishes when the weight of the divers disappears, but also linearly elastic. This terminology derives from the fact that if we plot the board deflections versus the loads, the graph we obtain is a straight line. The discovery of the linearly elastic behavior of materials, called for short elasticity, was made. Towards the end of the 17th century by an Englishman, Robert Hooke, who was a physicist, a surveyor, and an architect. He printed his discovery as an anagram of the statement of his law in Latin, se anastu, which he later unscrambled to read, ut tensio sic vis, as the elongation, so is the force. His secrecy was motivated by the fear that someone else might patent his discovery in connection with watch springs, which are, of course, typically elastic. Such fears were and are quite common. When the 16th century mathematician Tartaglia discovered the formula for the solution of the cubic equation, he kept it secret until one of his pupils betrayed him and gave the formula to Cardan, who to this day is credited with it. All structural materials behave elastically if the loads are kept within given limited values. When the loads grow above these values, materials develop deformations larger and no longer proportional to the loads. These deformations, which do not disappear upon unloading, are called permanent or residual deformations. When this happens, the material is said to behave plastically. If the loads keep increasing after the appearance of plastic behavior, materials soon fail. It has been pointed out that plastic behavior, and hence permanent deformations, is to be avoided in order not to impair the function of a structure. But it must not be thought that plasticity is entirely detrimental in structural materials. On the contrary, it can be quite useful. For example, if we progressively load a structure and measure its increasing deformations, we are warned that the structure is in danger of collapse as soon as we notice that these deformations grow faster than the loads. In other words, materials that behave elastically under relatively small loads and plastically under higher loads do not reach their breaking point suddenly. Once they stop behaving elastically, they keep stretching, or shortening, under increasing loads until they continue to do so even without an increase in the loads. Only. The word plastic has two different meanings in structures and in chemistry. In structures it indicates the inelastic behavior just described. In chemistry it describes a large variety of man-made organic materials like celluloid or bakelite, some of which, notwithstanding their name, behave elastically. Then they fail. If a steel wire is weighted heavily enough, it will keep stretching or yielding under a constant load. It thus gives warning of its impending failure. Materials which do not yield are called brittle and cannot be used in structures, because they behave elastically up to their breaking point and fail suddenly without any warning. This is one reason why glass cannot be used structurally although it is stronger than steel in tension or compression. Thus, strength, elasticity, and plasticity are all necessary to good structural behavior. The value of the loads under which a structure will start behaving plastically depends on a number of conditions, most importantly, temperature. Steel, the strongest structural material available to man, becomes plastic at high temperatures and loses its strength at 1,200 degrees Fahrenheit. Steel buildings must be fireproof to retard the heating of its columns and beams in a fire. Concrete, instead, is a particularly good insulating material and prevents for a long time the heating and yielding of its reinforcing steel bars. Reinforced concrete buildings do not have to be fireproofed. On the other hand, at a temperature of -30 degrees Fahrenheit, called its transition materials temperature, steel becomes brittle and breaks suddenly, particularly under impact, or suddenly increased loads. A steel railroad bridge in northern Canada had its girders break as if made of glass when a train driven by a steam locomotive ventured onto it in the middle of a particularly cold night. A concrete ring would not have behaved the same way. Safety factors. The strength of a structural material is measured by the number of pounds each square inch of material will carry before it breaks. This number, similar to those measuring stress, is called its ultimate strength and varies from material to material and even in the same material depending on how it is stressed. Steel, aluminum and other metals have the same strength whether pulled or pushed. A compressed steel column or a tensioned steel wire can support anywhere from 36,000 to 60,000 pounds per square inch before failing. Aluminum columns and wires behave identically, but deform 3 times as much as steel. This high deformability of aluminum together with its high cost per pound, large amounts of electricity are needed to manufacture it, makes structural aluminum alloys less popular than steel, although its ore, bauxite, is common everywhere. Steel also has the valuable property of changing from elastic to plastic behavior at a well-defined value of the stress, called its yield stress. Since plastic permanent deflections must be avoided, we can load steel up to only a fraction of its yield stress, usually 60% of it. This reduction ensures safety, and forces, as we have seen, the conservative estimates of the code loads. Due to all these causes, factors of safety, which must honestly be considered factors of ignorance, as high as 5 are used in designing structures. This means that such structures could be overloaded 5 times before collapsing. 0. A column of marble, concrete, or limestone could be as high as 12,000 feet before collapsing in compression under its own weight. Stronger. Whenever a material has a clearly defined stress at which it starts yielding, the factor of safety is established to allow a stress which is a fraction of its yield stress. For example, we have seen that in steel this fraction is 60/100. Hence, the safety factor is only 100 divided by 60 is equal to 1.6. When a material, like concrete, yields under low stress, but does not break soon thereafter, the allowable stress is established as a fraction of its ultimate strength at which it fails. For example, concrete with an ultimate strength in compression of 5,000 pounds per square inch may have an allowable stress of only 2,000 psi, i.e., a safety factor of 2.5. Stone, like granite, could reach 18,000 feet. But the tallest stone buildings ever erected, the limestone pyramids of Egypt, are less than 500 feet tall and, hence, have a factor of safety of at least 24. The Egyptians were very prudent. Unfortunately, stone and concrete resist pulling badly. They can only be used in elements that are never pulled, such as columns or arches, but are not well suited for beams, which, as we shall see, develop both tension and compression. Wood strength not only differs in tension and compression, but depends on whether we stress it in the direction of its grain or at right angles to it. To overcome this peculiarity, sheets of wood with fibers oriented in different directions are assembled with plastic glues, plywood and laminated woods. These have approximately the same strength properties in all directions. Wood is one of the few natural materials with a high tensile resistance and has been used throughout history in beams and other elements developing tension. Unfortunately, it burns at low temperatures and must be fire retarded, even though fire retardation decreases its strength. Steel. Man-made materials have permitted the realization of the record-breaking structures of modern times. The tallest building in the world today, the Sears Tower in Chicago, is supported by steel columns and beams, and the longest suspension bridge, the Humber Bridge in Great Britain, is held up by steel cables. Pound per pound, steel is the material with the greatest strength obtainable at the lowest price. Steel is an alloy of iron and carbon, with very tiny amounts of other metals to give it particular properties. For example, nickel is added to make stainless steel, which does not rust. The carbon content of steel varies from 0.1% to not more than 1.7%. Iron with less carbon is called wrought iron and is workable at low temperature. The first wrought iron man-made object is a dagger manufactured in Egypt. In 1350 BC, iron with a high carbon content is called cast iron and is an easily melted, but brittle material, which can be cast into complicated shapes. It was produced in China as early as in 600 BC. Iron ore, which is found practically all over the Earth's surface, is melted at high temperatures in furnaces and then alloyed with carbon to make steel. Modern structural steel is produced in 2 kinds of strengths: regular structural steel, that starts yielding under stress if 36,000 pounds per square inch, and high-strength steel that yields at about 50,000 pounds materials per square inch. The first is used in most steel buildings, but the second has recently become almost as inexpensive as the first and is supplanting it, particularly in high-rise buildings. It is conceivable that high-strength steels may soon be developed, which will overcome the problem of the increase of brittleness with increasing strength. For example, one particular type of high-carbon steel, obtained by drawing steel through dies into thinner and thinner wires, is used to build cables and has already achieved ultimate strengths of 300,000 pounds per square inch. It can be used at stresses of up to 150,000 pounds per square inch. This means that we could safely hang the entire Leaning Tower of Pisa from a cable only 1.1 inches in diameter. Tiny pieces of steel, called whiskers, with a strength of 1 million pounds per square inch have also been produced. May we hope to go much beyond these very high strength values. Only so far. The attraction forces within steel crystals have a value of 4 million pounds per square inch. Nature puts a limit to steel strength, although chemists and physicists still have a long way to go before exhausting its capacity. On the other hand, metallurgists have recently given steel new properties of great practical value. Although stainless steel does not rust, its production is too expensive to allow its use in the large amounts needed in construction. All steel structures, therefore, had to be painted at regular intervals, of a few years, to prevent rusting. It is only in the last 10 years that a new type of weathering steel, labeled with proprietary names like COR10 by the US Steel Company or MARI-R by the Bethlehem Steel Company, has solved this problem. Such steels have a rusting process which penetrates to a few hundredths of an inch from the surface and then stops, giving the steel a pleasant maroon color. The economies achieved by the elimination of continued painting have made this steel most popular for exposed structures and for the large pieces of sculpture called environmental sculpture. Some steel properties present obstacles to its use in structures. Its 1,200 degrees Fahrenheit melting point and its -30 degrees Fahrenheit transition temperature to brittleness have already been mentioned. Another appears when steel more than 2 or 3 inches thick is used in the beams of very long bridges or the columns of very high buildings. Unless carefully treated thermally, these thick elements tend to slice into thin layers like a piece of pastry, due to locked-in stresses. Only a few years ago, this dangerous phenomenon, called lamination, was the cause of the collapse of the West Gate Bridge in Australia and of others in other parts of the world. Luckily its causes are now understood and its dangers avoided. The tendency to move forward to greater achievement has often confronted technology with unsuspected dangers and motivated more thorough investigations of materials and structural behavior. The collapses of the West Gate Bridge and of the Tacoma Narrows Bridge have been blessings in disguise for the development of steel bridges. Lamination stresses are not caused by apparent loads. Similar locked-in stresses may be caused in steel structures by the welded connect tie-ins between elements. In welding, the steel of the two parts to be connected is melted at high temperature and a welding metal is deposited at the joint. When a well-executed joint cools, the connection becomes as strong as the steel of the jointed pieces. The high temperatures used in welding, if reached or cooled too rapidly and concentrated in too small an area around the joint, may produce thermal locked-in stresses, which the steel is unable to resist. They are similar to those in a steel hoop, made by bending a straight strip into a circle and welding its two ends. Once the hoop is welded, it looks unloaded, but if one cuts it with a pair of shears, it snaps open, indicating that it had to be forced into its curved shape and, hence, was stressed. In order to avoid the locked-in stresses due to improper welding, welders are carefully trained and certified by law, like doctors. Moreover, welds are often inspected by means of X-ray and other refined techniques to detect faults in their execution. Finally, it must be remembered that steel is fatigued by reversal of stress from tension to compression and vice versa, when this cycle is repeated many times. We use this phenomenon ourselves to break wire by bending it back and forth a number of times. Thus there is more to steel design than loads and strength. The prudent engineer must be alert to a variety of dangers. As Thomas Alva Edison said to a young man he had to fire from his lab, "I don't mind the fact that you don't know much, yet. The trouble is that you don't even suspect." A good engineer should, of course, know, but should also be intelligently suspicious. Reinforced concrete. Possibly the most interesting man-made structural material is reinforced concrete. Combining the compressive strength of concrete and the tensile strength of steel, it can be poured into forms and given any shape suitable to the channeling of loads. It can be sculpted to the wishes of the architect rather than assembled in prefabricated shapes. It is economical, available almost everywhere, fire-resistant, and can be designed to be light materials. Weight to reduce the dead load or to have a whole gamut of strengths to satisfy structural needs. Concrete is a mixture of cement, sand, crushed stone or pebbles, and water. The water and cement paste fills the voids between the grains of sand, and these fill the voids between the stones. After a few days the cement paste starts to harden or set, and at the end of 4 weeks it gives concrete its nominal ultimate strength, which is as good as that of some of the strongest stones. Concrete mixtures are designed by specialized laboratories and mixed in strictly controlled proportions in concrete plants, from which they are carried to the site in the revolving drums of large trucks that keep mixing them en route. Concrete samples in the shape of cylinders or cubes are taken from each truckload and tested for compressive strength after 7 and 28 days. The strength of concrete depends on the ratio of water to cement, and of cement to sand and stone. The finer and harder the aggregates, sand and stone, the stronger the concrete. The greater the amount of water, the weaker the concrete. The following episode illustrates in very human terms the importance of keeping the water to cement ratio low. During the construction of a terminal at JF Kennedy Airport in New York, the supervising engineer noticed that all the concrete reaching the site before noon showed good 7-day strength, but some of the concrete batches arriving shortly after noon did not measure up. Puzzled by this phenomenon, he investigated all its most plausible causes until he decided, in desperation, not only to be at the plant during the mixing, but also to follow the trucks as they went from the plant to the site. By doing so unobtrusively, he was able to catch a truck driver regularly stopping for beer and a sandwich at noon and, before entering the restaurant, hosing extra water into the drums so that the concrete would not start to harden before reaching the site. The prudent engineer must not only be cautious about material properties, but be aware, most of all, of human behavior. Portland cement, as modern cement is called, is a mixture of limestone and clay, burned in a furnace and then pulverized. Impervious to water, it actually becomes stronger if submerged after it hardens. Samples of concrete taken 30 years after a concrete boat sank during World War I showed that the concrete had doubled its compressive strength. The Romans used a cement made only of lime to manufacture a concrete with aggregates of broken bricks and stones. This cement slowly dissolves in water, but it becomes almost as strong as modern concrete when mixed with pozzolana, a volcanic ash found at Pozzuoli near Naples. The Romans did not invent concrete, but a combination of pozzolanic concrete and outer surfaces of excellent stone, or good brick of burnt clay, allowed them to erect the majestic and massive structures which survive to this day. Unfortunately, even the best concrete has a tensile strength barely 1/10 of its compressive strength, a property it has in common with all stones. The invention of reinforced concrete remedied this deficiency and produced a structural material that, pound per pound, is the most economical. In reinforced concrete, bars of steel are embedded in the concrete in those areas where pulls will develop under loads, so that the steel takes the tension and concrete the compression. For example, the bottom of a beam supported at its ends is always in tension, while its top is in compression. See Chapter 7. Steel bars set near the bottom of the beam prevent the concrete from cracking under tension, Fig. 4.1, and make the beam work as if it were made of a material, like steel or wood, capable of resisting both kinds of stress. Reinforced concrete was originally invented in France towards the middle of the 1800s, and its use spread very rapidly all over the world. It is today the most commonly used structural material. Ideal as it is for construction, concrete too has some unfortunate properties. If not properly wetted, or cured, while it hardens, it shrinks and cracks, allowing humidity to rust the reinforcing bars. Moreover, it continues to stretch or shorten, creeps, under constant tension or compression loads, up to 3 or more years after hardening. 0. The fact that the addition of a tensile material improves the performance of a compressive material was well known to the American Indians, and to the Babylonians and the Egyptians before them. Adobe is a paste of wet clay mixed with straw and sun-dried. The dried clay has a substantial compressive resistance and is stitched together by the tensile-resistant straw. Some Berber cities in Morocco are circled by adobe defense walls, built centuries ago and standing to this day. Materials. Pre-stressing is the most recent procedure devised to improve the performance of reinforced concrete. The concrete at the bottom of a reinforced concrete beam tends to develop tiny, capillary, tension cracks due to stretching under the load of the steel bars it grips. If this concrete were compressed before the beam is loaded, the tension caused by the load would be counteracted by this initial compression and the beam would not develop capillary cracks. When the tension induced in the concrete by the loads is less than the initial pre-stressing compression, the concrete of the entire beam is always compressed and, as if it were steel or wood, is capable of resisting both types of stress from the loads. How is the pre-compression of the concrete obtained? In pre-tensioning, the steel bars are substituted by steel cables or tendons, made of exceptionally strong piano string wire, and artam. Buckled into tension against end steel plates, Fig. 4.2. Once the concrete hardens, the tendons are released from the plates and the concrete gets compressed by the tension in the steel tendons. The tendons' tension and the concrete compression balance each other and are locked in stresses, invisible to an external observer. In post-tensioning, the tendons are threaded through plastic tubes set in the concrete, so that the concrete cannot grip them. After the concrete has hardened, the tendons are pulled against it and their tension puts the concrete in compression, Fig. 4.3. The post-tensioning operation can take place at the site after the beam has been erected, when the dead load is already acting on the beam, and can be adjusted as the loads on the beam increase. The principle of pre-stressing is so simple that the reader may wonder why it was not put into practice soon after the invention of concrete. 0. Pre-tensed concrete beams and columns are usually manufactured in special plants. The French concrete engineers of the 1800s thought, indeed, of pre-stressing concrete, but they discovered to their dismay that the creep of the concrete in compression, together with the yield of the steel in tension, caused the loss of most of the pre-stressing action shortly after the beams were pre-stressed. As the compressed concrete crept and became shorter, the tendons slackened and should have been turnbuckled again to regain their tension. This was impossible once the structure was built. Pre-stressed concrete became practical only after high-strength steel became available at low prices. This steel can be pulled to such a high stress that even if some stress is lost through yield due to concrete shortening, it can still sufficiently compress the concrete. Once again, progress was due to an improvement in material properties rather than the inventiveness of the engineer. Today, pre-stressed concrete is widely used all over the world. Because it is more economical than its cousin, reinforced concrete. Unfortunately, the high cost of the specialized labor required by pre-stressing has somewhat hampered its spread in the United States. At the beginning of the 20th century, of chemical methods of polymerization. The discovery, at the beginning of the 20th century, of chemical methods of polymerization, that is, of producing compounds with long chains of molecules, has opened a Pandora's box to new materials. Plastics. The discovery, at the beginning of the 20th century, of chemical methods of polymerization, that is, of producing compounds with long chains of molecules, has opened a Pandora's box to new materials. Under the name of plastics, a great variety of organic materials, obtained by a combination of temperature and pressure, has been manufactured with an infinite variety of properties. Plastics can be made as strong as steel in both tension and compression, can be given an elastic or a plastic behavior, and are practically indestructible. Among the most useful plastics are those reinforced by glass fibers, like fiberglass, which are shatterproof because glass, extremely strong in tension, has its brittleness cushioned by the plastic matrix in which it is embedded. It may seem strange that plastics have not found important structural applications yet. This is due to two causes. In the first place, almost all plastics are more deformable than our present structural materials and, hence, cannot be used in the manufacture of large structural elements. Secondly, they are expensive. The economy of plastics presents a typical chicken and egg question. On one hand, they are expensive because they are used and produced in relatively small quantities, not large enough for the requirements of construction. On the other, they are produced in small quantities because they are expensive. Such a vicious circle is bound to be broken, and it is foreseeable that the role of plastics in structures will increase in importance as plastics better adapted to structural usage become less expensive. For the time being, the most exciting structural application of plastics is that to high-strength fabrics in large inflatable roofs, dealt with in detail in Chapter 15. But years will have to pass before plastics can supplant materials as abundant, inexpensive, and well adapted to structural action as reinforced concrete, steel, masonry, and wood. 5 beams and columns. Newton's laws. During the academic years 1665 and 1666, Isaac Newton, then in his early 20s, was prevented from attending Cambridge University by the spread of the plague throughout England. This was a blessing in disguise for him and a boon for humanity. Cloistered in his mother's home at Woolsthorpe, Newton was able to ponder the deep questions of physics he had set his mind to answer, and to develop the ideas of his gravitational theory. These ideas were so daring for the time as to approach absurdity. He postulated, for example, that bodies could exert forces at a distance without material contact, contrary to all physical evidence. Even so, his law of gravitation predicted exactly why the moon rotated about the Earth in an elliptic trajectory in almost exactly 27 1/3 days and the Earth around the Sun in another elliptic trajectory in 365 days, 5 hours, 48 minutes and 46 seconds. It also explained why the legendary apple fell on his head. Not for 250 years would a genius of Newton's magnitude, Einstein, come up with another even more daring and abstract assumption, denying the existence of action at a distance and improving on the accuracy of Newton's results. Newton, with the modesty of some great geniuses, never asserted to have explained why bodies attract each other. He simply stated that bodies behave as if they attracted each other with a force governed by his gravitational law. But, having at least assumed a cause of motion, he 72. Proceeded to describe how motion takes place. His 3 laws of motion allow the determination of the speed with which all bodies move, from the apple to the sun's planets. His first and third laws, when added to that of elasticity, are sufficient to solve almost all structural problems. His synthesis remains possibly the greatest in the history of science. The first law of motion, as applied to structures, states that a body at rest will not move unless a new, unbalanced force is applied to it. The third states that, when a body is at rest, for each force applied to it there corresponds an equal and opposite balancing reaction, also applied to it. Since we want our structures not to move, except for the minuscule displacements due to their elasticity, Newton's laws of rest are the fundamental laws ruling the balance that must exist between all the forces applied to a structure. In physics, a body at rest is said to be in equilibrium, from the identical Latin word which means equal weights or balance. An understanding of 2 particularly simple aspects of the laws of equilibrium is essential to an insight into how structures work. Translational equilibrium. Consider an elevator hanging from its cables at a given bore. The pull of gravity on its cabin and occupants, that is, their total weight, acts downward. As the elevator does not move, is in equilibrium, a force upward must be exerted on it equal in magnitude to its total weight. This force can only be exerted by the cables. We conclude that the cables pull up on the elevator with such a force. The elevator is thus acted upon by two equal and opposite vertical forces and is in equilibrium in the vertical direction. According to Newton's third law, if we call action the force due to the weight, the pull of the cables constitutes the equal and opposite reaction. Similarly, if we stand on the bore, the pull of the earth, gravity, exerts a force pulling down on our body and, since we do not move down, an equal and opposite force must be exerted on it. This can only come from the bore pushing up on our feet, thus exerting a reaction, up, equal and opposite to the weight, down, of our body. Our body is in vertical equilibrium. Consider now two groups of children pulling on the two ends of a rope. If neither group prevails, the pull of one group must be equal to that of the other, and the rope, under the action of these two equal and opposite forces, is in equilibrium in the horizontal direction. If one group prevails, their force is greater than that of the opposing group and equilibrium is lost, the rope moves, it is not in equilibrium anymore. In the first case, it may be hard to decide which of the two equal and opposite pulls is the action and which is the reaction. It is really a question of semantics and, perhaps, if one's boy or girl belongs to one group, on purely psychological grounds, we might be inclined to call this group's pull the action and the other's the reaction. Identical considerations govern the equilibrium of structures. Since the total weight of one of the World Trade Center towers is approximately 140,000 tons and acts down, we know that the soil must exert on the foundation of the tower a force up of 140,000 tons. The soil under the tower must be quite hard to develop such a reaction. And so it is on Manhattan, an island which consists mostly of very solid rock. Similarly, if a wind exerts a horizontal pressure of, say, 30 pounds on each square foot of one of the tower's faces, which measure about 175,000 square feet, the total wind force on that face equals 30 times 175,000 square feet, or over 5,000 tons, and the soil under the building must also react horizontally, in a direction opposite to that of the wind, with a force of 5,000 tons. If the soil were unable to do so, the tower would slide in the direction of the wind. The two basic actions of tension and compression are usually developed in structural elements in equilibrium by equal and opposite forces acting along the center line or axis of the element. A steel column, with a weight usually negligible in comparison with the load it supports, is set in compression by the action down of the load's weight and the reaction up of its footing. One may say that the weight flows down the column until it is stopped by the footing. Similarly, the weight of the elevator pulls on its cables, and we can visualize this pull traveling up along the cables until it is stopped at the top by the pulleys. One can feel axial tension or compression by pulling or pushing on a door handle. The pull or push exerted by our body and balanced by the doorknob's reaction is felt by the muscles of our arm along which the pull or push travels. From the Latin word translare, meaning to move in the same direction, equilibrium in a given direction is called translational equilibrium. For a body to be at rest, it must move neither vertically nor horizontally. For example, a building will be at rest in total translational equilibrium if it does not move vertically or in either of the two directions parallel to its faces. Total translation equilibrium is thus satisfied by three conditions of translational equilibrium: vertical, parallel to one face, and parallel to the other face. Rotational equilibrium. If an empty cereal box is placed in front of an electric fan, it will move under the action of the airflow. If it rests on one of its long narrow sides, it will probably move horizontally, but if it rests on one of its short, narrow sides, its bottom, it will no doubt topple over before it moves horizontally. The cereal box is a good model for a tall building not well anchored into the ground and acted upon by a strong wind. Although in the second case the box was in vertical and horizontal equilibrium, since it did not slide or move up or down, it was not at rest since it toppled over. This motion occurs when the box turns around its lower edge on the side opposite to the wind or, as we say in physics, rotates around this leeward edge. To maintain the box at rest, this rotational motion must also be prevented. To understand the requirements of rotational equilibrium, consider a seesaw with two children of identical weight sitting on opposite ends, Fig. 5.la. The seesaw does not move vertically because the reaction up of its pivot balances the weights down of the two children. It is equal to twice the weight of one child. The seesaw does not rotate either unless one of the children moves nearer the pivot, in which case the seesaw starts rotating down on the side of the other child and is not in rotational equilibrium anymore. Clearly, rotational equilibrium requires not only that the weights of the two children be equal, but that their distances from the pivot also be equal. Let now a father weighing twice as much as his child sit on the seesaw and try to balance it. Fig. 5.lb. He succeeds if he sits half the distance of the child from the pivot. The two weights on opposite sides of the seesaw's pivot do not have to be equal for rotational equilibrium. What must be equal is the weight times its distance from the pivot. This is nothing else but the well-known law of the lever, which states that rotational equilibrium requires equal products of forces times lever arms, as distances from the pivot are called, tending to make the body rotate in opposite directions. If one now fills the upright cereal box with enough sand or stones and blows on it again with a fan, the box will not topple over, it will be in rotational equilibrium. This occurs whenever the wind force times its vertical lever arm from the leeward edge is less than or at most equal to the weight of the building times its horizontal lever arm from the same edge, Fig. 5.2. It is thus seen that the rotational action of a force can be balanced by that of another force in a different direction. Simple as this may seem, the task of the structure is to guarantee translational and rotational equilibrium of the building under the action of any and all forces and reactions applied to it, including, of course, its own weight. The task of the engineer is to shape and dimension the chosen structural materials so that the structure may produce equilibrium without breaking up, and with acceptably small elastic displacements. Beam action. Equilibrium guarantees the stability of an entire building and, of course, of each one of its parts. In the California earthquake of 1971, a small hospital building toppled over without suffering serious damage. Its strength was sufficient, but not its equilibrium capacity. To prevent the toppling of a very high building, when the building's weight is not sufficient to counteract the wind, its columns are anchored into a founder. For example, in the World Trade Center Tower, the horizontal wind force of 5,000 tons has a vertical lever arm of 700 feet, half the tower height, and a product equal to 5,000 x 700 equals 3,500,000 or 3.5 million ton-feet. The tower weight of about 140,000 tons has a horizontal lever arm equal to 60 feet, half the tower width, and a product equal to 140,000 times 60 is equal to 8,400,000 or 8.4 million ton-feet. The weight wins and the tower does not topple over. Tie on deep in the ground. In this case the building bends slightly under wind pressure, but remains in rotational equilibrium in part due to the counteraction of its weight but also due to the forces exerted by the anchored columns. The windward columns are set in tension and those on the leeward side in compression, Fig. 5.3, thus creating a tendency to turn the building against the wind. The wind drift or lateral displacement of the top of the building is due almost entirely to the lengthening of the windward columns under tension and the shortening of the leeward columns under compression. Since the floors are rigidly connected to the columns, they tilt slightly and remain at right angles to them. All these deformations are so minute that they cannot be detected by the naked eye, but give to the building a slightly deflected curved shape. The shortening of a column under the action of an allowable compressive axial force or the lengthening of a cable under an allowable tensile force is extremely small. In the building under lateral wind load, we find, however, that the lateral deflections may be substantial. The columns of a 1, 0, 0, 0 Foot skyscraper shorten under the vertical loads by only 1/10 of an inch, but the top of the skyscraper may bend out several feet under the action of lateral loads. The deflections due to loads perpendicular to / the structure are much larger than those due to axial, longitudinal loads. They are called bending deflections and are typical of basic structural elements, called beams, which are usually loaded at right angles to their longitudinal axis. A skyscraper under wind acts like a gigantic vertical beam stuck into the ground, much as a diving board acts in supporting the load of a diver. Fig. 5.4. Let us look in greater detail into the deformation of these cantilevered beams. Consider a beam stuck into a wall and carrying a load at its tip, for example, a wooden jumping board with a man on the end. Under the man's weight, the beam deflects and its tip displaces downward. The beam bends, because the fibers of its upper part become longer and those of its lower part shorter. If one draws vertical lines on one side of the beam, these remain straight and perpendicular to the beam's upper and lower surfaces. Fig. 5.5. The lengthening and shortening of the upper and lower wood fibers are shown by the crowding of the vertical lines at the bottom and the opening up of the lines at the top. The most remarkable feature of this deformation is that the fibers midway between the top and bottom maintain their original length. They are neither stretched nor shortened. Hence, they are neither under tension nor compression, they are unstressed. Moreover, we may also notice that the lengthening and shortening of the fibers in the upper and lower halves of the beam increases from being non-existent at the middle fiber to the greatest values at the top and bottom of the beam, respectively. Since the board's behavior is linearly elastic, the tension and compression in the beam fibers grow linearly from zero at the middle to maximum values at the top and bottom fibers. This explains why the short lateral lines remain straight, as Leonardo first and then Navier knew, see Chapter 1. In the compression of a column or the tension of a cable, the loads are evenly divided between all the fibers of these elements. In a beam, instead, the extreme lower and upper fibers are highly stressed, while all the other fibers are stressed less and less as we approach the middle fibers. These middle fibers do not do any work while the others do more and more work the nearer they are to the top and bottom of the beam. Thus, most of the beam material is not utilized to its maximum capacity. A beam, whatever its material, is not a very efficient structural element as, on the average, its fibers work at half its allowable capacity. In a beam supported at its ends on columns, the crowding towards the top of the vertical lines on its side and their opening up towards the bottom, Fig. 5.6, indicate, again, that the lower fibers are in tension and why buildings stand up. The upper in compression. This is why cracks appear at the bottom of beams made out of materials with a low tensile capacity, like stone or concrete, and why steel reinforcing bars are set at the bottom of concrete beams supported at their ends. In channeling loads to the ground, our most important and difficult task is to span horizontal distances so that loads may be carried across them. The structure of a bridge has no other purpose. Similarly, the floors of a building allow people to walk over the heads of people on lower bores. It is easy enough to support a load with a column right under it. It is much more difficult to carry the weight of a truck to the bridge supports so that the river may bow unimpeded below it. In buildings, distances of up to 100 feet are spanned by numerous horizontal beams. It is unfortunate that beams should be rather inefficient. Is there anything one can do to improve the efficiency of beams? Realizing that all the material in the neighborhood of the middle fiber, which is called the neutral axis, is understressed, the thought occurs to move this material away from the neutral axis toward the top and bottom of the beam. If this is done as shown in Figure 5.7, the shape of the beam's transverse cut, or cross-section, becomes similar to that of a capital I. Of course, one cannot displace all the material near the middle fiber up to the top and down to the bottom of the beam. Some material must always connect the top and bottom parts of the I-beam, called its flanges, or they would become two separate, thin and flexible beams. This narrow vertical strip is called the beam's web and is typical of the steel beams used in the construction of high-rise steel buildings. Beams of steel with wide flanges, called wide flange sections, are obtained by rolling heated and softened pieces of steel between the jaws of powerful presses and have flanges much wider than the top and bottom segments of a capital I. This is the most efficient shape a beam can be given to carry vertical loads horizontally from one point to another. One may think of a beam as a structural element that transfers vertical loads to the end supports along its horizontal fibers, as if the beam deflected the vertical flow of the loads by 90 degrees only to turn them around again in a vertical direction at the beam supports. Fig. 5.8. Beams are made out of steel, aluminum, reinforced concrete, and wood. Their downward bending displacements under load, larger than those of columns, must be limited lest they dip impossibly or the plaster begin to flake off the ceiling. Codes limit the bending deflection of a beam to less than the beam length divided by 360. The stiffness of a beam shape is increased by shifting part of the material away from its middle fibers and is measured by a quantity called the moment of inertia of the beam's cross-section, given in all beam manuals. Thus, deep beams are stiffer than shallow beams. On the other hand, the beam stiffness diminishes dramatically with increases in length. Doubling the length of a beam makes it 16 times more flexible. If tension is characterized by lengthening and compression by shortening, beam action or bending is characterized by the curving of the beam. Whenever a straight element becomes curved under load, it develops beam action, and the more curved it becomes, the larger its bending stresses. When a beam's ends curve up, as in a beam supported at its ends, its lower fibers are in tension and its upper fibers in compression. Whenever a beam curves down, like a cantilever supporting a balcony, the upper fibers are in tension and the lower in compression. Hence, in a balcony beam of reinforced concrete, the reinforcing bars must be located towards the tense top of the beam. In general, then, the tension appears on the opposite side of the curvature. See Figs. 5.5 and 5.6. It has been tacitly assumed so far that a beam supported at the ends on two walls or two columns is not rigidly connected to the supports so that its ends rotate due to the bending deflections. See Fig. 5.6. Most of the time, instead, the beam is fixed into the supporting walls or rigidly connected to the top of the columns. In a reinforced concrete beam, the simultaneous pouring of the concrete makes the comings monolithic with the beams, while in a steel structure beams are rigidly bolted to the columns. Such beams have ends which cannot rotate, or rotate only slightly. They are called fixed-end or built-in beams. Fixed-end beams are particularly stiff and strong. They carry 1.5 times the load of a supported beam of the same length, and they deflect 5 times less. Fixed-end beams deflect under load as shown in Figure 5.9. The figure shows that rigid connection to the supports makes the beam ends curve down, but that its middle curves up. This is why in the neighborhood of the supports of a fixed-end concrete beam the reinforcement is set near its top and in its middle portion near its bottom. There are 2 points in the beam at which the curvature changes from down to up. For a short length near these points the beam has no curvature and hence develops no bending stresses. Such points are called points of inflection. Thus, the deflected beam shape allows a visualization of the distribution of bending stresses in the beam. Beams and columns. Lest it may be construed from this brief discussion of bending that the reinforcing bars in a concrete beam should always appear either near its top or its bottom, let us notice that a vertical column stuck into its foundation acts like a vertical cantilever under lateral loads and may be hit by the wind from either side. When the wind blows from the right, its fibers in tension are on the right and its compressed fibers on the left, but when the wind blows from the left, the role of the fibers is interchanged. In such columns reinforcing steel must appear near both sides of the column. In addition, the reinforcing bars serve to stitch the concrete and keep it together. To this purpose in most beams the bars, set at top and bottom, are connected by vertical hoops of steel, called stirrups, constituting a steel cage containing the concrete. See Fig. 5.12. The concrete, in turn, covers the steel bars, thereby preventing them from rusting. An insufficient concrete cover of the bars, which allows water to penetrate the beam and rust its reinforcement, has been known to make the reinforcement crumble inside the concrete until the structure collapses. This is a dangerous phenomenon because the rusting of the bars may not show on the outside of the structure to give warning of its condition. Shear. When a cantilever is loaded at its tip, it tends to rotate, but its rotational equilibrium is guaranteed by the action of the tensile forces in its upper fibers and the compressive forces in its lower fibers, which tends to make the beam rotate in the opposite direction. Fig. 5.10. Obviously, its translational equilibrium must also be satisfied. This means that since the tip load acts down on it, an equal and opposite force or reaction must act up on the cantilever. This can only happen where the beam is supported. Hence, the support must exert an upward reaction equal to the load, Fig. 5.10, which is called shear because, together / if the tip load, it exerts on the beam the type of action that shears exert on a steel sheet while cutting it. Tension tends to move the particles of the material apart, compression pushes them together, shear makes them slide one with respect to the other. It may be rightly thought that shear action is a new and different type of structural action and that there are 3 elementary structural actions rather than 2, as stated in Chapter 3. This is not so. That shear action is a combination of tension and compression is shown in Figures 5.11a, b, c. Figure 5.lla shows a small cube cut out of a cantilever beam with 2 equal vertical and opposite forces acting on its left and right faces, the load down and the shear reaction up, which together guarantee the vertical equilibrium of the cube. But they're opposite directions together with the distance between them tend to make the cube rotate clockwise, just as pulling with our right arm and pushing with our left tends to turn the wheel of our car. To guarantee the rotational equilibrium of the cube, equal and opposite forces, or shears, tending to rotate the cube counterclockwise must appear on its horizontal faces as shown in Figure 5.llb. This indicates that whenever shear tends to slide the particles of a beam vertically with respect to one another, it also necessarily tends to slide them horizontally. The equivalence of shear to a combination of tension and compression can now be seen in Figure 5.llc. This figure shows how the upper and left shears actually combine to become a tensile force directed up and to the left, while the lower and right shears combine to become an equal tensile force acting down and to the right. But the upper and right shears also combine to become a compression acting down and to the left, while the lower and left shears combine to become an equal compression up and to the right. It is thus seen that shear is structurally equivalent to tension and compression at right angles to each other and at 45 degrees to the shears. A physical proof of this equivalence is given by a reinforced concrete beam insufficiently reinforced against shear. Diagonal cracks at 45 degrees appear near its support, showing that the concrete tensile strength has been overcome by the tension component of the shear. Such cracks are avoided by bending the lower bars of the beam at an angle of 45 degrees near the support so as to absorb the tension due to shear, or by stitching the horizontal concrete layers with stirrups to prevent their sliding with respect to one another. Fig. 5.12. Almost none of the problems presented by concrete beams exist in steel beams, since steel has as good a resistance to tension as to compression. And yet the next section will show that trouble can arise even in steel beams. Buckling. It may seem strange that in a modern steel building the columns should have the same wide flange shape as the beams, when this shape was shown to be ideal for bending while columns are not bent, but compressed. But this choice eliminates one of the most dangerous structural phenomena called buckling, the bending of a straight element under compression. If one pushes down with increasing pressure on a vertical thin steel ruler supported on a table, Fig. 5.13, the ruler at first remains straight, WHY buildings stand UP. But there comes a point when, rather suddenly, the ruler bends out. It can be proved that a perfectly straight ruler acted on by a compressive force perfectly aligned with its axis will bend out suddenly at a given value of this force, called its critical value. The real ruler does not bend so suddenly because it is never perfectly straight. The moment the ruler bends out, the compressive force acquires a lever arm with respect to its axis, Fig. 5.13, and bends it progressively more. This is a chain reaction where the more the ruler bends, the larger the lever arm becomes. This increases the bending action of the force, which increases the lever arm, and so on. Very soon the ruler fails in bending. The column is said to become unstable when the load reaches its critical value. This behavior is typical not only of thin columns, but of any thin element under compression, and has acquired great significance due to the thin sections allowed by modern, strong materials. The columns of a Greek temple could never buckle because they were chunky and short. The slender columns of a modern building are much more likely to buckle. Since buckling is a phenomenon involving bending, it becomes clear why modern steel columns have the shape of wide flange beams. Beams and columns. Their resistance to buckling is magnified by this shape without a costly increase in our material. The load capable of buckling a column, or its critical load, depends on the slenderness, the material, and the way a column is supported. Since the moment of inertia was found to be a quantity characterizing the amount of material moved away from the neutral axis of a beam and hence measuring its bending stiffness, it is not surprising that the buckling load increases in proportion with the moment of inertia of the wide flange columns. The longer a column, the slenderer it becomes, and its buckling load is reduced in proportion to the square of its length. A column twice as long as another has a buckling load 4 times smaller. A column stuck into its foundation and free to move at its top. A cantilevered column has a buckling load 8 times smaller than the same column stuck into its foundation and rigidly connected to a floor at its top, Fig. 5.14. Finally, the stiffer the column's material, the stronger the column. A steel column fixed to a floor at its top is 3 times stronger against buckling than an identical aluminum column. It is interesting to notice that buckling is a consequence of the basic least work law of nature. If an increasing load is applied to the top of dj c a column, the load first comes down by compressing and shortening the column. Since loads always tend to settle in their lowest balanced position, this type of lowering of the load would go on indefinitely, were it not for the fact that at a certain value of the load, the column can lower it further in 2 ways, either by continuing to shorten in compression or by bending out. As soon as the work required to further lower the load is less in bending than in compression, the column follows the easier path and bends. The column buckles. The shape given modern steel columns may prevent the buckling of the column as a whole, but may still allow the buckling of some of its parts when these are thin. Thin webs are most sensitive to local buckling and, at times, must be stiffened to prevent it. Buckling of the web of steel beams may occur near the supports due to the compressive component of the shear. The lower flange of a cantilevered wide flange beam, being thin and compressed in bending by vertical loads, may also buckle. This buckling occurs in a lateral direction, as shown in Figure 5.15, and twists the beam, besides bending it. Buckling is one of the main causes of structural failure. The roof of the Hartford Civic Center hockey rink was a space frame, described in Chapter 10, made out of steel bars. It covered an area of 360 feet by 300 feet and was supported on 4 massive pillars of concrete set 40 feet in from its comers. Its upper bars were compressed by its enormous dead load of 1,400 tons and by the weight of snow, ice, and water accumulated on it. After standing for 4 years, it suddenly failed, at 4 o'clock in the morning following a heavy snowstorm in 1978. 1,400 tons of steel came crashing down on the floor and stands of the hockey rink, where only 5 hours earlier 5,000 spectators sat watching the game. The roof collapsed in less than 10 seconds. This structural failure has been traced by engineers entrusted with its investigation to the buckling, at first, of only a few compressed bars, which shifted to adjoining bars the load they were supposed to support. The overloaded adjoining bars in turn buckled, and the progressive spreading of buckling to more and more bars produced the collapse of the entire roof. This dramatic occurrence shows that one of the most dangerous characteristics of a buckling failure is its suddenness, which gives no warning. Whenever a structure under load chooses the easy path of bending rather than the foreseen path of compression, the structure may fail. Good engineering judgment, correctly shaped and supported elements, strong materials, and careful supervision during construction are needed to avoid this particularly tricky and sensitive structural behavior. 6. Houses. Prehistoric and historic houses. The housing of primitives was usually, but not always, dictated by the environmental climate and the availability of structural materials. The use of wood prevailed wherever this almost ideal material abounded, but its natural decay, due to both humidity and fire, has left few, if any, remains of its use by primitive peoples. Even so, we can infer from the housing of the primitive tribes still living in our time that huts were first erected by leaning tree trunks or branches one against the other in a circular pattern so as to obtain a conical structure, which was then covered with mud. As centuries and millennia went by, the basic cell of the house acquired a rectangular plan. Walls of vertical trunks and mud appeared in cold climates together with roofs of wooden beams running from wall to wall made weatherproof by means of mud or earth sods. In hot climates, walls were made of small branches or cane, and roofs were thatched. The dimensions of the cell were limited by the length of the available timber, until interior columns were introduced. To reduce the beams' spans or to allow the use of long beams which would have been too flexible without intermediate support, Fig. 6.1. Finally, spans between walls were made longer, by use of main beams in the shorter direction of the rectangular plan and of secondary beams spanning the main beams. The essentials of the structural system to be used in houses for thousands of years had been established. This structural system delegated the resistance to wind and other horizontal forces to the outer cantilevered walls. The minor resistance of 90. Houses. The walls to bending and the weak connections between columns and beams, tied by vegetable ropes, made them easily damaged or destroyed by winds and earthquakes. This liability was not overcome until the Middle Ages, when solid, nailed joints between wooden elements were invented, and modern times, when monolithic construction was made possible by mortar, concrete, and steel. The solution to the housing problem took a totally different form in those areas of the world, like Asia Minor, Greece, Crete, Sardinia, southern France and England, where stone was abundant and wood scarce. In a band running uninterruptedly through this area, prehistoric houses dating back as early as 5000 BC still stand, characterized by a round plan, stone walls, and stone roofs. Houses with as many as 3 interconnected circular rooms and 2 stories are found among the Nuraghi of Sardinia. One of these has even a spiral outer staircase connecting 2 superimposed floors. The domed roofs of this type of house, the corbelled domes, are obtained by circular layers of stone slabs, each cantilevering inward from the layer supporting it and wedged in by the layer above it, Fig. 6.2. The trulli, see Fig. 1.2, the traditional housing of the villages in a large area of the Puglia region of southern Italy, are identical to the Nuraghi except for the whitewash inside and out. The palaces and houses of the Minoan civilization on Crete, which were built between 3000 and 2000 BC, have rectangular plans with outer stone walls and intermediate stone columns. They apparently were covered by wooden structured roofs, which have disappeared. The palaces had plastered walls covered with the most brilliant frescoes, some have survived, and large windows and doors framed by wooden beams. The bending resistance of wood allowed these large openings in stone walls. The wooden lintels at the top of the openings, supporting the stone blocks above them, were propped by wooden columns on the side of the openings. Airy and light housing with as many as 4 floors was thus created, ideally suited to the warm, at times tropical, climate of Crete. The Minoan civilization, which suddenly disappeared toward the middle of the 16th century BC, was transplanted to Greece, giving rise to the Mycenaean cities, again built with stone walls and wooden roofs or corbelled vaults. In extreme climate, solutions of a different character were adopted. In the jungles of Amazonia in South America, some tribes lived in extended households with as many as 100 people. Their houses, consisted of vertical wooden posts set in a large circular pattern, connected at their tops by peripheral wooden tree branches and secured by radial branches to vertical posts set in a smaller, inner, concentric circle, Fig. 6.3. A platform, raised a few feet for protection from the poisonous animals creeping on the ground, and a thatched roof completed the house. There were no walls and the cool wind could flow through unimpeded. What made this scheme interesting was the procedure used to protect privacy in the absence of partitions of any kind. The method was as simple as it was effective. If the occupants of the house were looking towards the outside, they were in public and behaved accordingly. But, if they looked toward the inner posts, they became invisible and could perform the most intimate acts of life unnoticed by their large family. In the Arctic, the Eskimos invented the igloo, a dome in the shape of a perfect half-sphere made out of snow blocks, which by its form is aerodynamically efficient in reducing the wind pressure on the building and at the same time produces one of the strongest structural shapes devised by man. The strength of a dome is superior to that of almost any other structural form, as we shall see in Chapter 14. The fire set in the middle of the igloo melted a thin layer of snow, that became ice when the fire was extinguished, making the igloo totally impermeable to the wind. Made of a material with unlimited availability, the igloo could have been a permanent abode, but was easily erected in a few hours when the Eskimos moved in search of food. Their mores allowed them to abandon their elders to freezing death on the ice pack when they became unable to undertake the long marches from one location to the other. On the other hand, Eskimo hospitality insisted that a solitary male traveler sleep in the same sleeping bag with the host's wife. It seems that concepts of modesty and morality are heavily influenced by the climate and the housing it demands. The use of sun-dried clay and adobe, a material relatively strong in tension and compression, was common in the dry countries of the East, and the later invention of fired clay bricks made possible the development of the Roman house, which was to become typical of the houses of the Middle Ages. These had not only brick walls, but roofs of clay tile supported on wooden inclined beams and superimposed horizontal beams, called purlins, a tradition which has survived to this day in many parts of France, Italy and other countries throughout the world. Walls of fired clay brick, held together by mortar, a mixture of lime, sand, and water, have a certain amount of resistance to tension, and thus to bending, and a remarkable resistance to compression. The tower of the City Hall of Siena in Italy, known as the Torre del Mangia, from the nickname of one of its bell ringers, famous for his gargantuan appetite, is built entirely of mortared brick and reaches a height of 334 feet. Although built in 1348, it is even today the tallest brick tower in the world. The height of the masonry lighthouse at Pharos in Alexandria, Egypt, erected in 300 BC, which collapsed in AD 1326, is said by some historians to have been higher, either 370 feet or even 600 feet. Houses with bearing wall of brick and mortar and with floor beams of wood could be many stories high due to the partial bending resistance of the walls against wind. The use of steel beams made possible longer spans, and modern housing with bearing walls of brick, stiffened by light reinforced concrete columns and beams, reaches today up to 27 stories. The American house. In the United States, as anywhere else, traditional houses were built of the most commonly available materials. In the Southwest, the mixture of clay and straw called adobe was used to build houses with thick walls, warm in winter and cool in summer. In the Great Plains, the pioneers used the sods cut by the plow in regular blocks to build walls and sometimes roofs of houses that were safe against fire, wind and earthquake. In wooded regions of the North, the log cabin, easy to build, with walls and roof tightly joined, safe against wind and comfortable in all seasons, has remained so popular that to this day 2 million of them are built a year, all the way from do-it-yourself models to mansions costing hundreds of thousands of dollars. The abundance of wood, new treatments against fire and insects, and standardization of structural elements in the shape of beams and columns of rectangular cross-section, the so-called 2x4s, 2x6 or 4x shave, made the one-family wooden house our most popular, even today. Limited to 1, 2, or at most 3 or 4 stories, these houses are supported by wooden columns, rigidly connected to the floor and to the roof beams. These rigid connections make them strong against lateral forces, because any force trying to bend the columns must also bend its beams and make them help carry the loads. Figs. 6.4, 6.5. Columns and beams are said to act as a frame. When one side of the frame is hit by the force of the wind, its beam transmits half of it to the other side by compression. While by virtue of the rigid connections the turning action of the wind is mostly resisted through the upward reaction of the leeward column and the downward reaction of the windward column. Fig. 6.5. The floors of narrowly spaced oists with nailed plywood covering increase the horizontal stiffness of the house besides carrying the floor loads. Fig. 6.6. 95. Thus, an all-wooden house with a structure of frames and triangular roof trusses, and with walls of sheathing and shingles, is capable of resisting the usual vertical loads of snow and the heavy forces due to the wind, except, at times, those of hurricanes and tornadoes. Since such houses can be built with simple tools, carpenters have always been responsible for a WHY building's stand up. Large percentage of the housing built in the United States. Framed and trussed wood buildings have been erected in Europe and other parts of the world since the Middle Ages, and houses similar to the American one-family house are built today in all countries having large availability of timber. The pre-cutting of wood beams and columns to standard sizes, the manufacture of inexpensive mechanized tools, and the production of easily installed heating and plumbing systems have perfected the old structural and mechanical systems, making the one-family house widely available. Entire pre-cut houses are sold to be assembled by the owner himself. These and the pre-cut log cabin houses are examples of prefabrication. Concrete frame housing. Frame action against wind and earthquake forces. Recoming rigid connections between the columns and the beams of the frame is inherent in reinforcing concrete construction. Frame structures of reinforced 96 concrete were built from the very inception of this modern material and are used all over the world, mostly for housing purposes. Houses. In a reinforced concrete building, heavily reinforced concrete foundation blocks, called footings, are first poured in the ground, often below its original level or grade in order to better utilize the available site area through the construction of one or more underground floors or basements. This is of the utmost importance in large cities like New York, where land may cost as much as $60 per square foot or almost $9 million for a high-rise building plot of 120 feet by 120 feet. Some of the footings' reinforcement is left protruding and hollow vertical wooden or steel forms for the columns are built around them over the footings. A cage of vertical reinforcing bars and horizontal thinner stirrups, Fig. 6, 7, is first lowered into these forms and concrete is then poured into them, leaving a length of vertical bars to stick up from the forms. Once the column concrete has set, a horizontal surface of wood planks, propped at many points by wooden columns or struts, is erected at the level of the column tops. Reinforcing bars for the floor are laid on top of the planks in a rectangular grid, supporting them on small blocks called chairs 1 or 2 inches above the planks. The bars of the floor are 97. Why buildings stand up. Tied to those coming out of the columns, and the thin concrete floor slabs are then poured over the horizontal planks, with the chairs allowing the concrete to flow under the floor bars, which are thus completely encased. The procedure is continued floor by floor, dismantling the forms for the columns and the floor planks after a few days and reusing them to build the upper floors. Once the concrete has completely set, the structural frame of the building consists of the columns, distributed more or less on a rectangular pattern, and of the floor slabs that, besides carrying the loads on the floors, act as horizontal beams to produce frame action between columns and floors in 2 directions. The length of bars superimposed at the top and bottom of the columns, Fig. 6.8. The continuity between columns and floors due to the set concrete, and the tying of the reinforcement of the columns and floors, create a structure that works always together. If one part of a floor is loaded and bends down, the adjoining parts of the floor and the columns will also bend and help the loaded floor to carry its load. Fig. 6.9. Such a framed structure is, in a sense, most democratic, since each one of its elements helps the carrying action of every other element. This action, which is due to the continuity of the structure, diminishes as one moves away from the loaded area, just as in a family distant. Relatives are inclined to help less than parents, brothers, or children. The reinforced concrete system just described gives rise to flat slab construction, which is ideal for housing due to the limited gravity loads required by building codes, the small spans between columns, and the simplicity of running pipes and ducts along the flat underside of the floors. 11-2 Illinois 1L JLJ Illinois JC JC JCJ, JC. RFJB3RE. Underscore GIC LFJLJI LC22 IL. 11 times houses. 99 without having to duct horizontal beams. For buildings with longer spans or carrying heavier loads, the columns are connected at their tops in two directions by horizontal beams, which in turn support the floor slabs, Fig. 6.10. These are conveniently poured in thicknesses of up to 12 inches and reinforced with a grid of bars running in directions at right angles to each other, so as to act as beams in both the direction of the width and the depth of the building. When the required floor depth exceeds 12 or at most 14 inches, floors are built as waffle slabs. These are created by placing on the flat formwork of planks for the floor square pans of steel or plastic, called domes, spaced at regular intervals in a rectangular pattern leaving gaps between them in two directions, Fig. 6.11. Reinforcing bars are set on chairs along these gaps and the concrete is then poured to a depth a few inches greater than the height of the domes. Once the concrete has set, the formwork is lowered by knocking off its supporting struts and the domes fall off, since they have been previously greased and do not stick to the concrete. While the upper surface of the floor is flat, the underside presents beams in two directions, as wide as the gaps between the domes. This system of perpendicular ribs gives the underside of the floor the appearance of a waffy, Fig. 6.12. The actual slab of a waffy floor, spanning between the close ribs, can be made quite thin, not more than a few inches. A large amount of concrete is thus saved, which would have been otherwise misused located in the lower part of the floor, where tension develops, as it does in the lower part of a beam. The domes can be reused many times and the formwork of wood for the floor is as inexpensive as in a flat slab, since it is still built by means of flat planks. Waffy slabs can carry substantially heavier loads than flat slabs and are used mostly in industrial buildings, although their appearance is so interesting that some architects use them exposed in other types of buildings as well. A concrete frame cannot be as high as a steel frame, but can be high enough to constitute the skeleton for a high-rise. The outer walls of such buildings are curtain walls, which do not carry loads. They can be made of light metal window frames and contain a large amount of glass, or they can have wall panels, with window openings, made of prefabricated concrete or blocks, similar to large bricks, glued with mortar, Fig. 6.13. Actually, the concrete blocks are strong enough in tension and compression to be used as bricks in load-bearing walls. The highest building erected so far with load-bearing walls of concrete blocks is the hotel at the Disney World in Florida, which is 192 feet high. However, high-strength plastic epoxy resin was used in its construction rather than mortar. Prefabricated concrete buildings. One of the disadvantages of concrete construction is the time required for the concrete to set, which makes the erection of a frame relatively slow. Since money to erect buildings is usually borrowed from banks at high rates of interest, any procedure that speeds up construction reduces cost. This requisite has introduced during the last few decades the methods of prefabrication in concrete construction. There are two basic methods of concrete prefabricated construction, one by beams and columns, and one by slabs. Both very much resemble the way children put together buildings of sticks or packs of cards. The sticks method consists in fabricating in factories columns and beams of reinforced or pre-stressed concrete, which are cured at high temperature so that the material can set in a few hours rather than a few days. This pouring and curing can be done while the foundations of the building and Other preparations are made ready so that time is saved both in the fabrication of the structural elements and the scheduled erection of the building. The prefabricated components, which can be shaped in a variety of ways at the pleasure of the architectural designer, are of very high strength due to the controlled curing process. Once ready, they are transported to the site and joined together to make a concrete frame either by pouring high-strength concrete at their joints, thus encasing the reinforcing bars left sticking out of them, or by pre-stressing tendons that pull together two or more adjoining elements, Fig. 6.14. A frame of such prefabricated elements can be erected almost as rapidly as one of steel and has become quite popular in countries in which the specialized manpower needed to execute the joints is not as expensive as in the United States. By far the most magnificent applications of this method were Pierluigi Nervi's airplane hangars built in Italy in the 1940s, Fig. 6.15. Measuring 1,080 feet by 427 feet, these hangars consisted of prefabricated reinforced concrete struts, or trusses, connected into arch shapes by welding the bars sticking out of the struts and by concreting the joints between the struts. Two sets of such arches, at an angle to each other, created a curved surface, supported by four large arched buttresses at the corners of the rectangular plan and sometimes by two additional ones at the middle of its long sides. Such a skeleton is commonly made out of wood or of steel in the United States and abroad and is called a lamella roof. Since only small cranes, capable of lifting not more than 2.5 tons, were available to Nervi, he had to lift in place and connect many hundreds of struts at a height of 40 feet above ground and then fill the openings between the struts by means of concrete slabs. The main criticism of this construction at the time was that it did not make use of the most favorable property of concrete, that of allowing monolithic construction. Nobody believed that the joints could make the structure as strong as a continuously poured roof. Unfortunately, a most drastic experiment proved only a few years later how unjustified this criticism of Nervi's joints was. When the Germans retreated from Italy during the last phase of World War II, they dynamited the 6 arched buttresses of these roofs, which crashed down to earth from a height of 40 feet. No concrete structure had ever been submitted to such a dynamic test, but even so Nervi's roofs remained intact, except for a few among many hundreds of joints. The lesson, although painful to Nervi, was not lost on him and led him to even more daring prefabricated buildings later on, as we shall see in Chapter 11. The second method of concrete prefabrication was perfected in France and other European countries after World War II and has been patented in a great number of slightly different forms. Essentially, it rests on the concept of putting together a building like a pack of cards. The cards are reinforced concrete slabs, poured and cured on special tiltable flat boxes of steel. These boxes can be heated by steam running in pipes attached to their underside and to the hinged steel tops that close the boxes after the concrete has been poured, Fig. 6.16. After the few hours required for curing, the boxes are tilted to a vertical position and the slabs are grabbed by a crane that brings them to rest in the factory's yard, where many can be stood on end, one next to the other, without using too much yard space. Simple slabs of the type described are manufactured to be used as floors and interior walls, while more complex prefabricated slabs, incorporating a layer of insulation and openings for windows, are used for the outside walls of the building. The reinforcement of all slabs sticks out so that the slabs can be joined together by pouring concrete in the horizontal and vertical joints, thereby producing a monolithic structure which performs also the functional duties of outside walls and partitions, Fig. 6.17. The partitions are, of course, load-carrying walls, while the floor slabs are capable of carrying loads due to their two-way reinforcement similar to that in the slabs of hat slab buildings. One of the main reasons for the economy achieved by the slab prefabrication method is that electrical conduits, water pipes, and air conditioning ducts can be set into the forms before pouring the concrete so that the mechanical systems are incorporated in the structural system. Moreover, all work is done inside a factory and at grade level rather than in the open air and at increasing heights, saving time and providing greater safety and comfort for the workers. Buildings of up to 30 stories have been thus built in France, the USSR, England, and the Scandinavian countries of Europe, as well as in Japan and other technologically advanced countries. Notwithstanding the support of the federal government, the slab method of prefabrication that has been so successful in building inexpensive housing abroad has not become popular in the United States. This failure is due mainly to two quirks of the American mind. On one hand, both the architects and the presumed occupants of such housing have consistently rebelled against the standardization and monotony of their appearance, even though the dimensions, space distribution, and composition of such houses can be varied so widely that prefabricated slab buildings are often less monotonous than our enormous low-income housing developments. The incredible construction by the prefabricated slab method in record time of entire suburbs in Bucharest, housing 200,000 to 300,000 people, proves this, as do similar buildings in the Soviet Union. On the other hand, part of the economic advantages achieved by the incorporation of the mechanical systems in the slab has been lost in the United States because the construction trade unions refuse to allow it. They are fearful of losing lucrative positions for their workers to easily trained, unspecialized labor. Thus, some deeply rooted ideas, difficult to eradicate because not entirely logical, have limited the application of these modern methods of housing construction in the United States, where to this day the scarcity of housing is all-pervading. Lest it should be felt that Americans are alone in this prejudice, it might be instructive to note that in the city of Milan families on welfare refuse to occupy apartments in concrete slab buildings. They could not stand living in and looking at buildings which had all identical windows. A comparison with the housing habits of the Patagonians and other primitive tribes shows that once the basic needs of humanity are served, other factors come into play. People will not be forced into buildings that do not attract them. One of the great challenges of architecture today is to join technological and economical requirements in innovative and winning designs. 7 skyscrapers. The high-rise building. They were called skyscrapers, a name to exalt the human mind. They are now called high-rises, a matter of times fact name that does not dare to reach the sky, and sometimes towers, a return to the Middle Ages and preoccupation with isolation and defense. In 1913 the Woolworth Building, dared to reach 55 stories, soaring up 791 feet. It looked like a Gothic cathedral. Only 18 years later the Empire State Building, reached 102 stories and 1,250 feet and took on the appearance of a modern building. Most high-rises are square, but there are high-rises with from 3 to 6 sides, as well as round ones. Some of them seem to be made of ethereal glass and reflect the ever-changing show of clouds and sun moving in a blue sky against a background of dark buildings. Others are as massive as fortresses of concrete. Some with the elegance of great ladies are clad in most expensive materials, like bronze. Others have the poise of distinguished matrons, dressed with slabs of black granite. Some are lily-white, with surfaces of anodized aluminum or treated concrete. Most exhibit in their facades the rigidity of geometrical forms, but some culminate in curlicued tops, reminders of Chippendale furniture. Some are textured and balconied, others as smooth as a wall of satin. Some proudly show on their surfaces bold structures of unrusting steel or of smooth, sand-blasted concrete. Their roofs are flat, for the most part, but some are inclined at steep angles. A few have curved, sloping facades of dark solar glass, which act like the distorting mirrors of sideshows. Some consist of a single slender tower, others of 2, sometimes identical like twins, sometimes of different shape or height, looking at each other in permanent challenge. All high-rises contain offices, but some have stores at street level, hotels above them, offices higher up and apartments toward the top. Some generously give parts of their site to the public, to be enjoyed as gardens of trees and sculptures, in calculated exchange for the advantages of greater heights conceded by city planning commissions. Others enclose in their interior immense, glass-covered atriums reaching hundreds of feet, available to the public for the same hidden reasons and advantages. Some are built on air rights over slightly older buildings or behind them or up from their courtyards. Some contain such a variety of occupancies that one could be born and live a fairly varied life in them, leaving only at the end in a casket. High-rises have changed the appearance of many a city, creating new skylines as impressive as mountain ranges. Even in socialist countries, their location is carefully studied in relation to their effect on the landscape. They are a dream to the engineer and anathema to the city planner. Volumes have been written about their influence on the life of man, both from a physiological and a psychological point of view. They have grown suddenly all over the world. In the capital of one of the European socialist states, the visitor is shown before anything else the skyscraper 17 stories high. In a small town in Tuscany, the citizens, oblivious of their medieval glory, point with pride to their skyscraper of 6 floors. Beyond any considerations of economy and energy savings offered in its defense, the skyscraper represents the fulfillment of one of man's aspirations, first voiced in the Bible. The same compulsion that sent Mallory to his death only a few hundred feet from the top of Mount Everest drives men to erect taller and taller buildings. They matter not because of their absolute height, but because they overcome the height of other buildings. In the flat countries of the north, towers are built just to look down at the plains, and this in the age of the airplane. Their purest expression has not been achieved yet but has already been suggested, sculptures as high as skyscrapers, existing only to be looked at. The race is on to build the first high-rise with 150 floors. Frank Lloyd Wright, always a visionary and the wittiest of architects, designed, probably as a joke, a building 1 mile high. But we should not be taken in by the skyscraper phenomenon. It is only 75 years old and could well be a passing whim of the mind of man. Posterity will tell whether, like so many other buildings, they will be demolished when they become economically inefficient or whether they will remain as permanent monuments to our dreams and folly. For the time being, their favor is not diminishing. In 1980, 27 of them were growing together in the center of Manhattan, healthy again after a few years of neglect due to temporary economic conditions. The growth of a high-rise is a civic drama of imposing magnitude. Let us understand it and, possibly, enjoy it from its very first act. The birth of a skyscraper. If birth is counted from the day of conception, as in the Buddhist canon, the inhabitants of a large city are never aware of the birth of a skyscraper. Its conception is in the mind of a professional real estate developer or of a corporation president years before the first step for its construction is undertaken. The search for a proper site starts only after a long series of thorough economic studies based on the requirements of the building and on the financing of its erection and operation. High-rise buildings may be built by developers to be sold to a client immediately upon completion or to be leased for long periods of time to a corporation. Banks must indicate the exact conditions of their mortgages, the city must express an interest in the building and specify the concessions, if any, it is willing to make beyond the rules and regulations of its building code. At long last, agreements in principle are reached on all these complex and interrelated matters. After a successful search for the site has been completed. With luck, a clear site may have become available, satisfying all the conditions. Most often the site had to be put together by buying in utmost secrecy a number of small adjoining sites, so as not to alert their owners lest they should increase their demands exorbitantly. The owner of the last tiny corner plot needed to complete a site has been known to hold up construction for months in order to obtain compensation 10 times higher than the real value of his land. Sometimes this tactic fails. A few skyscrapers in New York City have been built around an old restaurant or pub, rather than accepting the prices demanded by these establishments. Once the site has been acquired, construction must start at the earliest possible date in order to save mortgage interests and to obtain early. Putting together the site for the Avon building in New York at 9 West 57th Street took years of stealthy assembling of lots. As is the case for the building labeled 900 3rd Avenue in New York. Returns from the enterprise. It is at this moment that the first technical experts enter the game. Perhaps with the help of a computer program they decide, on the basis of many factors, the optimal size of the building, its height, the percentage of the site area to build on, the type of occupancy or occupancies, the size of the rooms, the number of elevators, their type and speed. The output of such programs has already played an important role in the search phase of the enterprise but becomes central to it now. At the same time, an architect is chosen if he was not already a member of the team, and starts contributing his ideas to the realization of the building. He cannot do this alone. He surrounds himself with a large group of experts: the structural engineer, the mechanical engineer, the construction manager, the environmental engineer, the cost estimator, the city code specialist. The team prepares sketches and estimates which must win the approval of the owner and of the various city departments of transportation, fire, building, and planning. As soon as the team feels that approvals are forthcoming, the first public act of the drama is unfolded: the excavation of the site begins. The wooden fence is built around it, decorated by signs advertising all the component members of the construction team. Holes are left in it for the sidewalk superintendents, and the noisy, messy, but highly organized process of excavating starts. Of course, if the site contains older buildings, these must be demolished by charges of dynamite, by the wrecker's ball, and by the dangerous and patient work of men perched on top of the ruinous walls, pick in hand, destroying the structure under their own feet. The demolition remains are carted away, but seldom discarded, since old steel is used in the manufacture of new steel, and old bricks, made stronger by time, may be worth even more than new ones. At this point, steel piles called soldiers are pushed into the earth all around the boundary of the site at 10-foot intervals, and wooden planks, known as breastboards, are set behind them to ensure that the sides of the excavation will not cave in. Fig. 7.1. Then holes are punched for inclined steel bars, which will support the sidewalks or the adjoining buildings. Many problems can be encountered at this stage, since networks of pipes and saws may run under the site. A subway line may even cross it. In this case, the subway tunnel is spanned by heavy steel girders, which may be 7 or more feet deep and will eventually support the portion of the building over them. When the soil to be excavated is not hard clay, sand, or weathered rock, the big front-loaded shovels scoop it out and load it on trucks for removal. Solid rock must be dynamited. The drilled holes in which the dynamite sticks have been embedded are covered with mattresses of heavy chain mesh to check the flying debris. 1 whistle blast warns the workers that the explosives are in place, 2 blasts require that they take shelter, and 3 give the all clear. The site is covered with seismographs, instruments used in measuring earthquake tremors in order to assess the effect of the explosions on the adjoining buildings. These must often be underpinned with walls of concrete going deep into the ground lest the excavation and the explosions damage them. And, to play it safe, numerous photographs of the foundations of the adjoining buildings are taken to disprove any later allegations of damage. Sometimes a deep excavation may reach soil capable of sustaining the enormous loads on the footings of the high-rise columns. At other times the soil continues weak to such a depth that it must be consolidated. This is done by hammering into the soil steel or reinforced concrete piles, reaching down to lower layers of stronger soil. Pile drivers do the job by dropping a heavy mass repeatedly on the top of the piles, to the desperation of the neighbors, who must endure this jarring noise for weeks, sometimes months. For their peace, in New York City an ordinance forbids this work to start before 8 in the morning or to last after 6 in the evening. There was a time when skyscrapers could be built only on solid rock. This explains the flowering of skyscrapers in Manhattan, which is mostly a rocky island. Modern soil techniques permit now the erection of high-rise buildings on the weakest soils. The John Hancock Insurance Company building in Chicago, 100 stories tall, is founded on soil so weak that its 4 commas had to be supported on numerous caisson steel tubes 3 feet in diameter and filled with concrete, some of which tended at first to sink into the ground. The Twin Towers of the World Trade Center in New York City, the second tallest building in the world, rest on a soil of low consistency that was consolidated by a special chemical process devised by an Italian company. Although these processes are costly, they make it possible to erect a modern tower almost anywhere. Once the work of the wreckers and the foundation contractors is finished, at long last the erection of the building starts. Certainly many months and at times years have passed since the idea of a skyscraper first glimmered in the developer's mind. Not that this time was wasted. Quite the opposite. All modern buildings are erected at present by the FA.ST track method, which consists in starting the construction of a building before its design is completed. There was a time when no construction would start until the last detail of the project had been designed and accepted by all concerned. Today these approvals would mean a delay of a year or more, and such a delay is unacceptable due, among other things, to inflation, which pushes up costs of materials and labor. The prolonged mortgage payment periods and the delay in receiving the first income from the building are other considerations in favor of fast-tracking. Fast-tracking is facilitated by the design procedure followed by the structural engineer. He first produces a schematic design based on architect's sketches in which the main components of the structural system are defined, such as the material, steel or reinforced concrete, the pattern and spacing of the columns, the type of floors, and the main wind bracing system. Through experience, this part of the design can be done in a few weeks, and approximate methods of estimating the quantities of required materials to within 10 to 15%, based on this scant information, have been devised. As soon as the schematic design is accepted by the architect and owner, materials to be delivered months later are ordered and contracts for their manufacture are signed. The structural engineer can then proceed with a more detailed preliminary design and cost estimate and, eventually, with the design documents. These consist of the working drawings, containing all the details of the structure, together with a thorough set of prescriptions for the manufacture and erection of the skeleton. These specifications constitute a document of the utmost technical and legal importance. The design documents are submitted to the building department for their official approval and are the basis for the bids to be taken and the prices to be paid. Open bids invite any contractor willing to participate, while limited bids are open only to contractors known for their capacity and integrity by the architect, the owner, and the other members of the team. The contract documents comprise the final drawings, whose preparation may cost $7,000 or $8,000 each, and the specifications. Behind them is all the computational work done on the hand calculator or on the electronic computer and based on the engineer's experience and the restrictions of the prevailing codes. At this time, the contractor winning the bid, who becomes there and then an important member of the construction team, must prepare more detailed drawings at a larger scale, the shop drawings, which are used by the fabricators in the shops to manufacture the separate elements and by the workers on site to put the building together. These ultimate drawings are reviewed and finally stamped for approval by the structural engineer. It would seem that after all these checks and counter-checks, few mistakes, if any, should ever occur. But people are fallible, and last-minute modifications do occur before the building finally goes up. Shop drawings in hand, the superintendent of construction directs the various operations. The first is to pour at the exact location of the columns the footings on which the columns will rest. Next, the steel columns manufactured in the fabricator's shop, with the holes for the high-strength bolts exactly located, are connected to the footings by bolting them to their protruding threaded bars until the forest of columns of the lowest floors is in place. These are then connected by the main beams, between which secondary or filler beams are often set to reduce the spans of the floor. Floors consist of reinforced concrete slabs poured on ribbed steel plates or decks, Fig. 7.2, which, supported by vertical struts during construction, serve both as forms for the concrete and as steel reinforcement instead of bars. Once the concrete sets, the struts are knocked down and the floor becomes a ribbed slab reinforced by the steel deck. The next set of columns is similarly erected together with the next floor slabs, and the skeleton grows, usually at the rate of a complete floor, columns and slab, every 3 or 4 days. During this operation, steel derrick small, easily demountable cranes are used to lift the columns and beams and set them in place. After a perfectly analogous procedure is followed in erecting a concrete high-rise, which the derricks pull themselves up to the next floor by their own bootstraps or with the help of the large cranes set along the periphery of the building to lift steel elements and concrete buckets to the high floors. For extremely tall structures, only these derricks can do the work, since cranes reach at most 300 feet, and an elevator attached to the side of the skeleton lifts materials and people to the work level. It is particularly thrilling to see the ironworkers, the boomers, walk on the narrow beams and tighten the bolts of the connections with the same nonchalance of the people looking up from the pavement many hundreds of feet below. Helmeted, carrying their tools on thick belts, these men and women perform an aerial ballet that would dizzy most of us. When the steel skeleton has reached the projected height, the building is said to be topped out. A flag is flown from the highest point and a celebration is held, where engineers and architects compete with the construction men in the appreciation of food and beer. But all the skill of the ironworkers, the care of the superintendents, the rules of the safety agencies, and the supervision of the insurance companies do not eliminate entirely the possibility of accidents. Some members of the construction team may be absent from the celebration. As the upper floors of the skyscraper are being built, the lower floors are completed by attaching the curtain wall to its exterior columns, so that work on the mechanical systems can be done in an enclosed space, made comfortable by temporary heat in winter. Vertical and horizontal pipes, electric conduits, and air conditioning ducts are attached to the skeleton after it has been painted with coats of anti-rust paint. Eventually, partitions and hung ceilings, which cover intricate networks of pipes and ducts, are set in place, together with the thermal insulation around the columns and the sprayed insulation on the lower surface of the steel decks, which will make the building fire retarded, as required by code, for the safety of its occupants. The sprayed insulation, that formerly consisted of a compound of asbestos fibers, was responsible for the exceptionally high number of deaths by lung cancer among the workers specializing in this type of work. Asbestos is prohibited now and, at long last, new, safe materials have been substituted. Partitioning and flooring are the very last jobs to be done, since they require the approval of the tenants and, at times, minor modifications to the structure. There is seldom an opening celebration of a skyscraper. The tenants occupy their premises as soon as these become available, while construction continues elsewhere and work on details lingers for a long time, often years. But the skyscraper was born and grew strong and healthy and on schedule. The design and construction team feel deeply about this last accomplishment, but must thank for it an unsung hero of the entire performance, the construction manager. This is not a person but an entire company, charged with the task of making sure that the erection of the building proceeds smoothly, without any undue delay in the arrival of materials to the site and in their erection, in the various reviews by the engineers and the architect, in the approvals by the owner, the architect, and the city officials. This is a monumental task of bookkeeping, made easier and at times only possible by the judicious use of computer programs, capable of keeping track of the infinite number of operations and materials used in the erection of a large structure. These programs, which are updated daily and weekly and whose results are presented visually on bar charts, Fig. 7.3, indicating the beginning and the end of each operation, are the only guarantee that the work is proceeding correctly and on schedule. A good construction manager is a blessing to the entire team, and his advice and admonitions are followed with the greatest respect. When we look at a growing skyscraper from the construction viewpoint, we forget that its composer and conductor, who at all times orchestrates the performance of the work, is the architect. He is the creator of the building and the leader of the team. To him goes the glory and the total responsibility, to the owner, the occupants and, above all, to the public. Architecture is today one of the most exciting and creative professions in the world, and so complex that few become recognized as great architects at the end of their career. Artist and technician, leader of men and expert in the ever-changing fields of finance and politics, the architect is perhaps the greatest humanist in our complex and at times chaotic societies. The skyscraper structure. The skyscraper is a triumph of American design and construction engineering. The key to its stability is a resistance to lateral wind or earthquake forces, which grow dramatically in magnitude with the building's height. For moderate heights of 30 or 40 stories, stability can be assured by the frame action of beams and columns rigidly connected at their joints. Reinforced concrete creates these rigid connections by its very monolithic quality. Steel is given rigidity by bolting the connections with high-strength bolts or by welding. Thus in 1883 Chicago engineer William LeBaron Jenney conceived and built the first building completely framed in steel, the Home Insurance Building, using all types of beam and column shapes. Only 20 years later the first high-rise made of reinforced concrete, the Ingalls Building in Cincinnati, was erected to a height of 16 stories. The frames of these buildings were not only capable of channeling the gravity loads to the ground, but of resisting the wind forces with a relatively small sway, thanks to their masonry walls that added materially to their lateral stiffness. The wind was always the essential obstacle to the great construction heights made possible by the high-speed elevator invented by Otis in 1857. It is easy to understand why. The weight of the structural materials needed to build a floor is the same whether the floor slab and its supporting beams are erected at the 10th or the 100th story, since each floor carries more or less the same loads. Columns, however, must carry the weights of all the floors above them. Therefore the lower floor columns carry much larger loads than those at the top. Actually, the topmost columns carry only the load of the roof and their own weight. Those of the next floor down carry twice as much load and, as the loads accumulate down the building, the bottom columns carry the weight of all the floors of the building. In other words, the load on the columns increases with the number of floors of the building, and their weight must vary in the same proportion. But both the wind forces and their lever arms increase with the height of the building. Their product that measures the tendency to tumble the building over, see Chapter 5, thus increases with the square of the height. The Sears Tower, about twice as tall as the Woolworth Building, must resist wind effects 4 times as large as those on the Woolworth Building. With the high strength developed by both modern steel and concrete, resistance to these forces would not be a real difficulty were it not for the swaying due to the elasticity of these materials, which must be limited to ensure the comfort of the skyscraper occupants. For reasons of both safety and comfort, buildings must be stiff. In the first skyscrapers, horizontal rigidity was obtained by the use of closely spaced columns and deep beams and by filling the voids between them with heavy masonry of brick walls. The key to the solution of lighter frames and partitions was found when it was decided that the channeling of the gravity loads to earth and the resistance to wind forces should be attributed to 2 separate structural systems. This simple concept gave rise to buildings with relatively flexible exterior frames and an inner core of stiff wind-bracing frames, inside of which ran the elevators and many of the pipes and ducts of the mechanical systems. The frames of the core, in addition to beams and columns, had diagonal bars which exced their openings, Fig. 7.4, and gave them greatly increased stiffness by working in tension and compression rather than in bending. Remembering how the longitudinal deformations due to pulling and pushing are minute as compared to the lateral deformations due to bending, it is not difficult to realize how the triangulated frames of the core can be light but stiff enough to resist almost all the wind forces. Diagonals, of course, cannot be systematically used in exterior frames without cutting across windows or in interior frames without destroying open door space. 3 of the 4 frames surrounding the core can be exed, and the 4th can be stiffened around the relatively small elevator door openings. It was an easy step to realize that the cooperation of 2 different materials could achieve the same results with increased economy. Rather than stiffening the core frames by means of diagonals, one could fill their openings with thin, concrete walls. Such walls have great stiffness in the horizontal direction, as one may find out by trying to slide in opposite directions the upper and lower sides of a piece of plywood or cardboard, Fig. 7.5. It then becomes logical to build the entire sides of the core with reinforced concrete walls, thus obtaining an interior narrow, self-supporting, stiff tower, to which the light, outer steel frame is attached. To go the last step, one must be aware of the fact that in steel construction rigid or moment, bolted or welded, connections are costly, Fig. 7.6. They require specialized manpower and dangerous work at great heights. Their cost may represent 10% of the entire cost of the structure. But, if the inner core was stiff enough, one could forsake the rigid connections between the beams and columns of the exterior frames and use much cheaper connections, which allow beams and columns to rotate one with respect to the other, as if they were hinged, Fig. 7.7. Such hinged, or shear, connections could not be used without a core, since the frames would collapse like a house of cards, Fig. 7.8, but they are economical and practical if the core stands up rigidly and the outer hinged frame leans on it. The separation of the two structural functions is now complete. The hinged frame carries the vertical loads to the ground and the core resists the wind forces. The principle of using the walls of a concrete core, the shear walls, or the exed inner core steel frames, together with a hinged outer frame has reduced the weight of skyscrapers very considerably. To realize the efficiency achieved by the core system, it is enough to notice that the Empire State Building, 102 stories high, has a total weight of steel of City, Fig. 7.10, where the exed walls are the narrow lateral walls of the building and resist the wind. Acting on the wider, longitudinally curved walls. In this building the wind on the narrow lateral walls is resisted by the frame action of the columns and beams without any need for an inner core. This mixed system using both exed walls and frame action could be used because the building has only 50 stories. The new concept of an outer core reduces the skyscraper to an immense, hollow, cantilever beam, stuck into the ground and anchored to heavy foundations. The towers of the World Trade Center have outside columns spaced only 3 feet from one another and connected by deep outer beams, or spandrels. They act more like shear walls with small window openings than as frames, and they give the cantilevered towers their needed lateral stiffness. Buildings like the towers of the World Trade Center or those of the John Hancock Insurance Company building in Chicago are often called tube buildings since their outer walls act as the walls of a hollow tube. They are the most efficient structures designed so far against the wind and can even be combined into a bundle of tubes, as was done by the Pakistani engineer Fazlur Khan, one of the great engineers of our time, in the tallest building in the world, the Sears Tower. This consists of 9 square tubes, each 75 feet square, erected one next to the other in a pattern of 3 squares by 3 squares and reaching different heights, Fig. 7.11. Although the Sears Tower is 1,450 feet high, the weight of its steel frame per square foot of floor is only 33 pounds. At the present time, 1980, this is the most notable refinement of the tube concept and the greatest achievement in the field of skyscrapers. 0. Reinforced concrete is lagging behind steel in terms of achieved building heights but has contributed interesting developments in the City, Fig. 7.10, where the exed walls are the narrow lateral walls of the building and resist the wind. Acting on the wider, longitudinally curved walls. In this building the wind on the narrow lateral walls is resisted by the frame action of the columns and beams without any need for an inner core. This mixed system using both exed walls and frame action could be used because the building has only 50 stories. The new concept of an outer core reduces the skyscraper to an immense, hollow, cantilever beam, stuck into the ground and anchored to heavy foundations. The towers of the World Trade Center have outside columns spaced only 3 feet from one another and connected by deep outer beams, or spandrels. They act more like sheer walls with small window openings than as frames, and they give the cantilevered towers their needed lateral stiffness. Buildings like the towers of the World Trade Center or those of the John Hancock Insurance Company building in Chicago are often called tube buildings since their outer walls act as the walls of a hollow tube. They are the most efficient structures designed so far against the wind and can even be combined into a bundle of tubes, as was done by the Pakistani engineer Fazlur Khan, one of the great engineers of our time, in the tallest building in the world, the Sears Tower. This consists of 9 square tubes, each 75 feet square, erected one next to the other in a pattern of 3 squares by 3 squares and reaching different heights, Fig. 7.11. Although the Sears Tower is 1,450 feet high, the weight of its steel frame per square foot of floor is only 33 pounds. At the present time, 1980, this is the most notable refinement of the tube concept and the greatest achievement in the field of skyscrapers. 0. Reinforced concrete is lagging behind steel in terms of achieved building heights but has contributed interesting developments in the field of skyscraper construction. In the reinforced concrete, 42-story Columbia Broadcasting System building in New York City, which was designed by Eero Saarinen and engineered by Weidlinger Associates in 1962, Fig. 7.12, wind forces are resisted by both an inner core and the shear wall facades of columns 5 feet wide and spaced 5 feet apart, connected by the rigid waffy floor slabs. Taller buildings in concrete have been first built in Brazil and then in the United States. The initial success of the Brazilian engineers was due to the fact that elevator requirements in their country are less stringent, so that the bottom concrete columns could occupy a larger amount of floor space, which in the United States had to be allotted to the elevators. With the increase in concrete strength obtained during the last few years, buildings of 750 feet and 800 feet have been erected in Brazil and in the United States, which at the present time holds the record with the 859 feet water tower building, erected in Chicago in 1977. Are skyscrapers a blessing for the densely populated areas of our modern metropolises, or are they a dehumanizing fruit of technology for technology's sake? Are they the symbol of our overpowering interest in financial returns or of our spiritual aspirations towards the conquest of natural difficulties? Are they an expression of a madly materialistic culture or the realization of man's dreams of long standing? Are these enormous, air-conditioned beehives the ideal environment for modern man, or are they a negation of our individuality and of our communication with nature? Whether we believe in skyscrapers or not, let us remember that the aspirations and realizations of man have taken different forms in different ages, and that most certainly the skyscrapers will also disappear when the time comes for their demise. The impermanence of our structures is the best hope for our future, whether it will take us to live in space or underground. 8. The Eiffel Tower. The symbol. The 3 largest steel structures in the world were products of an outburst of structural creativity in the last half of the 19th century. The Crystal Palace, erected for the 1851 Great Exhibition in London, covers the largest area. The Brooklyn Bridge, completed in 1883, has the longest span, and the Eiffel Tower, started in 1887, reaches the greatest height. All were made out of steel. The first 2 had utilitarian purposes. Sir Joseph Paxton's Crystal Palace not only served royally the Great Exhibition but, being demountable, was transferred afterwards to Sydenham, where it was used for sculpture, painting, and architectural exhibits, and for concerts until 1936. It was demolished in 1941, being an excellent guide for Nazi aircraft. The Brooklyn Bridge, built to connect the 2 great boroughs of New York City, reflected the desire to increase real estate values in Brooklyn. The Eiffel Tower, on the other hand, is a case in itself. Built for the Paris exhibition of 1889, it was meant to provide ostensibly nothing more or less than a magnificent view of Paris. Monsieur Eiffel extolled its utility as a military lookout, the salubrity of the air at its top, its uses as a laboratory to experiment with wind and gravity, but the inner spring to its construction was to demonstrate that France, 200 years after the Revolution, was a leader of the technical world, capable of realizing the dream of a tower 300 meters high, almost 1,000 feet. It would be twice as high as the Washington Monument, at that time the tallest structure. Fig. 8.1. Whatever its motivation, the tower in itself was and is totally useless from a practical point of view. If we leave aside defense towers built by the Saracens all along the Mediterranean coast and similar defense towers of the medieval walled towns of Italy and France, almost all the other great towers of the past were built for spiritual purposes. They rose next to Renaissance churches and from the tops of Gothic cathedrals calling with their bells the prayer hours. As minarets they served and still serve to remind Muslim worshippers of their well-timed duties. They were also built as symbols of civic pride on or next to city halls. If they could be used to warn of an approaching enemy or bring citizens to important gatherings, so much the better. And they were tall, 200, 300 feet and more, all of them of stone, masonry, or bricks. La Tour Eiffel acknowledges nothing so lofty or utilitarian. It was from the beginning a gigantic lark, a steel toy from which Parisians might admire their city, at the cost of $1.5 million. Academic painter, Garnier, the architect of the opera, Dumas, Jr., the novelist, Gounod, the composer, Leconte de Lisle, the poet, Prudhomme, the essayist, Guy de Maupassant, the novelist, all signed a resounding letter of indignant protest to the Minister of Public Works in an attempt to stop the horror. Guy de Maupassant, never relenting, had lunch at the tower as often as possible so as not to have to look at it. And he had a point, for the tower so dominated Paris it could be seen from anywhere in the city, except from inside one of its restaurants. If La Tour was an insult to the representatives of the effete class, it was love at first sight for the people. 2 million of them flocked to visit it during its first year. More than half of them reached its top. Thousands climbed the 1,671 steps before the elevators were open to the public. The crowds even increased long after the exhibition closed and, slowly but surely, their visits acquired new meanings. They went to look at the tower as much as to look from it, to look inside, at its filigree of steel, as much as to point out the other monuments of their city. It became the symbol of Paris, the Mecca of all travelers, visited by far more people than Notre Dame or Sacré-Cœur. And then it became, somehow, the symbol of France. Tourist posters ignored virtually all else. The new poets, writers, painters, and musicians exalted its shape, its lightness, its infinitely widening significance. It became the subject of 51 paintings by Delaunay, the initiator of the dismembered visual image, who drew it simultaneously from top and bottom, right and left. Hitler vowed to destroy it. The resistance fighters of World War II hoisted the tricolor from its top while the Nazi panzer divisions were still battling American tanks in the streets of Paris. The Algerian rebels planned to dynamite it, as did their French right-wing military opponents, both in vain. By then the tower had become like a mountain that always was and will always be. Paris would be inconceivable without it. Surpassed in height by many a modern utilitarian tower, by chimneys, antennas, and skyscrapers, it is still the Tower of Towers. Of no other man-made structure can one say that it transcended technology to become a great human symbol. The builder of the tower. No bourgeois is as bourgeois as a provincial Frenchman, and Alexandre Gustave Boenic Horseneufel, 1832–1922, was no exception. He was the soul of respectability. A dutiful and bright student, he nevertheless flunked an entrance examination to the prestigious École Polytechnique and thus attended École Centrale, studying chemical engineering. His modest goal was to gain employment in the vinegar factory of one of his uncles. Luckily the factory failed. Gustave Eiffel became a structural engineer and, not incidentally, a rich man. By 1867 he had started his own steel fabricating concern and began to be both the designer and the contractor of his own works. As a designer he championed a new breed of engineers, the mathematical engineer, who relied totally on his calculations after initial tests on hypotheses, materials, and procedures. He was not flamboyant in either speech or behavior, but had the calm self-assurance of the scientist-engineer, who studies a problem first, chooses the most practical among its many solutions, and proceeds, without hesitation, to the realization of his idea. He cannot be said to have invented any revolutionary device, but he perfected so many that his works add up to a large number of original insights. All of them are economical in execution and ingenious in conception. He was so methodical and unflashy as to contradict the classical image of the genius. But a genius he was. What else can we call a man who produced 14,352 square feet of drawings for the Eiffel Tower drawings, which called for 15,000 structural members and 2,500,000 rivet holes, and who put this immense jigsaw puzzle together without, as far as we know, a single error? A man whose every rivet slid smoothly into its respective hole. A man who erected the 8,000-ton tower without a single accident to its 250 workers, its only 250 workers. Who promised, and did deliver, the finished tower in 2 years, 2 months, and 5 days, on time for the opening of the exhibition, although progress was delayed by innumerable squabbles with the supervising committee and several strikes by his workers, who estimated the cost of the tower at $1,500,000 and built it, making a handsome profit, at 5% below budget. Who was so sure of his success that he agreed to finance the construction of the tower and to pay, outside of his contractual obligations, not only for all the workers' insurance but also for any damage claims by outsiders. And finally, a man who emerged triumphant from a financial scandal, and at age 57 started a new and brilliant 30-year career in the burgeoning science of aerodynamics. It has been said that genius is 90% perspiration and 10% inspiration. The most amazing aspect of Eiffel's genius is that he does not seem to have perspired. Gustave Eiffel did not come to the tower unprepared. For 20 years he had built train stations, dome observatories, large department stores, churches, and above all, bridges. All of his structures were made of steel. He designed and built all over the world, including Indochina, Russia, and Peru. Only one of his masterpieces is in the United States, the skeleton for the Statue of Liberty. Fig 8.2. In each structure he introduced some new concept. The dome of the observatory in Nice was so supported that it could be rotated by hand. His bridge pier caissons were so perfect that no worker suffered from the bends. When bridge piers could not be built in a river, he launched his bridges from both banks with the help of temporary cables, as Eads had done before him, see Chapter 10, but over much longer spans. He was the first bridge engineer to realize and assess the importance of wind forces on tall bridges and to lace them with trusses, see Chapter 11, to minimize their effects. In addition, he often laid the 2 steel arches supporting a bridge on inclined planes, one leaning against the other and supporting each other at their crowns to increase their resistance to lateral winds, Fig. 8.3. He spread apart the arch legs, as we do when we wish to resist a shove, Fig. 8.4. The use of bridge caissons made him thoroughly familiar with soil conditions, and his mastery of steel came from an exact knowledge, personally acquired, of its properties. When his company bid on the tower, he was ready technically, financially, and politically. Knowing that no great civic work was ever built without the help of the politicians, Eiffel made their job simple. He indoctrinated them so well that by the time the bid papers for the tower were ready, only one company in France could successfully bid on it, Eiffel and Company. A tower is a challenge to the wind. Its own weight and the weight of the people and the objects on it have to fight the overturning force of wind pressure, an enemy whose greatest blows have not been felt yet. This battle can be fought in two essentially different ways. The weight of the tower can be made so large that by brute force it will always counterbalance the wind. Or, more elegantly, one may make the surface of the tower so minimal that the wind has little on which to apply its pressure. Towers of brick and masonry had to rely on the first principle, but steel made the second possible. Eiffel, the master of steel and the first student of aerodynamics, relied entirely on the second method. He made his tower a filigree of steel on which the wind has almost no grip. All pieces of the tower, except some vertical columns, are an open lattice of light trusses through which the wind can blow. Eiffel also played safe. He assumed a wind, never yet encountered in Paris, of up to 148 miles per hour at the top of the tower, diminishing to 105 miles per hour at its foot, or with an even speed of 134 miles per hour from top to bottom. It was easy to prove that, even ignoring the laced nature of its surfaces, the weight of the tower could easily resist such wind forces. So much so that Eiffel could ignore in his design the weight of its 10,000 daily visitors, whose combined weight was at most a meager 10% of the weight of the tower. The scheme of the tower's design is simplicity itself. See Fig 8.1. Starting at the top, for steeply inclined, square, box columns come down to the level of the second platform, 380 feet above the ground. The four columns are connected by wind-bracing excess of laced trusses, which transform them into a rigid obelisk of steel, inside which run, one above the other, the last two elevators from the second to the third platform at the top of the tower. The slight curvature of the corner columns emphasizes the aspiration of the tower towards the sky. This feeling is reinforced by two secondary columns placed at the middle of the tower sides, also curved and meeting at an intermediate platform, where the two inside elevators stop to allow passengers to transfer from the lower to the upper. The second platform introduces a strong horizontal connection between the four upper columns, tying them together at their base, and is supported, in turn, not by four but 8 heavier columns. 4 on the outer corners of the tower continue with increasing curvature the slight curvature of the upper columns, while 4 on the middle of the sides are parallel to the corner columns. All 8 end at the first platform 180 feet above the ground. Below, each corner of the massive first platform is supported by 4 inclined buttresses consisting of 4 straight columns, each inclined inward at an angle of 54 degrees. These enormous buttresses spread the base of the tower to a square 420 feet on each side and give the visual impression that the tower is solidly grounded against any wind blowing on its thinner upper part, the top platform being a square only 30 feet square. The structure of the tower does not end at ground level. Its 8,000 tons must be supported by solid foundations, which consist of 4 immense, inclined concrete pylons going into the ground to depths depending on the strength of the soil under each of the 4 inclined buttresses they support. While excavating the ground for these pylons and pouring their concrete, Eiffel had to make use of his experience with underwater caissons, since the water of the Seine seeped into the soil of the Champs de Mars, where the tower is situated. The final silhouette of the tower is a visual representation of its structure, for massive buttresses inclined towards each other and prevented from falling by the powerful first platform, continued in the slimmer curved columns between the first and second platforms, and ending in the thin, almost vertical columns of the upper 620 feet of the tower, which support the tiny, domed, top platform and the flagstaff, now a TV antenna. The steel for this tallest of towers, not surpassed in height until 1929 by the erection of the Chrysler Building in New York, is so light that if the tower was squashed into a plate the size of its base 4 acres it would be only 2½ inches thick. But if the schma of the tower is simplicity itself, the erection of its 15,000 parts presented problems never encountered in engineering before. To begin with, the 4 inclined buttresses at the foot of the tower had to be temporarily supported during construction lest they fall inward before the erection of the first platform. To this purpose, Eiffel designed 4 gigantic wooden trusses which propped up the buttresses like the hands of giants, Fig. 8.5. Possibly the most difficult technical problem he encountered was that of the accuracy with which the 4 enormous buttresses had to meet the first platform at a height of 180 feet, so that the connections between the buttresses and the platform could be smoothly executed. If the inclination of the buttresses had been incorrect by only 1/10 of a degree, the rivet holes in the platform and the buttresses would have been 5 inches off and the connections could not have been realized. The constructive genius of Eiffel found a simple solution to this problem. He supported each of the 4 columns of the corner buttresses on a hydraulic jack, which could be operated by 2 men through a pump activating a piston. By controlling the amount of water in the cylinders of the jacks, the location of the bottom of the columns could be adjusted with great accuracy and then fixed by inserting an iron wedge between the column and its supporting concrete pylon. An ultimate refinement in the location of the top of the 4 buttresses was obtained by an even more ingenious method. At the points where the 4 corner buttresses were temporarily propped up by the gigantic wooden trusses, Eiffel placed steel cylinders, each filled with fine sand and with a hole at the bottom, and 4 jacks capable of lifting the buttresses from the wooden trusses. If a buttress was too high, even by a fraction of an inch, it was lowered by letting the sand run out of the cylinder. If the buttress was too low, the jacks could lift it, matching the rivet holes in the buttresses to those in the platforms. A round bar was pushed through the holes to align them perfectly and then a rivet, heated on a portable forge, was inserted into the holes and hammered by hand from the side opposite its head, creating a connection between the 2 elements that became tighter when the rivets cooled and shrank. Of course, the structural drawings for each one of the elements had to be extremely accurate and their fabrication just as exact for the 15,000 pieces to fit as perfectly as they did. The correct structural design of the tower has been proved through 90 years of use. The only structural change ever required was the opening up and lacing of 2 sides of the box columns between the first and the second platforms to allow easier inspection and painting. The incredible structural honesty of the tower design had to bow to the aesthetics of the time in only 2 areas. 10 gingerbread arches of steel were built around the first platform for purely decorative reasons. Obviously contrary to the linear design of the structure, they were eventually taken down, with a substantial improvement in the tower's appearance. Unfortunately, the second concession to the fashion of the times is still part of the tower structure. Eiffel himself, afraid of the reaction of the public to the inclined buttresses supported by the horizontal squaring of the first platform, added to the 4 sides of the tower, under the level of the first platform, for decorative arches that have no structural purpose whatsoever, see Fig. 8.1. He thought they might reconcile the Parisians to his daring design by reminding them of the familiar arches of their bridges. He thus gave the impression to the casual observer that the lower level of the tower was supported by commonly used arches, while these have no role but to fool the eye and detract from the strong action of the inclined buttresses leaning against the quadrilateral of the first platform. For aesthetic and structural reasons, these 4 fake elements should be dismantled, although by now they are thought to be an essential component of the tower shape. The outrageous fakery of the supporting arches becomes obvious where the lower parts of these arches, after just touching the supporting straight buttresses, curve inward like the arches of a mosque. Destroying the linearity and simplicity of the tower base, these arches are a detriment to the tower's aesthetics and its magnificent structural honesty. Cranes and elevators. Once the tower had been conceived and designed in all its details, two more problems had to be faced: how to lift the steel beams and columns to their final destinations and how to bring the estimated 10,000 daily visitors to the three platforms. These problems in mechanical engineering were somewhat outside the competence of Eiffel, although he had encountered the first in the construction of his large bridges. Aware of the speed with which relatively light steel elements could be maneuvered, he limited the weight of the heaviest piece to 3 tons. This allowed the use of small cranes and winches and paid in terms of ease and speed of construction. The first pieces were lifted by regular steam-powered cranes which had to be abandoned as soon as their reach was exceeded. At this point Eiffel introduced a system of cranes, Fig. 8.6, capable of creeping up the rails of the future elevators, set inside the bottom buttresses. The crane arms could rotate a full 360 degrees and cover the needs of an entire buttress. Once the first platform had been built, he used winches to lift the structural elements up to it and other winches to lift the additional elements from the first to the second platform. To move the steel components up to the top of the tower he again used a crane capable of creeping up the central columns that were to serve as guides for the top elevators, Fig. 8.7. This crane was supported on a frame that allowed it to move up 30 feet and then proceed to another frame set above the lower frame. Thus the central crane, which could reach all 4 columns of the upper part of the tower, needed only 2 temporary frames for its support. By this combination of cranes, winches, and creeping cranes the tower was erected in record time. The vertical transportation of visitors was an altogether new and more difficult problem. The most efficient passenger elevators developed until then were the work of the American inventor Elisha Graves Otis, who moved the cabins by means of a piston sliding inside a cylinder through the introduction of water under pressure. His invention had 2 significant and new features. The elevators were hung from cables attached through pulleys to the end of the piston, so as to allow a large cabin displacement with a piston of shorter length, and they had a safety device gripping the guides to prevent the fall of the elevators in the case of cable failure. European elevators at the time were instead directly supported from below by the vertical water-activated piston, and thus presented the safety feature of resting at all times on the piston. They could not fall under any circumstances. Eiffel, by contract, had to use French manufacturers for all parts of his tower. He thus had no choice but to request bids from French elevator companies. But none of them were willing to bid on the elevators for the curved run between the first and second platforms, and Eiffel and the supervising committee had to accept the bid of a suspended elevator from Otis. When all was said and done, the tower found itself with 3 totally different vertical circulation systems. 2 double-decker elevators ran inside the east and west buttresses from the first to the second platform. They were activated by an extremely complicated mechanism, never used again, consisting essentially of a gigantic bicycle chain moved by an enormous sprocket wheel, Fig. 8.8. Each roue convolution elevator could carry 100 people at a speed of 200 feet per minute, making a tremendous racket, but achieving the required goal. They were dismantled in 1900. The elevators in the north and south buttresses were designed by Otis. They carried 40 persons but ran smoothly at 400 feet per minute. One reached only the first platform, the other had a stop at the first, but continued to the second platform. Eiffel, the pragmatist, decided to test the safety of the hung elevator once and for all. He replaced the steel cables of the elevator with hemp rope, lifted the elevator 15 feet and cut the ropes. The elevator slowly descended along the rails, braked by the Otis safety device, and proved its value. The original proposal for the 2 upper elevators, going from the second platform to the top of the tower, was extremely original in that it consisted of a central shaft shaped like a gigantic screw, along which the elevators would be moved up and down by rotating nuts driven by 2 independent electric motors, one for each elevator. The supervising committee, however, got cold feet at the thought of using electric motors and disapproved the scheme. Thus the two elevators are operated by the classical European system of hydraulic pistons, only 36 feet long, whose run is magnified by steel cables running over sheaves. All the elevator problems could have been easily solved by adopting a single piston-run system going all the way to the top of the tower, but, for once, Eiffel put his foot down and refused to have the piston sunk 200 feet into the ground, exposed between the buttresses of the tower, ruining its elegant, upward-curving shape. Complicated as the adopted systems were, none interfered with the aesthetics of the tower. If the mechanical system do not have the simplicity and elegance of the structure, it must be said that they served their purpose and allowed visitors to reach the top of the tower in about 7 minutes. 90 years have gone by since the inauguration of the tower, and the original speed of its vertical circulation only hinted at the speeds to be reached by elevators in our high-rise buildings. It is, on the average, 2.4 feet per second in the tower and 20 to 40 feet per second in our skyscrapers. The life of the tower. Since 1889, tens of millions of visitors have been up the tower, but not all have used its elevators. In 1906, a race was run up to the first platform and won by a man in 3 minutes flat. A slower time was clocked for a Mr. Dutroux in 1959, but he did it on one leg. Going down, of course, is an easier task, and someone did on a bicycle in 1923 only to be beaten by another cyclist 26 years later, this time on a unicycle. If the main reason for climbing a mountain is the fact that it is there, man-made mountains have the same attraction as real ones for mountain climbers, and a 1,000-foot tower is bound to have for them an irresistible fascination. In 1954, a German student climbed to the top along the outside trusses of the tower, stopping during the night for a short bivouac and reaching the top the morning after. But climbing was officially recognized as a proper and actually glorious way of reaching the towers. Top when a party led by a famous Italian mountain climber went all the way to the top along the west column, followed by millions of television viewers, to celebrate the 70th anniversary of the tower's erection. And in true rock climbing style, the leader upheld from the top to the second platform along his rope. Like other dramatic structures, the tower has been since its opening a favorite jumping platform for suicides. An average of 4 people a year kill themselves from it, although the B.RST did not jump but hanged himself from its beams. Only the Golden Gate Bridge can compete with the tower in this lugubrious count. Over 12 people a year have committed suicide from it since it was opened to traffic. But not all that happened at the tower was sad or crazy. Thanks to the unquenchable thirst of Eiffel for new scientific knowledge, during his lifetime it became an important station for the study of weather and, above all, of aerodynamics. Eiffel had an apartment in the tower, still maintained as a museum, where he spent many hours dedicated to the new science of flight. He was the B.RST to prove experimentally that the suction over the upper surface of a wing is more important to its weight carrying capacity than the air pressure under it. His studies were recognized all over the world and particularly in the United States. The gentleman divided his time between his studies, his investments, and his family, apparently unruffled by the storm of scandal in which he found himself involved. While he was designing and building the tower, as if this commitment were not enough for his energy, he had become the technical director of the new French company which, under the leadership of de Lesseps, the mastermind of the Suez Canal, was working on the first phase of the Panama Canal. Eiffel designed and began to build all the enormous steel gates for the canal and was directing the excavation through the jungle that had stymied all his predecessors. A combination of bribes, political corruption, antisemitism, and hostility from the United States put a sudden end to this gigantic endeavor and, for a while, tarnished the good name of Eiffel. Cleared of any malfeasance a few years later, he renounced any and all construction work and gave his time and attention exclusively to aerodynamics. The unflappable bourgeois gentleman did not seem hurt by the episode or by the renunciation of his lifetime career in construction. He wined and dined his friends in his apartment in the tower and enjoyed his family, particularly on his birthdays, when every member had to be present to celebrate the unsmiling father and grandfather. His autobiography, completed 3 months before his death, has not been published. According to a statement by one of his grandchildren, he left only one typed copy of it to each of his 5 children. Hence we do not know what Eiffel thought of himself, and it is most improbable that he would have given himself away even in a private work of this kind, but we have a glimpse of the man in a statement he is said to have often made: "I should be jealous of the tower. It is much more famous than I am." Considering his indefatigable achievements through 90 years of life, we may understand his veiled regret. But if official Paris has been strangely cool towards her son, how many engineers have a monument erected, not in a cemetery but in the middle of a bustling metropolis, at once a center of life and a symbol of science and country, instantly recognizable by name the world over? The taller towers. For 40 years the Eiffel Tower was the tallest in the world. There are now 4 skyscrapers and at least 4 TV towers taller than Eiffel's masterpiece. A reinforced concrete tower in Moscow reaches 1,750 feet. The Canadian National Railroad Tower in Toronto is 1,805 feet tall, with the help of a 300-foot antenna, Fig. 8.9. The antenna in Fargo, North Dakota is 2,063 feet tall, but it cheats. It is a guide tower, restrained by inclined steel wires. And the same can be said of the 2,117-foot TV antenna in Warsaw. Higher towers will certainly be built in the near future now that both structural theory and aerodynamics have acquired sounder knowledge. But they will never mean what the Eiffel Tower meant, first to the French and then to the world. They will be built for a purpose and not for an idea. They will attract attention but not become symbols. They will show how easy it is to improve on a first achievement once it becomes obvious that such an achievement is possible. The Eiffel Tower will always be the tallest tower in the world, since the achievements of man are measured by more than mere feet. 9 bridges. Arches. The world of bridges is so infinitely varied that the layman must be somewhat baffled by it. Why is one bridge as light and elegant as a suspension span and another as massive as a medieval castle of brick, arches, and buttresses? Why does one steel bridge have an arch above the roadway and another an arch below it? Why do some bridges have an arched shape while others are straight? Why are some made out of reinforced concrete and others out of steel? The answers to all these questions, and many others, rest on the fact that the type of bridge best suited to a particular site depends on a large number of factors. The length to be spanned, the nature of the river banks, the free height required under the bridge, the variations in the river's water level, the materials and the specialized labor available for its construction, the kind of traffic present and that to be expected, the kind of road approaches usable, and, last but not least, economic and even aesthetic considerations together with the preferences of the engineer will play a role in the choice of a bridge. Type. If one considers all the possible combinations of these factors, then no large bridge can be identical with any other. Each is, or ought to be, the best structural solution to a very specific problem and, since bridges are almost all structure, one should look at them first from the structural point of view to understand how the various types work. Their behavior is quite simple to grasp as the infinite world of bridges divides itself into at most 4 or 5 basic types. Let us look first at the arch bridge. 144. If a weight is hung from a piece of string held in 2 hands, the string takes a triangular shape with 2 straight sides meeting at the point where the weight hangs. If 2 weights hang, separately, from the string, its shape changes to one with 3 straight sides. When many weights hang from the string shape has many short, straight sides and looks rather like a curve, Fig. 9.1. The cables of a suspension bridge are loaded by a large number of weights hanging from the numerous suspenders. If we could look at them with binoculars, we would see a shape consisting of many straight sides, but so many of them that from far away the cables look smoothly curved. The varying shapes taken by a string or a cable under varying weights are called string or, from the Latin funiculum string, funicular polygons, that is, many-angled figures. Very thin, flexible elements can work only in tension. Strings and cables are so flexible that they cannot resist compression or bending, as a beam does. They can only resist pulls, and since they straighten when pulled, they are always straight between hanging loads. This is why, in order to carry loads by tension only, cables must change shape whenever loads change in location or number. The adaptability of cables to carrying different loads in tension, while wonderful, presents practical difficulties. Our structures are submitted to varying loads, but it would be inconvenient to have structures change shape all the time. Thus, to stop a cable from changing shape, we must stiffen it by means of a beam or truss, which we have seen in Chapter 5 to be rigid in bending. In supporting a single weight by means of a string held in two hands, we may notice an important fact. Besides pulling up on the string ends to balance the weight pulling down, we must also pull outward to counteract the tendency of the two string ends to move towards each other, Fig. 9.2. These outward pulls of our hands are called thrusts. Similarly, in a suspension bridge the anchorages, massive masonry or concrete blocks built into the ground, pull not only down, but outward on the cables to provide them with the needed thrusts. Once the behavior of a cable is grasped, one easily realizes that an arch is nothing but an upside-down cable. Imagine ripping a loaded cable over after freezing it in its curved shape. The cable becomes an arch. The pull, or tension, in the cable becomes a push, or compression, in the arch, and the outward thrusts on the cable become the inward thrusts on the arch, which prevent it from opening up, Fig. 9.3. Of course, to freeze the arch shape, often called the antifunicular of the loads, we must make it stiff, and hence much thicker than a slender cable, or it will buckle, as all thin, compressed elements tend to do. And because the arch has to be stiff to prevent its buckling, it does not need a stiffening truss. It keeps its shape under a variety of loads and is said to be stable, while a cable without a stiffening truss is unstable. Since an arch is compressed all over its own weight, the roadway, and the traffic loads all pushed down on it can be built of materials strong in compression, like stone, brick, and concrete. The availability of natural compressive materials explains why our ancestors built arch bridges and arched roofs over 2,500 years ago. The Romans, who were masters of masonry construction, used arches profusely and in a variety of applications. Masonry and brick arch bridges were found all along their road network and also in their monuments. The Colosseum's outer walls are pierced by arches, the Roman baths were covered by arched vaults, and the Pantheon has a large domed roof that works somewhat like a series of arches set around a circle, see Fig. 13.5. Their aqueducts carried water along the top of as many as 3 sets of superimposed arches. The maximum span of a Roman arch was about 100 feet and its shape was always that of a half-circle, because of the ease of erecting circular wooden scaffolds or centerings for their construction. While a long-span cable can be spun from tower to tower without any intermediate support, see Chapter 10, a masonry arch is built of separate blocks or voussoirs which must be temporarily supported on a centering, still usually made out of wood. The arch is started simultaneously from both ends of the centering, and when the top block or keystone is wedged between the two adjoining blocks, Fig. 9.4, the centering can be lowered since each half-arch leans on the other, as Leonardo observed. Once the arch is built, its ends must be prevented from spreading apart. The inward forces or thrusts needed to keep the arch from opening can be provided by the banks of the river when these consist of solid rock. OT1RYs, heavy buttresses of masonry or concrete must be built that resist the tendency of the arch to push outward, just as the anchorages resist the tendency of the suspension bridge cables to pull inward. Modern arch bridges are often built of reinforced concrete poured in place or of large blocks, often hollowed to make them lighter, which are prefabricated on land and lifted on top of the centering, where their reinforcing bars are welded and the blocks are glued to one another by strong cement mortar. The longest reinforced concrete bridge built so far connects the Adriatic island of Krk to the mainland of Yugoslavia and spans 1,280 feet, Fig. 9.5. To carry the roadway, vertical columns or struts of varying length must be built up from the arch. These are the counterpart of the suspenders in the suspension bridge. The weight of the roadway and the vehicles pushes down on the struts that are compressed, while the roadway is supported by a series of beams spanning from strut to strut. These beams, stiff in bending, and the roadway itself contribute to the overall stiffness of the arch bridge and act very much like the stiffening truss of a suspension bridge. The extremely elegant bridges of the Swiss engineer Robert Meyer consist of very thin concrete arches, sometimes only 7 inches thick over a span of 300 feet, which share the task of carrying the loads with the concrete beams and slabs of the roadway. An upside-down picture of a Meyer bridge looks exactly like a suspension bridge, explaining visually their opposite, but analogous behavior, Fig. 9.6. The longest arch bridges in the world today are built of steel. They look and work very much like reinforced concrete bridges and usually have the advantage of being lighter because of the high strength of steel in compression. Now, 1980, the very longest is the New River Gorge Bridge in West Virginia, which spans 1,700 feet, Fig. 9.7. Previously it was the Kill Van Cole Bridge, connecting Staten Island to New Jersey, but not by much. It was purposely made just RVE feet longer than the famous steel bridge at the entrance of Sydney Harbour in Australia so that the United States could boast the longest steel arch bridge in the world. Railroad bridges. The heroic age of bridge construction coincided with the expansion of the railroads in Great Britain and the United States. The first modern locomotive, the Rocket, was invented and built by George Stephenson in 1829, and the first passenger railroad was inaugurated in England in 1825. But the greatest of railway achievements was the spanning of the American West in the 19th century. The networks of the Baltimore and Ohio, the Erie, and the Pennsylvania railroads and the first transcontinental railway, the Union Pacific, completed in 1860. Forgetful of the violence and chicanery which characterized this era, we have developed a great nostalgia for the old railroads, manifested in the expensive and widely appreciated hobby of toy trains. Both children and parents actively participate in it, and while the first outgrow it, the last often don't. To carry the unprecedented loads of the locomotives and the railroad cars across deep gorges and wide rivers, all kinds of new bridges had to be built, with great urgency and increased strength. After a few wooden spans were erected, mostly in the form of trestles, Fig. 9.8, with their narrowly spaced towers of timber connected by short, heavy timber beams. The miraculous new iron material, steel, was universally adopted. Steel arches, large trusses, cantilevered bridges, lift, bascule and pivoted bridges mushroomed throughout the country. Meanwhile, after the example of England, France had built by 1840 the largest railway system in Europe. Germany, Italy, and Russia followed suit. The railroad gauge had been standardized to a width of 4 feet 8½ inches by 1880, and for about 100 years the railroad reigned supreme all over the world. Bridges 151. Possibly the most common structure used in railroad construction to span rivers and valleys was the truss. Hence, a brief discussion of railroad bridges must start with an analysis of this most ingenious extension of the beam, involving straight bars of steel working only in tension or in compression. As the span of a beam and the loads on it increase, its dead load increases rapidly out of proportion with the loads it has to carry. We have seen in Chapter 5 how efficiency is improved by giving the beam an shape, provided its depth is increased and the flanges are set farther and farther away from each other. Consequently, the web connecting them becomes deeper and heavier. And here is where the basic idea of the truss comes in. To lighten the web, why not open up holes in it, obtaining a perforated beam? Finally, as the dimensions of the beam make its fabrication as a single rolled element impractical or impossible, why not build it up by connecting the upper bar to a lower bar by means of inclined and vertical bars, Fig. 9.9, which constitute, so to say, a discontinuous web. To make this built-up beam rigid, its meshes or holes, created by the web bars, should be of a triangular shape, since the triangle, as the great bridge builder John Roebling put it, is the most indeformable geometric figure. A triangulated truss is thus obtained, which can be made as deep as necessary and is substantially lighter than a full web beam. Why buildings stand up? Since a truss supported at its ends is but a perforated one beam, its upper flange or chord is compressed, while its lower chord works in tension, see Chapter 5. The web bars resist the equivalent tension and compression of the beam shear and work in tension or compression depending on their inclination. Since all the bars of the truss are either tensed or compressed, they work much more efficiently than the layers of a beam, in which the material near the middle, neutral axis does very little work at the expense of the material of the flanges. It is no wonder that trusses are used for 1001 applications in all kinds of structures, from those stiffening the core of high-rise buildings, which were called XZ frames in Chapter 7, to the prefabricated trusses called bar joists available on the market in lengths from 20 to 100 feet, with cords and diagonals of steel, Fig. 9.10a, or cords of wood and diagonals of steel pipe, Fig. 9.10b, from the enormous steel trusses used in bridge construction to those made of laminated wood and used in roof construction. Steel trusses with horizontal parallel cords were patented during the railroad era with a variety of patterns for the web bars, Fig. 9.11, and each is called to this day by the name of its inventor. But soon the concept of triangulating a steel structure was extended to trusses with one or both cords in a curved shape, and finally large steel bridges were built as triangulated arches, as they are to this day, see Fig. 9.7. Prior to the advent of the railroad, most of the freight traffic, of course, traveled through a network of canals and rivers on barges, pulled first by mules and eventually by locomotives. Memories of our canals still linger in the lovely songs of the 19th century, and the words Erie Canal evoke dreams of peaceful travel on slow water through the locks. The canal lobby fought the railroads. Whenever a railroad bridge was planned to cross a river or canal at grade level, a cry arose about impeding the water traffic, and the bridge was required to cross high above the water. These clearances reached hundreds of feet under some of our important bridges, and such rules are even today strictly enforced by the Corps of Engineers of the U.S. Army, who have jurisdiction over water traffic. This makes the erection of a bridge at times a very costly enterprise. One of the reasons for the variety of bridge types lies in the effort to beat this problem. To begin with, the roadway of an arch bridge can be located at the level of its supports or abutments, whenever these are high enough above the river. Two birds are killed with one stone in this case, since the roadway and the approaches to the bridge are cheaper and, moreover, the roadway acts as a tie between the arch ends, preventing their spreading out, and supplying the needed thrusts. When the bridge crosses a deep gorge, an inverted arch can be set under the roadway, really acting as a tensed cable, with the advantage of allowing the use of smaller bars, since no additional strength is required against buckling in compression. If the roadway cannot be located in its lowest position, it may be built halfway up the arch or above it. In its lowest position the roadway hangs from the arch, in its highest it is supported on it by means of compressive struts, in the intermediate location it is partly hung and partly supported. The next ingenious idea is aimed at allowing a free flow of river traffic during construction of the arch by eliminating its centering founded at the bottom of the river. It was Eads, the great bridge engineer of the second half of the 19th century, who first conceived of erecting the two halves of the arch as cantilevers by supporting them at their tips with cables from temporary towers until the two cantilevered halves met and were joined at midspan. The Great Three-Arch Steel Bridge over the Mississippi was built by Eads by this daring new method in 1867, Fig. 9.12. It was almost a natural step to build next cantilevered arches in which the temporary cables were replaced by permanent steel members, thus obtaining a bridge supported both by its upper members acting as cables and its lower members acting as arches. One of the greatest bridges ever built, the Firth of Forth Bridge in Scotland. With a span of 1,700 feet, cantilevers its three sections from three piers but has in addition two truss bridges end supported on the tips of the cantilevers, Fig. 9.13. Although erected in 1890, it remains the second longest bridge of its kind in the world and was overtaken by the Quebec Bridge only in 1917. The last expedient to free the navigable channel from impediments during the arch, or truss, construction consists in building the arch on its centering away from the site, then floating both centering and arch to the site, and finally rapidly connecting the arch to its abutments. This procedure is also most efficient when the waters under the bridge are subject to short, violent floods or storms. The greatest of French concrete engineers, Resonant, used this method to erect the monumental Plougastel Bridge in northern France in 1920, lifting the heavy arch from the centering by means of hydraulic jacks. To get a low bridge out of the way when river traffic must go through, a variety of movable bridges has been invented. In one type the center span consists of two trusses, each pivoted at one end, and capable of rotating upward when a boat needs to go by. It is called a bascule bridge, Fig. 9.14. Or the center span may be lifted between two end towers, as in so many bridges in the New Jersey industrial area and the large bridge over the Harlem River in New York, the first link of the Triborough Bridge system, Fig. 9.15. Or finally the entire center span of a bridge may be made to rotate horizontally on a central pier, as in some of the bridges crossing the Harlem River, thus clearing two separate channels on the sides of the pier, Fig. 9.16. 4 times. Concrete bridges. Some if not all of the bridge concepts born under the impact of the railroads and executed in steel have been extended to concrete. The trestle, built of wood at first and then of steel, has acquired a new elegant expression in the long viaducts built in Europe. These consist of hollow piers of reinforced concrete, at times 200 to 300 feet high, over which runs a roadway of hollow reinforced or pre-stressed concrete pipes of rectangular shape which are prefabricated on the river banks and slid into position. In the latest application of this principle the roadway pipes are extruded continuously, like spaghetti from a pasta maker, from both ends of the bridge until they meet at midspan. The simplicity, slenderness, and pure geometric shape of these viaducts make them works of beauty, Fig. 9.17, showing that high technology does not have to sacrifice aesthetics to economy. One of the longest bridges in the world, over 5 miles long, the Maracaibo Bridge in Venezuela, Fig. 9.18, designed by Ricardo Morandi, is built in concrete with a complex sequence of 20 end-supported spans of 120 feet, followed by 77 spans of 150 feet, cantilevered from trestles and supporting shorter spans on their trips, and by 5 780-foot cantilevered spans supported by cables at their ends, which in turn support short spans on their tips on the same principle as the Firth of Forth Bridge. The construction of this monumental work took only 40 months, and its roadway has a clearance of 150 feet over the navigable channel. Longer bridge and tunnel systems are used to cross wide stretches of water, like the Chesapeake Bay Bridge, consisting of 12 miles of concrete trestles and including a 2-mile-long tunnel. But the longest bridges in the world are those that do not have to contend with water traffic and can be laid right on the water. These floating bridges consist of reinforced concrete hollow barges or pontoons anchored to the bottom of the water. by draping steel cables, Fig. 9.19, and connected to each other by elastic joints that allow them to move slightly with respect to each other in case of violent storms. If water traffic is necessary, one of the pontoons rotates on a vertical pivot at one end and opens up a gate while floating in the water. The Hood Canal Pontoon Bridge over Lake Washington in Seattle is 6,250 feet long. If the magnificence of modern bridges cannot be appreciated from a fast-moving automobile, there are few experiences to equal crossing a large bridge on foot. The half-mile walk over the Red Golden Gate Bridge in San Francisco, suspended over the blue waters of the Pacific and profiled against the cloud-dotted sky, the short promenade over the middle deck of the Brooklyn Bridge against the background of the New York skyline, the leisurely bicycle ride over the George Washington Bridge with the view of Manhattan from the high-rises of the Columbia Medical Center to the towers of the World Trade Center, are as exciting as the passage along the heavy cantilevered trusses of the Queensboro Bridge or that on the Williamsburg Bridge reached through the cavernous stairs in its towers. And what is more exhilarating than to cross the suspension bridge over the Tagus River in Lisbon, surrounded by a landscape of incredible beauty and the memory of Columbus sailing for the Indies, or to walk the Bosphorus Bridge connecting Europe to Asia? Human enjoyment rests on physical contact with reality. Bridges can best be 0 backslash colon 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 r underscore dot equals backslash equals plan understood and appreciated as expressions of the human spirit and works of subtle beauty when crossed on foot. Humanly useful technology can, in fact must, go hand in hand with beauty. The hideousness of some of our surroundings is not inherent in the development of our technical culture. Space frames. A large horizontal roof over a rectangular area, unimpeded by intermediate columns, is but a bridge in 2 dimensions, which can be crossed from any of the walls supporting it to its opposite wall. Some of the bridge systems in steel and concrete have, therefore, been adapted to fill the roofing needs of our large convention and exhibition halls. The inventiveness of Pierluigi Nervi suggested the use of a suspension bridge for the roofing of a paper plant in Mantua, Italy, which demanded a clear span of 830 feet with a width of 100 feet. The roof towers were inclined backwards to resist the thrusts of the cables and were propped by shorter concrete struts so as to look like gigantic Greek letters lambda, while the roof surface was the deck of the suspension bridge, Fig. 9.20. In collaboration with the steel engineer Cover, Nervi thus produced one of the longest roofs in the world with great economy and, as usual in his work, pleasing aesthetic results. Bridges. The same principle of the suspension bridge, but in a cantilevered form using essentially one half of a bridge, has been used in airplane hangar roofs, which require one entire openable wall to allow the entrance and exit of the planes. Such cantilevered roofs can be seen in some of the hangars at the JF Kennedy Airport in New York and in other airports around the world. At JFK, a cantilevered cable-supported roof has been arranged in an elliptical pattern for the Pan Am Terminal with cantilevers of 150 feet, Fig. 9.21. For more nearly square areas, like those of convention and exhibition halls, it would seem logical to support the roof surface on a rectangular grid of vertical TMSs which can be built of bars of few different sizes. Such systems would be practical but for 2 reasons: the cost of the joints formed by the TMSs meeting at right angles and, more importantly, the fact that the system consists of rectangles, and rectangles are not inherently stiff. One of the great minds in the field of American invention, Alexander Graham Bell, was the first to realize that if such a roof could be triangulated in space, it would acquire a much greater stiffness in all directions and hence could be made lighter. Thus the modem space frame sprang from the mind of an electrical engineer and gave rise to a whole family of roofs having the enormous advantage of modular construction, easy assemblage, economy, and visual impact. These roofs consist essentially of a number of pyramids, some with bases up and others down, creating two parallel horizontal grids of bars interconnected by zigzagging bars in at least 3 directions, Fig. 9.22. One obstacle postponed their adoption. The mathematical calculations required by their design are so time-consuming that they did not become practical until the advent of the electronic computer. Thus one field of engineering had to rely on another before a new conception could become reality. The space frame is today one of the most economical steamixtures for covering large areas. The largest was erected in Brazil, where the translucent plastic roof of the exhibition hall at Anhembi Park in São Paulo is supported by an aluminum space frame covering an area 853 feet square, subdivided by tubular tripod supports into squares 197 feet on each side. Such is the visual appeal of the zigzagging bars of a space frame, that they were used, by IMPay, in the roofing of the magnificent main hall of the new wing of the National Gallery in Washington, as well as in the roofing of the immense Air and Space Museum in the same city. And just for the sake of their appearance, vertical space frames have been used as transparent walls on entire sides of large buildings or as roofs over interior courtyards. The structure of both the walls and the roof of the new convention hall in New York City, occupying an area of 2 by 5 city blocks, consists of a single space frame covered with reflecting glass. It is hard to put into words the many reasons for the visual appeal of space frames. Their lightness, their transparency, and their geometry, which seems to vary dramatically with a change in vantage point, certainly contribute to it. But their aesthetic content is so high that Kenneth Snelson has become famous the world over for his beautiful tensegrity sculptures, which are nothing but spaceframe towers and girders floating in space. Tensegrity, invented and patented by Snelson, has added a new component to the elegance and airiness of the space frame. Since its bars work either in compression or in tension, Snelson uses aluminum or steel pipes as compressed members and connects them with a continuous steel cable that constitutes the tension bars. He does this in such a way that no two pipes touch each other, Fig. 9.23. Thus, no continuous compression path can be discovered in the structure of his sculptures, and the compressed pipes seem to float independently in space. Down-to-earth engineers of the 19th century invented the humble truss for purely utilitarian purposes. Now it has become an expression of art. This may be a lesson to the detractors of technology, who emphasize its negative aspects and ignore the many facete meanings of so many of its fruits. 10. The Brooklyn Bridge. The creator of the bridge. On May 24, 1883, the mayors of Brooklyn and New York, Lowe and Edson, Governor Cleveland of New York and President Chester Arthur, followed by a throng of thousands, inaugurated the Brooklyn Bridge, Fig. 10.1. The engineer in charge of its construction, Washington Roebling, was not there. Paralyzed from the waist down by the bends he suffered while working in the underwater caisson for the tower's foundations, he watched through binoculars from his house on the Brooklyn shore. What he saw was a masterpiece conceived by John Roebling, his father, 36 years earlier, and built by the son over a period of 14 years. The Brooklyn Bridge was a reality and a symbol, the longest suspension bridge in the world with a main span of 1,595.5 feet, a monument to the persistence of two men and a woman, the two Roebelings and Emily Warren, Washington's wife. It is, perhaps, the most beautiful bridge in the world. There is no view more exciting than that of the Manhattan skyline at sunset seen through the network of inclined stays, vertical suspenders, and curved cables of the bridge. It made Greater New York a possibility by uniting its two most populous boroughs. It was conceived so wisely that, notwithstanding the unexpected increase in traffic, it needed strengthening only by the addition of light trusses, 70 long years after its construction. Designated a landmark in 1964, it carries a plaque on the west face of the Brooklyn Tower which reads, "The builders of the bridge dedicated to the memory of Emily Warren Roebling 1843 to 1903. whose faith and courage helped her stricken husband Cole, Washington A. Roebling, C.E. 1837 to 1926 complete the construction of the bridge from the plans of his father John A. Roebling, C.E. 1806 to 1869, who gave his life to the bridge. Back of every great work we can find the self-sacrificing devotion of a woman. This tablet erected 1951 by the Brooklyn Engineers Club with funds raised by popular demand. John A. Roebling, the designer of the bridge, was born in Germany and studied architecture and engineering in Berlin. A liberal opposed in principle to the Prussian government, he was inspired to come to the United States by no less a teacher than the philosopher August Hegel. Upon arriving in America, Roebling and his young friends established the town of Saxonburg in Pennsylvania on a plan drawn by Roebling, who soon after conceived an idea that made himself and Saxonburg rich. He suggested the substitution of steel wire rope for the hemp hawsers then used to pull the boats of the Portage Railroad. Roebling and his friends built a factory for the wire's manufacture. The first step towards the erection of the bridge had been taken, and the Roebling Wire Rope Company is to this day one of the most important manufacturers of steel cables in the world. In 1841, the 35-year-old Roebling got his first chance to use steel wires in a suspension bridge over the Allegheny River. This led to his second stroke of genius. He proposed not only to reconstruct an aqueduct over the river as a suspension bridge, but to build its cables using a new procedure. Rather than lay all the wires constituting a cable on the ground, as was traditional, then fastening them together and lifting them up to the top of the towers, Roebling proposed to spin the wires from one anchorage in the ground, over the towers, to the other anchorage and to tie them together in their naturally acquired curved configuration. This method required fording first a few light ropes of twisted steel wires across the river, lifting them up to the towers by means of hoists, and then spinning the cable wires back and forth from one anchorage to the other by shuttling along a catwalk. Hanging from the ropes. His method is still used in all suspension bridges today, when the weight of the cables has become so great that it would be impossible to lift them to the top of the towers after they have been assembled. On May 17, 1854, the Wheeling Bridge over the Ohio River, spanning 1,010 feet and designed by Roebling's rival Charles Ellet, collapsed during a windstorm. A local reporter described the disaster, lunging like a ship in a storm. The deck rose to nearly the height of the towers, then fell, and twisted and writhed, and was dashed almost bottom upward. By substituting Tacoma for Wheeling, this becomes the exact description of the Tacoma Narrows Bridge failure in 1940 due to aerodynamic effects. Roebling, undaunted, it had not been his bridge rush to propose a new suspension bridge on the Ohio, and his superb engineering intuition led him to a third stroke of genius: inclined cables or stays, connecting the tops of the towers to various points on the sides of the deck. These prevent the opposite up and down motions of the deck sides and stop any twisting. Aerodynamic oscillations. Again, Roebling's stays are used in some modern suspension bridges, and this concept has been recently extended to the idea of supporting the deck by stays alone, doing away with curved suspension cables. Pioneered by German engineers, stayed bridges are rapidly taking the place of suspension bridges for spans of intermediate length, Fig. 10.2. These were ingenious and creative times. While Roebling was rebuilding the Wheeling Bridge, his rival Ellet was busy with the construction of a suspension bridge over Niagara Falls. This bridge eventually was finished by Roebling. Obviously, one could not ford the initial ropes through the onrushing waters, but it occurred to Ellet to call for a competition among youngsters, with a prize of $5 to the first who would hitch-wire a kite across the falls. The competition was successful, and Ellet attached to the kite string a very light steel wire, then a heavier one to the light wire, and continued the process until his first wire bundle exhibited its lovely catenary shape across the falls. Ellet's idea has been extended to the erection of large balloon roofs by carrying the steel cables required by this type of roof, see Chapter 15, from one anchorage to the other by means of a helicopter. As if to rehearse the great feat of the Brooklyn Bridge, John Roebling was entrusted in 1856 with the construction of a 1,200-foot span over the Ohio River in Cincinnati. His bridge looks almost exactly like the bridge, except for some minor stays attached under, rather than above, the deck. Roebling was almost 60 and, incredible but true, ready then to leave bridge building to younger folks. His wish was not to be satisfied. The thought of connecting Brooklyn to Manhattan had occurred often since the year 1800 and had always been rejected as a physical or financial impossibility. But in 1866 a company was chartered by New York State to build a totally undefined bridge between the two cities, and Boss Tweed of Tammany Hall, the Democratic New York stronghold, and a number of his cronies bought stock in the company, at an 80% discount after a first bribe the 1st of May of $65,000. Like the Roman Emperor Vespasianus, who set a tax on public urinals and answered the objections of his advisers by the famous saying, "Non olet, money never stinks," Roebling, a man of absolute integrity, accepted this shady participation, well knowing that without the help of the politicians his dream would never become reality. The project, almost complete in every structural and construction detail, was approved by an advisory committee of the best civil engineers in the country 3 years later. When the corruption of the Tammany Ring was exposed, Tweed and his friends were expelled from the charter company. By 1876 the federal government required the mayors, controllers, and chief aldermen of the two cities to sit on the executive committee for the bridge, and some kind of honesty was restored to its administration. The creator of the bridge was barely able to start its construction. The year of the bridge approval. After he had sent his son Washington and his wife Emily to Europe for almost a year to study the use of underwater air-pressured caissoons for the foundation of bridges, John Roebling's right foot was caught between the boat fender and the pilings of a ferry slip from which he was studying the Brooklyn Tower location. Tetanus developed, and on July 21, 1869, John Roebling died. A month later his son, Colonel Washington Roebling, a graduate of Rensselaer Polytechnic Institute and a hero of the Civil War, was appointed to his father's position as chief engineer for the bridge. The saga of its construction had started. The construction of the bridge. The first step in the construction of a bridge, built on piers or towers under the level of the water, is the placement of their foundations at the bottom of the river. James Eads, one of the great bridge engineers of the 19th century, had learned the technique of compressed air caissoons for bridge foundations during a convalescent trip to France. The caissoons consist of enormous watertight boxes or working chambers, Fig. 10.3, that have no bottom, from whose top a well-like steel shaft extends above the water level. A pump pushes compressed air through pipes in the shaft into the working chamber until the water in the chamber is pushed out. The workers, soon nicknamed sandhogs, descend into the submerged chamber and, breathing the highly compressed air, excavate the soil at its open bottom. Other workers meanwhile build the bridge towers of brick and stone on the solid top of the working chamber. As the soil is excavated, the cutting steel edges of the chamber's sides penetrate into the soil, pushed down by the increasing weight of the tower being built on its roof. This operation is continued until the cutting edges reach solid rock or sufficiently strong soil, at which time the chamber and the steel shafts are filled with concrete and constitute the foundation of the tower, which, partly underwater, is built above water to the height required by the design. When a sandhog has to move down to the working chamber, he first stops in a small Deckham 7 Dreschen chamber or airlock. At the top of the shaft, Fig. 10.3. This is closed tight and pumped full of air until it is at the same pressure as the working chamber. The sandhog can then proceed down by opening a hatch at the bottom of the airlock, whose pressure has been equalized to that in the working chamber. On the way out the sandhog must again enter the airlock through a bottom hatch and wait until the pressure in it is decreased and equalized to that of the outside air. The hatch in the ceiling of the airlock is then opened and the sandhog can get out. This last operation is critical. It must occur very slowly because the nitrogen gas which at high pressure is dissolved in the blood, forms bubbles if the pressure is suddenly or rapidly reduced, and these bubbles can impede or even stop the blood circulation, producing serious damage and often death. While the caissoons are a few feet underwater, this danger is relatively minor, but at depths greater than 30 feet the pressure required to keep the water out of the working chamber is so high that upon rapid decompression the sandhog feels a sudden, acute pain in the stomach that bends him double. Hence the nickname of the condition, the bends paralysis. Follows. Washington Roebling adopted caissoons for the foundations of the bridge. The caisson on the Brooklyn side was 168 feet by 102 feet, made out of wood, with a roof 20 feet thick and walls decreasing from 8 feet at the top to 2 inches at the cutting steel sheathing edge. It was to be founded 4 to 4 feet underwater. The New York side caisson was 172 feet by 102 feet with a roof 22 feet thick and was to be founded 72 feet underwater. All kinds of accidents plagued the descent of the Brooklyn caisson. On December 2, 1870, a fire in it was caused by the flames of the lights or of a worker's candle that set fire to the oakum caulking of the caisson's walls. It had to be flooded and its sides and roof patched up. Another source of dangerous incidents was the miscalculated overpressure in the working chamber causing the air to bubble out of the caisson's bottom along the sides. Minor bubbles did not blow out much of the working chamber air, but major ones, like the one called the Great Blowout, spouted rock, mud, and water to a height of 500 feet. Luckily the Great Blowout occurred on a Sunday at 6 in the morning, when nobody was in the chamber. The chamber had to be flooded again to compensate for the lost air pressure, which was also reduced when the airlocks were opened by mistake. Miraculously almost no damage occurred as the caisson dropped suddenly 10 inches into the soil. But by the middle of 1875 the Brooklyn Tower had reached its height of 316 feet, as its caisson had gone down at the rate of 3 feet per week thanks to the dynamite used to blast the big boulders found on the way down. New York caisson produced the first cases of the bends. 110 sandhogs were hit and 3 died during the first 5 months of 1872, a toll equal to the incidents in the caissons built by Eads for the Mississippi River Bridge in St. Louis. The doctor in charge of Eads's St. Louis Bridge had been struck by the bends himself, and was the first to realize their cause. He established a decompression rate of not more than 6 pounds of pressure per minute, a substantial improvement over the few minutes of decompression used by the sandhogs, but a far cry from the maximum of 1 pound of pressure reduction per minute in use now. With the rate adopted by Roebling, the danger of the bends for workers at a depth of 72 feet was great indeed. Although Roebling reduced their shift to 2 hours and allowed only the strongest men to work at great depths, incidents of this type continued to occur, and finally, chief engineer, who was with his sandhogs so very often, was struck himself. Paralyzed from the waist down, Washington found in his wife Emily the faithful interpreter of his ideas and the new leader of the construction crew. While he sat in his room overlooking the river from the Brooklyn side, Emily carried out his orders, handled the urgent daily problems, drew sketches, dealt with the workers, and became an expert on bridge construction, aware of every detail of this complex work. Forceful but shy by nature, she refused any and all honors in favor of her husband and at the end of construction retired to their house, where she died in 1903, leaving her husband and John, her child born in Europe during their caisson studying trip. The sister of General Warren of Civil War fame, she was born and rests in Cold Spring, New York, one of the very first liberated women of the 19th century to dedicate some of her best energies to engineering. Finally by 1872 both caissons had reached bottom, the Brooklyn caisson on rock and the New York caisson on hard sand, 7 to 9 feet under the river level. Caissons and wells were filled with concrete and the New York Tower was completed in 1876, a year after the Brooklyn Tower. They are 140 feet long and 59 feet wide at water level, and 136 feet long and 53 feet wide at their top. Each has two 119 feet high and 34 feet wide Gothic arches, where the roadway meets the towers. They are two most imposing monuments, contrasting the slenderness of the steel cables with their massive granite structure. Finally, work on the cables could start. From laboring 79 feet underwater, the crew now proceeded to work at 266.5 feet above it, a height surpassed then only by the spire of Trinity Church. Washington Roebling lost the bid for the cable wires to a competitor, the Hague Wire Company of Brooklyn. Like his father before him and James Eads before his father, Washington did not trust the steel companies of the day and insisted on having each batch of wire tested in the factory before shipment to the site. With this guarantee he proceeded. He hoisted a wire rope from its anchorage in Brooklyn over the Brooklyn Tower, ferried it across the river, hoisted it over the New. The words on her tombstone say, Emily Warren Roebling, gifted, noble, true. The wife of Washington A. Roebling. Not a word about the bridge. And back. 278 wires constituted a bundle called a strand, and 19 strands constituted a cable, 15 3/4 inches in diameter. 4 cables were spun over 4 saddles, 2 close to the center line of the bridge and 2 along its outer edges. The strength of the ropes supporting the catwalks had been spectacularly tested by the chief mechanic and assistant bridge engineer, E.F. Farrington, who crossed the river both ways on a bosun's chair hanging from a pulley over the first rope, to the acclaim of the populace, the first user of the Brooklyn Bridge, Fig. 10.4. But on June 14, 1878, a strand of wires broke loose from the New York anchorage, fell into the river, barely missed a ferry boat, killed 1 worker instantly, fatally injured another and hurt 3 more. A scandal developed, and Roebling was accused of having used some weaker Bessemer steel from his own company. A thorough investigation proved instead that his rival's company had all along faked the strength tests on the wire by the simple expedient of testing a batch of good wire, loading it on a wagon for transportation to the site, unloading the wagon en route, and reloading it with inferior wire. This operation was repeated with successive wagon loads, using the same batch of good, tested wire each time. Roebling had 150 wires added to the cables to compensate for the strength deficiency of the delivered wire, and the Hague Wire Company was allowed to keep their contract. Once the 19 strands of each cable had been spun, they were wrapped in a tight spiral of coated steel wire, supplied by the Roebling Company. The wire spiral binds the strands to make them work together, gives the cables a circular shape, and prevents water from reaching the wire strands. 380 suspenders of steel rope attached to the cables reach down to the level of the roadway deck, and stays of decreasing slope connect further points on the deck to the top of the towers. The stays are strong enough to support the weight of the deck in case of suspender or cable failure, a most unlikely event since, like all good engineers, John Roebling had been a most conservative man. The cables can carry a weight 6 times heavier than the weight of the roadway. The work of 7 years had only one purpose: to build a support for the roadway, over which the flow of trains, carriages, and pedestrians was to run. The roadway is supported by transverse steel trusses hanging from the suspenders and connected by longitudinal beams to constitute a steel grid. It was built by starting simultaneously at the 2 towers and moving towards the center of the bridge. The 2 vertical stiffening trusses along the edges of the bridge were erected on this grid. They are 10 feet high and are connected at their top by transverse beams. The roadway thus has a rectangular pipe shape with sides built of trusses. This type of construction is very rigid, resists twisting and adds strength against dangerous twisting bridge oscillations due to wind. The original roadway had 6 lanes, 2 near the center line of the bridge for the railroad tracks and 2 double lanes on the outside for carriages, Fig. 10.5. In addition, a pedestrian path ran at a higher level along the center line of the bridge. In 1948, D.B. Steinman, a world-famous bridge engineer and an impassioned New Yorker, was entrusted with the strengthening of the bridge. The train lanes were converted to car traffic and additional light trusses were added over the side trusses, Fig. 10.5. These impede somewhat the view from the bridge, but do not impair its beauty. Together with the complex network of new approaches on the New York side, the almost 100-year-old bridge is fulfilling its mission as well or better today than it did in 1883. Even the greatest works can be and are often misused by the unwise. The Brooklyn Bridge, dedicated to the union of two cities, fruit of the unswerving devotion of its engineers and workers, a catalyst to the erection of 15 additional bridges connecting Manhattan to Brooklyn, the Bronx, and New Jersey, and Brooklyn to Staten Island, has become the favorite jumping platform for suicides. They fall 135 feet, but even so some have been known to survive. Robert Odium jumped first in 1885 and died. The legendary Steve Brodie, who boasted about his jump to the clients of his bar, probably never did jump. Stuntmen have also jumped with mixed results. But the largest number of people killed by the bridge in one day occurred only a week after its opening. 12 were trampled to death in a panic perhaps created by someone who yelled that the bridge was falling. Their senseless deaths remind us of the tragic deaths of the more than 20 workers killed on the job and of the maiming of its creators. Emily was given only 13 years to gaze upon the bridge that absorbed her labor for longer.